Okay, so I decided not to do the project's only information security part and skip right to the machine learning section. So I'm gonna start now.
So in this first section, I'm going to spend a few minutes discussing the difference between artificial intelligence, neural networks, and machine learning. Now, the reason we need to go into this is because we're going to be covering all of these topics throughout this course, so it's vital that you guys understand what these actually mean and you can kind of differentiate between them. So that's what we're going to focus on now. Now, quick disclaimer here, just so everyone's aware, I'm using something called Windows Ink. This just default comes with Windows. I have a drawing tablet down here, and this is what I'm going to be using for some of the explanatory parts where there's no real coding, just to kind of illustrate some concepts and topics to you. Now, I have very horrible handwriting. I'm not artistic whatsoever. Programming is definitely more of my thing than, drawing and doing diagrams and stuff. But I'm going to try my best, and this is just the way that I find I can convey information the best to you guys. So anyways, let's get started and discuss the first topic here, which is artificial intelligence. Now, artificial intelligence is a huge hype nowadays, and it's funny because a lot of people actually don't know what this means, or they try to tell people that what they've created is not artificial intelligence, when in reality it actually is. Now, the kind of formal definition of AI, and I'm just going to read it off of my slide here to make sure that I'm not messing this up, is the effort to automate intellectual tasks normally performed by humans. Now, that's a fairly vague definition, right? What is considered an intellectual task? And really, that doesn't help us too much. So what I'm going to do is bring us back to when AI was first created to kind of explain to you how AI has evolved and what it really started out being. So back in 1950, there was kind of the question being asked by scientists and researchers, can computers think? Can we get them to figure things out? Can we get away from just hard coding and, can we get the computer to think? Can it do its own thing? So that was kind of the question that was asked, and that's when the term artificial intelligence was kind of coined and created. Now, back then, AI was simply a predefined set of rules. So if you think of an AI for maybe like tic-tac-toe or an AI for chess, all they would have had back then is predefined rules that humans had come up with and typed into the computer in code, and the computer would simply execute those set of rules and follow those instructions. So there was no deep learning, machine learning, crazy algorithms happening. It was simply, if you wanted the computer to do something, you would have to tell it beforehand, say you're in this position and this happens, do this. And that's what AI was. And very good AI was simply just a very good set of rules, where a ton of different rules that humans had implemented into some program. You could have AI programs that are stretching, 500,000 lines of code just with tons and tons and tons of different rules that have been created for that AI. So just be aware that AI does not necessarily mean anything crazy complex or super complicated, but essentially if you're trying to simulate some intellectual task, like playing a game that a human would do with a computer, that is considered AI. So even a very basic artificial intelligence for a tic-tac-toe game where it plays against you, that is still considered AI. And if we think of something like Pac-Man, right, where we have, our little ghost, and this will be my rough sketch of a ghost, but we have our Pac-Man guy who will just be this, well, would we consider this ghost AI? What it does is it attempts to find and kind of simulate how it would get to Pac-Man, right? And the way this works is just using a very basic pathfinding algorithm. This has nothing to do with deep learning or machine learning or anything crazy, but this is still considered artificial intelligence. The computer is figuring out how it can kind of play and do something by following an algorithm. So we don't necessarily need to have anything crazy, stupid, complex to be considered AI. It simply needs to just be simulating some intellectual human behavior. That's kind of the definition of artificial intelligence. Now, obviously today, AI has evolved into a much more complex field where we now have machine learning and deep learning, all these other techniques, which is what we're going to talk about now. So what I want to start by doing is just drawing a circle here, and I want to label this circle and say AI like that. So this is going to define AI because everything I'm about to put inside of here is considered artificial intelligence. So now let's get into machine learning. So what I'm going to do is draw another circle inside of here. We're going to label this circle ML for machine learning. Now notice I put this inside of the artificial intelligence circle. This is because machine learning is a part of artificial intelligence. Now what is machine learning? Well, what we talked about previously was kind of the idea that...
And I'm gonna skip these parts because I already know roughly.
means it's going to make the fewest mistakes possible. Because just like a human, our machine learning models, which are trying to simulate, human behavior, can make mistakes. So to summarize that, essentially, machine learning, the difference between that and kind of, algorithms and basic artificial intelligence is the fact that rather than us, the programmer, giving it the rules, it figures out the rules for us. And we might not necessarily know explicitly what those rules are when we look at machine learning and create machine learning models, but we know that we're giving some input data, we're giving the expected output data, and then it looks at all of that information, does some algorithms, which we'll talk about later on that, and figures out the rules for us. So that later, when we give it some input data and we don't know the output data, it can use those rules that it's figured out from our examples and all that training data that we gave it to generate some output. Okay, so that's machine learning. Now we've covered AI and machine learning, and now it's time to cover neural networks or deep learning. Now this circle gets to go right inside of the machine learning right here. I'm just going to label this one NN, which stands for neural networks. Now neural networks get a big hype. They're usually what the first, when you get into machine learning, you want to learn neural networks. You're kind of like, neural networks are cool, they're capable of a lot. But let's discuss what these really are. So the easiest way to define a neural network is it is a form of machine learning that uses a layered representation of data. Now we're not going to really understand this completely right now, but as we get further in, that should start to make more sense as a definition. But what I need to kind of illustrate to you is that in the previous example, we just talked about machine learning. Essentially what we had some input bubbles, which I'm going to define as these. We had some set of rules that is going to be in between here, and then we had some output. And what would happen is we feed this input to this set of rules. Something happens in here, and then we get some output, and then that is what our program does. So that's what we get from the model. We pretty much just have two layers. We have kind of the input layer, the output layer, and the rules are kind of just what connects those two layers together. Now in neural networks and what we call deep learning, we have more than two layers. Now I'm just trying to erase all this quickly so I can show you that. So let's say, and I'll draw this one another color because why not? If we're talking about neural networks, what we might have, and this will vary and I'll talk about this in a second, is the fact that we have an input layer, which will be our first layer of data. We could have some layers in between this layer that are all connected together, and then we could have some output layer. So essentially what happens is our data is going to be transformed through different layers, and different things are going to happen. There's going to be different connections between these layers, and then eventually we will reach an output. Now it's very difficult to explain neural networks without going completely in depth, so I'll cover a few more notes that I have here. Essentially in neural networks we just have multiple layers. That's kind of the way to think of them. And as we see machine learning, you guys should start to understand this more, but just understand that we're dealing with multiple layers, and a lot of people actually call this a multi-stage information extraction process. Now I did not come up with that term, I think that's from a book or something, but essentially what ends up happening is we have our data at this first layer, which is that input information, which we're going to be passing to the model, that we're going to do something with. It then goes to another layer where it will be transformed, it will change into something else using a predefined kind of set of rules and weights that we'll talk about later. Then it will pass through all of these different layers where different kind of features of the data, which again we'll discuss in a second, will be extracted, will be figured out, will be found until eventually we reach an output layer where we can kind of combine everything we've discovered about the data into some kind of output that's meaningful to our program. So that's kind of the best that I can do to explain neural networks without going on to a deeper level. I understand that a lot of you probably don't understand what they are right now, and that's totally fine, but just know that they are a layered representation of data. We have multiple layers of information, whereas in standard machine learning we only have 1 or 2 layers, and in artificial intelligence in general we don't necessarily have to have like a predefined set of layers. Okay, so that is pretty much it for neural networks. There's one last thing I will say about them is that they're actually not modeled after the brain. So a lot of people seem to think that neural networks are modeled after the brain and the fact that you have neurons firing in your brain and that can relate to neural networks. Now there is a biological inspiration for the name neural networks and the way that they work from human biology, but it is not necessarily modeled about the way that our brain works. And in fact, we actually don't really know how a lot of things in our brain operate and work. So it would be impossible for us to say that neural networks are modeled after the brain because we actually don't know how information is kind of happens and occurs and transfers through our brain, or at least we don't know enough to be able to say this is exactly what it is in neural networks. So anyways, that was kind of the last point there. Okay, so now we need to talk about data. Now data is the most important part of machine learning and artificial intelligence, neural networks as well, and it's very important that we understand how important data is and what the different kind of parts of it are because they're going to be referenced a lot in any of the resources that we're using. Now what I want to do is just create an example here where I'm going to make a data set that is about students' final grades in a school system. So essentially we're going to make this a very easy example where all we're going to have for this data set is we're going to have information about students. So we're going to have their midterm 1 grade, their midterm 2 grade, and then we're going to have their final grade. So I'm just going to say midterm 1, and again, excuse my handwriting here, it's not the easiest thing. That's a 70, their midterm 2 grade, maybe that was final grade. Now obviously we could have some other information here that we're omitting, like their midterm 2 grade. So this is where we're going to talk about features, and features, our input information, are going to be midterm 1 and final. Term 2 here is what we would call the label or the output. Now, the label is simply what we are trying to look for or predict. So when we talk about features versus labels, features is our input information, the information that we have that we need to use to make a prediction, and our label is that output information that is just representing what we're looking for. So when we feed our features to a model, it will give to us a label, and that is kind of the point that we need to understand. So that was the basic here. And now I'm just going to talk a little bit more about data because we will get into this more as we continue going and about the importance of it. So the reason why data is so important is this is kind of the key thing that we use to create models. So whenever we're doing AI and machine learning, we need data pretty much, unless you're doing a very specific type of machine learning and artificial intelligence, which we'll talk about later. Now for most of these models, we need tons of different data. We need tons of different examples, and that's because we know how machine learning works now, which is essentially we're trying to come up with rules for a data set. We have some input information, we have some output information, some features, and some labels. We can give that to a model and tell it to start training, and what it will do is come up with rules such that we can just give some features to the model in the future, and then it should be able to give us a pretty good.
Yeah, just basic stuff on this first one. And I've seen this guy YouTube channel. I think his videos are
Now, what
really good.
is a tensor? Now, tensor just immediately seems kind of like a complicated name. You're like, all right, tensor, like this is confusing. But what is it? Well, obviously, this is going to be a primary aspect of TensorFlow, considering the name similarities. And essentially, all it is a vector generalized to higher dimensions. Now, what is a vector? Well, if you've ever done any linear algebra or even some basic kind of vector calculus, you should hopefully know what that is. But essentially, it is kind of a data point, is kind of the way that I like to describe it. And the reason we call it a vector is because it doesn't necessarily have a certain coordinate. So like if you're talking about a 2-dimensional data point, you have, maybe an x and a y value, or like an x1 value and an x2 value. Now, a vector can have any amount of dimensions in it. It could have 1 dimension, which simply means it's just one number. It could have 2 dimensions, which means we're having 2 numbers, so like an x and a y value. If we're thinking about a 2-dimensional graph, we have 3 dimensions if we're thinking about a 3-dimensional graph, so that would be 3 data points. We could have 4 dimensions if we're talking about sometimes some image data and some video data, 5 dimensions, and we can keep going with vectors. So essentially what a tensor is, and I'll just read this formal definition to make sure I haven't butchered anything that's from the actual TensorFlow website. A tensor is a generalization of vectors and matrices to potentially higher dimensions. Internally, TensorFlow represents tensors as n-dimensional arrays of basic data types. Now we'll understand what that means in a second, but hopefully that makes sense. Now, since tensors are so important to TensorFlow, they're kind of the main object that we're going to be working with, manipulating, and viewing, and it's the main object that's passed around through our program. Now, what we can see here is each tensor represents a partially defined computation that will eventually produce a value. So just like we talked about in the graphs and sessions, what we're going to do is when we create our program, we're going to be creating a bunch of tensors, and TensorFlow is going to be creating them as well, and those are going to store partially defined computations in the graph. Later, when we actually build the graph and have the session running, we will run different parts of the graph, which means we'll execute different tensors and be able to get different results from our tensors. Now, each tensor has what we call a data type and a shape, and that's what we're going to get into now. So, a data type is simply what kind of information is stored in the tensor. Now, it's very rare that we see any data types different than numbers, although there is the data type of strings and a few others as well, but I haven't included all of them here because they're not that important. But some examples we can see are float 32, int 32, string, and others. Now, the shape is simply the representation of the tensor in terms of what dimension it is. And we'll get some examples because I don't want to explain the shape until we can see some examples to really dial in. But here are some examples of how we would create different tensors. So what you can do is you can simply do tf.variable, and then you can do the value and the data type that your tensor is. So in this case, we create a string tensor, which stores one string, and it is tf.string, so we define the data type second. We have a number tensor, which stores some integer value, and then that is of type tf int 16. And we have a floating point tensor, which stores a simple floating point. Now, these tensors have a shape of, I believe it's going to be 1, which simply means they are a scalar. Now, a scalar value, and you might hear me say this a lot, simply means just one value. That's all it means. When we talk about like vector values, that typically means more than one value. When we talk about matrices, we're having different, it goes up, but scalar simply means one number. So yeah, that is what we get for the different data types and creating tensors. We're not really going to do this very much in our program, but just for some examples here, that's how we do it. So we've imported them. So I can actually run these, and I mean, we're not going to really get any output by running this code because, well, there's nothing to see. But now we're going to talk about the rank/degree of tensors. So another word for rank is degree. So these are interchangeably. And again, this simply means the number of dimensions involved in the tensor. So when we create a tensor of rank 0, which is what we've done up here, we call that a scalar. Now the reason this has rank 0 is because it's simply one thing. We don't have any dimensions to this. There's like zero dimensionality if that is even a word. It's just one value. Whereas here we have an array. Now when we have an array or a list, we immediately have at least rank 1. Now the reason for that is because this array can store more than one value in one dimension, right? So I can do something like test, I can do okay, I could do Tim, which is my name, and we can run this, and we're not gonna get any output obviously here, but this is what we would call a rank 1 tensor, because it is simply one list, one array, which means one dimension, and again, that's also like a vector. Now this, what we're looking at here, is a rank 2 tensor. The reason this is a rank 2 tensor is because we have a list inside of a list, or in this case, multiple lists inside of a list. So the way that you can actually determine the rank of a tensor is the deepest level of a nested list. At least in Python with our representation, that's what that is. So here we can see we have a list inside of a list, and then another list inside of this upper list. So this would give us rank 2, and this is what we typically call a matrix. And this, again, is going to be of tf.string, so that's the data type for this tensor variable. So all of these we've created are tensors. They have a data type, and they have some rank and some shape, and we're going to talk about the shape in a second. So to determine the rank of a tensor, we can simply use the method tf.rank. So notice when I run this, we get the shape, which is blank, of rank 2 tensor. That's fine. And then we get numpy 2, which simply means that this is of rank 2. Now if I go for that rank 1 tensor, and I print this out, so let's have a look at it, we get numpy 1 here, which is telling us that this is simply of rank 1. Now if I want to use one of these ones up here and see what it is, so let's try it. We can do number, so tf.rank number, so we'll print that here, and we get numpy 0 because that's rank 0, right? So we'll go back to what we had, which was rank 2 tensor, but again, those are kind of the examples we want to look at. Okay, so shapes of a tensor. So this is a little bit different now. What a shape simply tells us is how many items we have in each dimension. So in this case, when we're looking at rank 2 tensor.shape, so we have .shape here, that's an attribute of all our tensors, we get 2, 2. Now let's look up here. What we have is, well, look at this, 2 and 2. So we have 2 elements in the first dimension, right, and then 2 elements in the second dimension. That's pretty much what this is telling us. Now let's look at the rank or the shape of rank 1 tensor. We get 3. So because we only have a rank 1, notice we only get one number. Whereas when we had rank 2, we got 2 numbers, and it told us how many elements were in each of these lists, right? So if I go and add another one here, like that, and we have a look now at the shape. Oops, I gotta run this first. So that's something, can't convert non-square to tensor. Sorry, so I need to have a uniform amount of elements in each one here. I can't just do what I did there, so I'll add a third element here. Now what we can do is run this, shouldn't get any issues. Let's have a look at the shape, and notice we get now 2, 3. So we have 2 lists, and each of those lists have 3 elements inside of them. So that's how the shape works. Now I could go ahead and add another list in here if I wanted to, and I could say like, okay, so let's run this. Hopefully no errors. It looks like we're good. Now let's look at the shape again, and now we get a shape of 3, 3, because we have 3 interior lists, and in each of those lists we have 3 elements. And that is pretty much how that works. Now, again, we can go even further here. We can put another list inside of here. That would give us a rank 3 tensor, and we'd have to do that inside of all of these lists. And then what that would give us now would be 3 numbers representing how many elements we have in each of those different dimensions. Okay. So changing shape. All right, so this is what we need to do a lot of times when we're dealing with tensors in TensorFlow. So essentially, there is many different shapes that can represent the same number of elements. So up here, we have 3 elements in a rank 1 tensor, and then here we have 9 elements in a rank 2 tensor. Now there's ways that we can reshape this data so that we have the same amount of elements but in a different shape. For example, I could flatten this, where I take all these elements and throw them into a rank 1 tensor that simply is a length of 9 elements. So how do we do that? Well, let me just run this code for us here and have a look at this. So what we've done is we've created tensor 1 that is tf.1s. What this stands for is we're going to create a tensor that simply is populated completely with 1s of this shape. So shape 1, 2, 3, which means, that's the shape we're going to get. So let's try this out and look at tensor 1 just so I can better illustrate this. So tensor 1, look at the shape that we have. 1, 2, 3, right? So we have one interior list, which we're looking at here, and then we have 2 lists inside of that list, and in each of those lists we have 3 elements. So that's the shape we just defined. Now we have 6 elements inside of here. So there must be a way that we can reshape this data to have 6 elements but in a different shape. In fact, what we can do is reshape this into a 2, 3, 1 shape, where we're going to have 2 lists, right? We're going to have 3 inside of those, and then inside of each of those we're going to have 1 element. So let's have a look at that one. So let's have a look at tensor 2. Actually, what am I doing? We can print all of them here. So let's just print them and have a look at them. So when we look at tensor 1, we saw this was a shape, and now we look at this tensor 2, and we can see that we have 2 lists, right? Inside of each of those lists we have 3 lists, and inside of each of those lists we have 1 element. Now finally, our tensor 3 is a shape of 3, -1. Well, what is -1? When we put -1 here, what this does is infer what this number actually needs to be. So if we define an initial shape of 3, what this does is say, okay, we're going to have 3 lists. That's our first level. And then we need to figure out, based on how many elements we have in this reshape, which is the method we're using, which I didn't even talk about, which we'll go into in a second, what this next dimension should be. Now, obviously, this is going to need to be 3, so 3, 3, right? Because we're going to have 3 lists, and inside of each of those lists we need to have, or actually, is that correct? Let's see if that's even the shape. 3, 2, my bad. So this actually needs to change to 3, 2. I don't know why I wrote 3, 3 there, but you get the point, right? So what this does is we have 3 lists, we have 6 elements. This number obviously needs to be 2 because, well, 3 times 2 is going to give us 6, and that is essentially how you can determine how many elements are actually in a tensor by just looking at its shape. Now, this is the reshape method, where all we need to do is call tf.reshape, give the tensor and give the shape we want to change it to, so long as that's a valid shape. And when we multiply all of the numbers in here, it's equal to the number of elements in this tensor. That will reshape it for us and give us that new shaped data. This is very useful. We'll use this actually a lot as we go through TensorFlow, so make sure you're kind of familiar with how that works. All right, so now we're moving on to types of tensors. So there's a bunch of different types of tensors that we can use. So far, the only one we've looked at is variable. So we've created tf.variables and kind of just hard-coded our own tensors. We're not really going to do that very much, but just for that example. So we have these different types. We have constant, placeholder, sparse tensor, variable, and there's actually a few other ones as well. Now, we're not going to really talk about these two that much, although constant and variable are important to understand the difference between. So we can read this. So with the exception of variable, all of these tensors are immutable, meaning their value may not change during execution. So essentially, all of these, when we create a tensor, mean we have some constant value, which means that whatever we define here, it's not going to change. Whereas the variable tensor could change. So that's just something to keep in mind. When we use variable, that's because we think we might need to change the value of that tensor later on. Whereas if we're using a constant value tensor, we cannot change it. So that's just something to keep in mind. We can obviously copy it, but we can't change it. Okay, so evaluating tensors, we're almost at the end of this section, I know, and then we'll get into some more kind of deeper code. So there will be some times for this guide we need to evaluate a tensor, of course. So what we need to do to evaluate a tensor is create a session. Now, this isn't really, like, we're not going to do this that much, but I just figured I'd mention it to make sure that you guys are aware of what I'm doing if I start kind of typing this later on. Essentially, sometimes we have some tensor object, and throughout our code, we actually need to evaluate it to be able to do something else. So to do that, all we need to do is literally just use this kind of default template block of code. Where we say with tf.session as some kind of session, doesn't really matter what we put here. Then we can just do whatever the tensor name is, .eval. And calling that, we'll actually have TensorFlow just figure out what it needs to do to find the value of this tensor. It will evaluate it, and then it will allow us to actually use that value. So I put this in here. You guys can obviously read through this if you want to understand some more depth on how that works. And the source for this is straight from the TensorFlow website. A lot of this is straight up copied from there, and I've just kind of added my own spin to it and made it a little bit easier to understand. Okay, so we've done all that. So let's just go in here and do a few examples of reshaping just to make sure that everyone's kind of on the same page, and then we'll move on to actually talking about some simple learning algorithms. So I want to create a tensor that we can kind of mess with in reshape. So what I'm going to do is just say t equals, and we'll say tf.ones. Now what what tf.ones does is just create, again, all the values to be ones that we're going to have in whatever shape. Now we can also do zeros, and zeros is just going to give us a bunch of zeros. And let's create some like crazy shape and just visualize this. Let's do like a 5 by 5 by 5. So obviously, if we want to figure out how many elements are going to be in here, we need to multiply this value. So I believe this is going to be 625 because that should be 5 to the power 4. So 5 times 5 times 5 times 5. And let's actually print t and have a look at that and see what this is. So we run this now, and you can see this is the output we're getting. So obviously, this is a pretty crazy looking tensor, but you get the point, right? And it tells us the shape is 5 by 5 by 5. Now watch what happens when I reshape this tensor. So if I want to take all these elements and flatten them out, what I could do is simply say, we'll say t equals tf.reshape like that, and we'll reshape the tensor t to just the shape 625. Now if we do this and we run here, oops, I got to print t at the bottom after we've done that, if I could spell the print statement correctly. You can see that now we just get this massive list that just has 625 zeros. And again, if we wanted to reshape this to something like 125, and maybe we weren't that good at math and couldn't figure out that this last value should be 5, we could put a -1. This would mean that Tensorflow would infer now what the shape needs to be. And now when we look at it, we can see that what we're going to get is, well, just simply 5 kind of sets of these, I don't know, matrices, whatever you want to call them, and our shape is 125, 5. So that is essentially how that works. So that's how we reshape. That's how we kind of deal with tensors, create variables, how that works in terms of sessions and graphs. And hopefully with that, that gives you enough of an understanding of tensors, of shapes, of ranks, of values, so that when we move into the next part of the tutorial, we're actually writing code, and I promise we're going to be writing some more advanced code, you'll understand how that works. So with that being said, let's get into the next section.
Don't understand what reshaping does. Other than changing the format of the thing. But maybe he's gonna talk about it later.
So welcome to Module 3 of this course. Now what we're going to be doing in this module is learning the core machine learning algorithms that come with Tensorflow. Now these algorithms are not specific to Tensorflow, but they are used within there, and we'll use some tools from Tensorflow to kind of implement them. But essentially these are the building blocks before moving on to things like neural networks and more advanced machine learning techniques. You really need to understand how these work because they're kind of used in a lot of different techniques and combined together. And what I'm about to show you is actually very powerful if you use it in the right way. A lot of what machine learning actually is, and a lot of machine learning algorithms and implementations and businesses and applications and stuff like that, actually just use pretty basic models, because these models are capable of actually doing very powerful things. When you're not dealing with anything that's crazy complicated, you just need some basic machine learning, some basic classification. You can use these kind of fundamental core learning algorithms. Now, the first one we're going to go through is linear regression, but we will cover classification, clustering, and hidden Markov models, and those are kind of going to give us a good spread of the different core algorithms. Now, there is a ton, like thousands of different machine learning algorithms. These are kind of the main categories that you'll cover, but within these categories, there is more specific algorithms that you can get into. I just feel like I need to mention that because I know a lot of you will have maybe seen some different ways of doing things, and this course might show you, a different perspective on that. So let me just quickly talk about how I'm going to go through this. It's very similar to before. I have this notebook, as I've kind of talked about. There's a link in the description. I would recommend that you guys hit that and follow along with what I'm doing and read through the notebook. But I will just be going through the notebook, and then occasionally what I will actually do, oops, I need to open this up here, is go to this kind of untitled tab I have here and write some code in here. Because most of what I'm going to do is just copy code over into here so we can see it all in kind of one block, and then we'll be good to go. And the last note before we really get into it, and I'm sorry I'm talking a lot, but it is important to make you guys aware of this, you're going to see that we use a lot of complicated syntax throughout this kind of series and the rest of the course in general. I just want to make it extremely clear that you should not have to memorize or even feel obligated to memorize any of the syntax that you see. Everything that you see here, I personally don't even have memorized. There's a lot of what's in here that I can't just come up with off the top of my head. When we're dealing with kind of a library and module so big that, like Tensorflow, it's hard to memorize all those different components. So just make sure you understand what's happening, but you don't need to memorize it. If you're ever going to need to use any of these tools, you're going to look them up, you're going to see what it is, you're like, okay, I've used this before, you're going to understand it, and then you can go ahead and copy that code in and use it in whatever way you need to. You don't need to memorize anything that we do here. All right, so let's go ahead and get started with linear regression. So what is linear regression? Well, it's one of the most basic forms of machine learning, and essentially what we try to do is have a linear correspondence between data points. So I'm just going to scroll down here to a good example. So what I've done is use Matplotlib just to plot a little graph here, so we can see this one right here. And essentially, this is kind of our data set. This is what we'll call our data set. What we want to do is use linear regression to come up with a model that can give us some good predictions for our data points. So in this instance, maybe what we want to do is, given some x value for a data point, we want to predict the y value. Now in this case, we can see there's kind of some correspondence linearly for these data points. Now what that means is we can draw something called a line of best fit through these data points that can kind of accurately classify them, if that makes any sense. So I'm going to scroll down here and look at what our line of best fit for this data set actually is. You can see this blue line. It pretty much, it is the perfect line of best fit for this data set. And using this line, we can actually predict future values in our data set. So essentially, linear regression is used when you have data points that correlate in kind of a linear fashion. Now this is a very basic example because we're doing this in 2 dimensions with x and y, but oftentimes what you'll have is you'll have data points that have 8 or 9 kind of input values, so that gives us a 9-dimensional kind of data set. And what we'll do is predict one of the different values. So in the instance where we were talking about students before, maybe we have a student's midterm grade and their second midterm grade, and then we want to predict their final grade. What we can do is use linear regression to do that, where our kind of input values are going to be the 2 midterm grades, and the output value is going to be that final grade that we're looking to predict. So if we were to plot that, we would plot that on a 3-dimensional graph, and we would draw a 3-dimensional line that would represent the line of best fit for that data set. Now, for any of you that don't know what line of best fit stands for, it says line. Oh, this is just the definition I got from this website here. Line of best fit refers to a line through a scatterplot of data points that best expresses the relationship between those points. So exactly what I've kind of been trying to explain. When we have data that correlates linearly, and I always butcher that word, what we can do is draw a line through it, and we can use that line to predict new data points. Because if that line is good, it's a good line of best fit for the data set, then hopefully we would assume that we can just pick some point, find where it would be on that line, and that'll be kind of our predicted value. So I'm going to go into an example now where I start drawing and going into a little bit of math so we understand how this works on a deeper level, but that should give you a surface level understanding. So actually I'll leave this up because I was messing with this beforehand. This is kind of a data set that I've drawn on here. So we have our x, and we have our y, and we have our line of best fit. Now, what I want to do is I want to use this line of best fit to predict a new data point. So all these red data points are ones that we've trained our model with. They're information that we gave to the model so that it could create this line of best fit. Because essentially all linear regression really does is look at all these data points and create a line of best fit for them. That's all it does. It's pretty, I don't know the word for it. It's pretty easy to actually do this. This algorithm is not that complicated, it's not that advanced, and that's why we start with it here because it just makes sense to explain. So I hope that a lot of you would know in 2 dimensions, a line can be defined as follows. So with the equation y equals mx plus b. Now b stands for the y-intercept, which means somewhere on this line. So essentially where the line starts. So in this instance, our b value is going to be right here. So this is going to
Just going to skip because I know
in this case we might call it. This means how much we went up versus these data points, and x plus, well, I can use this line to values at like 2.
More interested in the coding, not the math, because
for dimensions. So let's say we
I
have
already know all of
they're
this.
kind of like this. And I'm trying my best to kind of draw them in some. Now notice that this line is in 3 dimensions, right? This is going to cross our, I guess this is our x, y, and z axes. So we have a 3-dimensional line. Now the equation for this line is a little bit more complicated. I'm not going to talk about exactly what it is, but essentially what we do is we make this line and we say, okay, what value do I want to predict? Do I want to predict y, x, or z? Now, so long as I have 2 values, so 2 values, I can always predict the other one. So if I have, the x, y of a data point, that will give me the z. And if I have the z, y, that will give me the x. So long as you have, all of the data points except one, you can always find what that point is based on the fact that, we have this line and we're using that to predict. So I think I'm going to leave it at that for the explanation. I hope that makes sense. Again, just understand that we use linear regression when our data points are correlated. Older, things are going to be correlated in that sense. Install sklearn. Now, even if you're in a notebook, you actually need to do this because for some reason it doesn't come by default with a notebook. So to do this, we just did an exclamation point, pip install -q sklearn. Now, if you're going to be working on your own machine, again, you can use pip to install this, and I'm assuming that you know to use pip if you're going to be going along in that direction. Now, as before, since we're in the notebook, we need to define we're going to use Tensorflow version 2.x. So to do that, we're going to just do that up here with the % sign, and then we have all these imports which we're going to be using throughout here. So from future import, absolute import, division, print function, Unicode literals, and then obviously the big ones, so Numpy, Pandas, Matplotlib. We're going to be using IPython, we're going to be using Tensorflow, and yeah. So I'm actually just going to explain what some of these modules are because I feel like some of you may actually not know. Numpy is essentially a very optimized version of arrays in Python. So what this allows us to do is lots of kind of multi-dimensional calculations. So essentially, if you have a multi-dimensional array, which we talked about before, right, when we had those crazy shapes like 5555, Numpy allows us to represent data in that form and then very quickly manipulate and perform operations on it. So we can do things like cross product, dot product, matrix addition, matrix subtraction, element-wise addition, subtraction, vector operations. That's what this does for us. It's pretty complex, but we're going to be using it a fair amount. Pandas. Now, what Pandas does is it's kind of a data analytics tool. I almost want to say. I don't know the formal definition of what Pandas is, but it allows us to very easily manipulate data. So load in data sets, view data sets, cut off specific columns or cut out rows from our data sets, visualize the data sets. That's what Pandas does for us. Now, Matplotlib is actually a visualization of kind of graphs and charts. So we use that a little bit lower when I actually graph some different aspects of our data set. The IPython display, this is just specific for this notebook. It's just to clear the output. There's nothing crazy with that. And then obviously we know what Tensorflow is. This crazy import for Tensorflow here. So compat v2 feature column is FC. We'll talk about later. But we need something called a feature column when we create a linear regression algorithm or model in Tensorflow. So we're going to use that.
And so far, nothing really crazy. Just simple stuff.
Okay. So now that we've gone through all that, we need to start talking about the data set that we're going to use for linear regression and for this example. Because what we're going to do is actually create this model and start using it to predict values.
Wow.
So the data set that we're going to use, actually I need to read this because I forget exactly what the name of it is the Titanic data set. That's what it is. So essentially what this does is aim to predict who's going to survive or the likelihood that someone will survive being on the Titanic, given a bunch of information. So what we need to do is load in this data set. Now I know this seems like a bunch of gibberish, but this is how we need to load it. So we're going to use pandas, so pd.read_csv from this URL. So what this is going to do is take this CSV file, which stands for comma separated values, and we can actually look at this if we want, I think. So I said it's a control click. Let's see if this pops up. So let's actually download this, and let's open this up ourselves and have a look at what it is in Excel. So I'm going to bring this up here. You can see that link, and this is what our data set is. So we have our columns, which just stand for, what is it, the different attributes in our data set, the different features and labels of our data set. We have survive. So this is what we're actually going to be aiming to predict. So we're going to call this our label, right, or our output information. So here, a 0 stands for the fact that someone did not survive, and 1 stands for the fact that someone did survive. Now, just thinking about it on your own for a second, and looking at some of the categories we have up here, can you think about why linear regression would be a good algorithm for something like this? Well, for example, if someone is a female, we can kind of assume that they're going to have a higher chance of surviving on the Titanic just because of, kind of the way that our culture works, saving women and children first, right? And if we look through this data set, we'll see that when we see females, it's pretty rare that they don't survive. Although, as I go through, there's quite a few that didn't survive. But if we look at it compared to males, there's definitely a strong correlation that being a female results in a stronger survival rate. Now, if we look at age, right, can we think of how age might affect this? Well, I would assume if someone's way younger, they probably have a higher chance of surviving because they would be, prioritized in terms of lifeboats or whatever it was. I don't know much about the Titanic, so I can't talk about that specifically, but I'm just trying to go through the categories and explain to you why we picked this algorithm. Now, number of siblings, that one might not be as, influential in my opinion. Parch, I don't actually remember what Parch stands for. I think it is like what Parch. I don't know exactly what this column stands for, so unfortunately I can't tell you guys that one. But we'll talk about some more in a second. Fair, again, not exactly sure what fair stands for. I'm going to look on the Tensorflow website after this and get back to you guys. And we have class. So class is what class they were on the boat, right? So first class, second class, third class. So you might think someone that's in a higher class might have a higher chance of surviving. We have deck. So this is what deck they were on when it crashed. So unknown is pretty common. And then we have all these other decks. If someone got hit, if someone was standing on the deck that had the initial impact, we might assume that they would have a lower chance of survival. Bark 2 is where they were going, and then are they alone? Yes or no? And this one, this is interesting. We're going to see, does this make an effect? If someone is alone, is that a higher chance of survival? Is that a lower chance of survival? So this is kind of interesting. And this is what I want you guys to think about, is that when we have information and data like this, we don't necessarily know what correlations there might be, but we can kind of assume there's some linear thing that we're looking for, some kind of pattern, right? Whereas if something is true, then maybe it's more likely someone will survive. Whereas like if they're not alone, maybe it's less likely. And maybe there's no correlation whatsoever, but that's what we're gonna find out as we do this model. So let me look actually on the Tensorflow website and see if I can remember what Parch and I guess what fair was. So let's go up to the top here. Again, a lot of this stuff is just straight up copied from the Tensorflow website. I just added my own stuff to it. You can see like I just copied all of this. We're just bringing it in there. Let's see what it says about the different columns, if it gives us any exact explanations. Okay, so I couldn't find what Parch or fair stands for. For some reason, it's on the Tensorflow website either. I couldn't really find any information about it. If you guys know, leave a comment down below. It's not that important. We just want to use this data to do a test. So what I've done here is I've loaded in my data set, and notice that I've loaded a training data set and a testing data set. Now we'll talk about this more later. This is important. I have 2 different data sets, one to train the model with and one to test the model with. Now, kind of the basic reason we would do this is because when we test our model for accuracy to see how well it's doing, it doesn't make sense to test it on data it's already seen. It needs to see fresh data so we can make sure there's no bias and that it hasn't simply just memorized the data that we had. Now, what I'm doing here at the bottom with this y train and this y eval is I'm essentially popping a column off of this data set. So if I print out the data set here, and actually I'm going to show you a cool trick with pandas that we can use to look at this. So I can say df train dot head. So if I look at this by just looking at the head, and we'll print this out. I might need to import some stuff above. We'll see if this works or not. Yeah, so I need to just do these imports. Let's install and let's do these imports. I'll wait for this to run. Okay, so I've just selected Tensorflow 2.0. We're just importing this now. Should be done in 1 second. And now what we'll do is we'll print out the data frame here. So essentially what this does is load this into a Pandas data frame. Now, this is a specific type of object. Now, we're not going to go into this specifically, but a data frame allows us to view a lot of different aspects about the data and kind of store it in a nice form, as opposed to just loading it in and storing it in like a list or a Numpy array, which we might do if we didn't know how to use Pandas. This is a really nice way to do it. Read CSV, it'll load it into a data frame object, which actually means we can reference specific columns and specific rows in the data frame. So let's run this and just have a look at it. I need to print dftrain.head. So let's do that. And there we go. So this is what our data frame head looks like. Now, head, what that does is show us the first 5 entries in our data set, as well as show us a lot of the different columns that are in it. Now, since we have more than, we have a few different columns, it's not showing us all of them, it's just giving us the ... But we can see this is what the data frame looks like, and this is kind of the representation internally. So we have entry 0, survived 1, we have male, female, all of that. Now, notice that this has the survived column, okay? Because what I'm going to do is I'm going to print the data frame head again, so dftrain.head, after we run these 2 lines. Now, what this line does is takes this entire survived column, so all these 0s and 1s, and removes it from this data frame, so the head data frame, and stores it in the variable ytrain. The reason we need to do that is because we need to separate the data we're going to be classifying from the data that is kind of our input information or our initial data set, right? So since we're looking for the survived information, we're going to put that in its own, kind of variable stored here. Now, we'll do the same thing for the evaluation data set, which is df evaluation or testing data. And notice that here this was train.csv and this one was eval.csv. Now, these have the exact same form. They look like completely identical. It's just that, some entries we just kind of arbitrarily split them. So we're going to have a lot of entries in this training set, and we'll have a few in the testing set that we'll just use to do an evaluation on the model later on. So we pop them off by doing this. Pop removes and returns this column. So if I print out ytrain, actually let's look at this one first just to show you how it's been removed. We can see that we have the survived column here. We popped, and now the survived column is removed from that data set. So that's just important to understand. Now we can print out some other stuff too. So we can look at the ytrain and see what that is, just to make sure we really understand the status. So let's look at ytrain, and you can see that we have 627 entries, and just 0s or 1s representing whether someone survived or whether they did not. Now the corresponding indexes in this kind of list or data frame correspond to the indexes in the testing and training data frame. What I mean by that is entry 0 in this specific data frame corresponds to entry 0 in our ytrain variable. So if someone survived at entry 0, it would say 1 here, right? Or in this case, entry 0 did not survive. Now I hope that's clear. I hope I'm not confusing you with that, but I just want to show one more example to make sure. So we'll say dftrain 0. I'm going to print that, and I'm going to print ytrain at index 0. Oops, if I didn't mess up my brackets, and we'll have a look at it. Okay, so I just looked up the documentation because I totally forgot that I can do that. If I want to find one specific row in my data frame, what I can do is print .loc. So I do my data frame and then .loc and then whatever index I want. So in this case, I'm locating row 0, which is this, and then on the ytrain, I'm doing the same thing. I'm locating row 0. And what I had before, right? If I did dftrain and I put square brackets inside here, what I can actually do is reference a specific column. So if I wanted to look at, say the column for age, right? So we have a column for age. What I can do is do dftrain age, and then I can print this out like this, and it gives me all of the different age values. So that's kind of how we use a data frame. We'll see that as we go further on. Now let's go back to the other example I had because I just erased it, where I want to show you the row 0 in the data frame that's training, and then in the ytrain, output, whatever that is, so the survival. So you can see here that this is what we get from printing dftrain.loc0, so row 0. This is all the information, and then here this corresponds to the fact that they did not survive at row 0 because it's simply just the output is value 0. Now I know this is weird. It's saying like name 0, dtype object 0. Don't worry about that. It's just because it's trying to print it with some information, but essentially this just means this person who was male, 22, and had 1 sibling did not survive. Okay, so let's get out of this now. We can close this and let's go to we pretty much already done what I just have down here. But we can look at the data frame head. This is a little bit of a nicer output when we just have dftrain.head. We can see that we get kind of a nice outputted little graph. We've already looked at this information, so we know kind of some of the attributes of the data set. Now we want to describe the data set sometimes. What describe is just give us some overall information. So let's have a look at it here. We can see that we have 627 entries. The mean of age is 29. The standard deviation is 12 point whatever, and then we get the same information about all of these other different attributes. So for example, it gives us the mean fair, the minimum fair, and just some statistics. If you guys understand this, great. If you don't, it doesn't really matter. The important thing to look at typically is just how many entries we have. Sometimes we need that information, and sometimes the mean can be helpful as well because you can kind of get an average of like what the average value is in the data set. So if there's any bias later on, you can figure that out, but it's not crazy important. Okay, so let's have a look at the shape. So just like Numpy arrays and tensors have a shape attribute, so do data frames. So we want to look at the shape. We can just print out dftrain.shape. We get 627 by 9, which essentially means we have 627 rows and 9 columns or 9 attributes. So so that's what it says here. 627 entries, 9 features. We can interchange attributes and features. Then we can look at the head information for y, so we can see that here, which we've already looked at before, and that gives us the name, which was survived. Okay, so now what we can actually do is make some kind of graphs about this data. Now I've just stolen this code, straight up from the Tensorflow website. I wouldn't expect you guys to do any of this, like output any of these values. But what we're gonna do is create a few histograms and some plots just to look at kind of some correlations in the data, so that when we start creating this model, we have some intuition on what we might expect. So let's look at age. So this gives us a histogram of the age. So we can see that there's about 25 people that are kind of between 0 and 5. There is maybe like 5 people that are in between 5 and 10, and then the most amount of people are kind of in between their 20s and 30s, so in the midpoints. This is good information to know because that's going to introduce a little bit of bias into kind of our linear correlation graph, right? So just understanding, that we have like a large subset. There's some outliers here, like there's one person that's 80, right? Over here, a few people that are 70. Some important things to kind of understand before we move on to the algorithm. So let's look at the sex values now. So this is how many female and how many male. We can see that there's many more males than there's females. We can have a look at the class. So we can see if they're in first, second, or third class. Most people are in third, then followed by first, and then second. And then lastly, we can look at, what is this that we're doing? Oh, the percentage survival by sex. So we can see how likely a specific person or a specific sex is to survive just by plotting this. So we can see that males have about a 20% survival rate, whereas females are all the way up to about 78%. So that's important to understand. That kind of confirms that what we were looking at before in the data set when we were exploring it. And you don't need to do this every time that you're looking at a data set, but it is good to kind of get some intuition about it. So this is what we've learned so far. Majority of passengers are in their 20s or 30s. The majority of passengers are male, they're in third class, and females have a much higher chance of survival. Kind of already knew that.
It's pretty much a review of the Pandas stuff.
All right, so training and testing data sets. Now we already kind of went through this, so I'll skim through it quickly. Essentially, what we did above is loading 2 different data sets. The first data set was that training data set, which had the shape of 627 by 9. And what I'm actually going to do is create a code block here and just have a look at what was this df eval.shape to show you how many entries we have in here. So here in our testing data set, you can see we have significantly less at 264 entries, or rows, whatever you want to call them. So that's how many things we have to actually test our model. So what we do is we use that training data to create the model, and then the testing data to evaluate it and make sure that it's working properly. So these things are important. Whenever we're doing machine learning models, we typically have testing and training data. And yeah, that is pretty much it. Now I'm just going to take 1 second to copy over a lot of this code into the kind of other notebook I have, just so we can see all of it at once, and then I'll be back and we'll get into actually making the model. Okay, so I've copied in some code here. I know this seems like a lot of kind of gibberish right now, but I'm going to break down line by line what all this is doing and why we have this here. But we first need to discuss something called feature columns and the difference between categorical and numeric data. So categorical data is actually fairly common. Now when we're looking at our data set, actually I can open, I don't have it open in Excel anymore, but let's open this from my downloads. So let's go downloads. Where is this? Train. Okay, awesome. So we have this Excel data sheet here, and we can see what a categorical data or categorical data is something that's not numeric. So for example, unknown, C, first, third, city, N, Y, right? So anything that has different categories, there's going to be like a specific set of different categories there could be. So for example, for age, kind of the set of values we can have for age was numeric, so that's different. But for categorical, we can have male, or we can have female, and I suppose we could have other, but in this data set we just have male, and we just have female. For class, we can have first, second, third. For deck, we can have unknown, C, A, I'm sure through all the letters of the alphabet, but that is still considered categorical. Now, what do we do with categorical data? Well, we always need to transform this data into numbers somehow. So what we actually end up doing is we encode this data using an integer value. So for the example of male and female, what we might say, and this is what we're going to do in a second, is that female is represented by 0 and male is represented by 1. We do this because although it's interesting to know what the actual class is, the model doesn't care, right? Female and male doesn't make a difference to it. It just needs to know that those values are different or those values are the same. So rather than using strings and trying to find some way to pass that in and do math with that, we need to turn those into integers, so we turn those into zeros and ones, right? Now for class, right? So first, second, third. You guys can probably assume what we're going to encode this with. We're going to encode it with 0, 1, 2. Now again, this doesn't necessarily need to be in order. So third could be represented by 1 and first could be represented by 2, right? It doesn't need to be in order, it doesn't matter, so long as every third has the same number, every first has the same number, every second has the same number, and then same thing with deck, same thing with embark, and same thing with alone. Now we could have an instance where we've encoded every single one of these values with a different value. So in the rare occasion where there's one category that's categorical and every single value in that category is different, then we will have 627 in this instance different encoding labels that are going to be numbers. That's fine, we can do that, and actually we don't really need to do that because you're going to see how Tensorflow can handle that for us. So that's categorical data. Numeric columns are pretty straightforward. They're anything that just have integer or float values already. So in this case, age and fair. And yeah, so that's what we've done. We've just defined our categorical columns here and our numeric columns here. This is important because we're going to loop through them, which we're doing here to create something called feature columns. Feature columns are nothing special. They're just what we need to feed to our linear estimator, our linear model to actually make predictions. So kind of our steps here that we've gone through so far is import, load the dataset, explore the dataset, make sure we understand it, create our categorical columns and our numeric columns. So I've just hard coded these in, right? Like sex, parch, class, deck, alone, all these ones. And then same thing with the numeric columns. And then for linear estimator, we need to create these as feature columns using some kind of advanced syntax, which we're going to look at here. So we create a blank list, which is our feature columns, which will just store our different feature columns. We loop through each feature name in the categorical columns. And what we do is we define a vocabulary, which is equal to the data frame at that feature name. So first we would start with sex, then we go n siblings, then we go parch, then we go class, and we get all of the different unique values. So that's actually what this does. .unique gets a list of all unique values from the feature column. And I can print this out. I'll print this in a different line. We'll just take this value and have a look at actually what this is, right? So if I run, I just want to run all of these in order, and then we'll create a new code block while we wait for that to happen. Let's see if we can get this installing fast enough. Run. Okay, now we go to df train, and we can see this is what this looks like. So these are all the different unique values that we had in that specific feature name. Now that feature name was what? Categorical columns. Oh, what I do? Feature name. Oh, sorry, that's gonna be the unique one. Let's just put, rather than feature name, let's put sex, right? And let's have a look at what this is. So we can see that the two unique values are male and female. Now I actually want to do, what is it, Embark Town, and I want to see what this one is, so how many different values we have, so we'll copy that in. And we can see we have Southampton, cannot pronounce that, and then the other city is an unknown. And that is kind of how we get the unique value. So that's what that method is doing there. Let's actually delete this code block because we don't need it anymore. All right, so that's what we do. And then what we do down here is we say feature columns.append, so just add to this list the Tensorflow feature column.categorical column with vocabulary list. Now I know this is a mouthful, but this is kind of something again you're just gonna look up when you need to use it, right? So understand you need to make feature columns for linear regression. You don't really need to completely understand how, but you just need to know that that's what you need to do, and then you can look up the syntax and understand. So this is what this does. This is actually going to create for us a column. It's going to be in the form of a like Numpy array kind of that has the feature name, so whatever one we've looped through, and then all the different vocabulary associated with it. Now we need this because we just need to create this column so that we can create our model using those different columns, if that makes any sense. So our linear model needs to have all the different columns we're going to use. It needs to know all the different entries that could be in that column, and it needs to know whether this is a categorical column or a numeric column. In previous examples, what we might have done is actually change the dataset manually, so encoded it manually. Tensorflow just can do this for us now in Tensorflow 2.0, so we'll just use that tool. Okay, so that's what we did with these feature columns. Now for the numeric columns, it's a little bit different. It's actually easier. All we need to do is give the feature name and whatever the data type is and create a column with that. So notice we can omit this unique value because we know when it's numeric, but there could be an infinite amount of values. And then I just printed out the feature columns so you can see what this looks like. So vocabulary list, categorical column gives us the number of siblings, and the vocabulary list is these are all the different encoding values that it's created. And then same thing, we go down here, parch, these are different codings, so they're not necessarily in order, like what I was talking about before. Let's go to a numeric one. What do we have here? Yeah, so for a numeric column, just as is the key, that's the shape we're expecting, and this is the data type. So that's pretty much it. We're actually loading these in, so now it's almost time to create the model.
I think I kind of understand that, but probably don't know how to code it on my own if I had to. So if I understood, you have to assign a number to each one to do linear regression later, because it's faster probably.
Categorical, we can have male, or we can have female, and I suppose we could have other, but in this data set we just have male, and we just have female. For class, we can have first, second, third. For deck, we can have unknown, C, A, I'm sure through all the letters of the alphabet, but that is still considered categorical. Now, what do we do with categorical data? Well, we always need to transform this data into numbers somehow. So what we actually end up doing is we encode this data using an integer value. So for the example of male and female, what we might say, and this is what we're going to do in a second, is that female is represented by 0 and male is represented by 1. We do this because although it's interesting to know what the actual class is, the model doesn't care, right? Female and male doesn't make a difference to it. It just needs to know that those values are different or those values are the same. So rather than using strings and trying to find some way to pass that in and do math with that, we need to turn those into integers, so we turn those into zeros and ones, right? Now for class, right? So first, second, third. You guys can probably assume what we're going to encode this with. We're going to encode it with 0, 1, 2. Now again, this doesn't necessarily need to be in order. So third could be represented by 1 and first could be represented by 2, right? It doesn't need to be in order, it doesn't matter, so long as every
Yeah, so it translates everything into a number, so it's easier to calculate. Because the algorithm
So what we're
doesn't
going to
care.
do to create the model now is talk about first the training process and training some kind of,
We'll be right back. Right, I'm back.
machine learning model. Okay, so the training process. Now, the training process of our model is actually fairly simple, at least for a linear model. Now, the way that we train the model is we feed it information, right? So we feed it those data points from our data set. But how do we do that, right? Like, how do we feed that to the model? Do we just give it all at once? Well, in our case, we only have 627 rows, which isn't really that much data. Like, we can fit that in RAM in our computer, right? But what if we're training a crazy machine learning model and we have, 25 terabytes of data that we need to pass it? We can't load that into RAM. At least I don't know any RAM that's that large. So we need to find a way that we can kind of load it in what's called batches. So the way that we actually load this model is we load it in batches. Now, we don't need to understand really kind of how this process works and how batching kind of occurs. What we do is give 32 entries at once to the model. Now, the reason we don't just feed one at a time is because that's a lot slower. We can load, a small batch size of 32. That can increase our speed dramatically, and that's kind of a lower level understanding, so I'm not going to go too far into that. Now that we understand, we kind of load it in batches, right? So we don't load it entirely all at once. We just load a specific set of kind of elements as we go. What we have is called epochs. Now, what are epochs? Well, epochs are essentially how many times the model is going to see the same data. So it might be the case, right? When we pass the data to our model the first time, it's pretty bad. Like, it looks at the model, creates a line of best fit, but it's not great. It's not working perfectly. So we need to use something called an epoch, which means we're just going to feed the model, feed the data again, but in a different order. So we do this multiple times, so that the model will look at the data in a different way, in a kind of a different form, and see the same data a few different times and pick up on patterns. Because the first time it sees a new data point, it's probably not going to have a good idea how to make a prediction for that. So if we can feed it more and more and more, then we can get a better prediction. Now, this is where we talk about something called overfitting, though. Sometimes we can see the data too much. We can pass too much data to our model to the point where it just straight up memorizes those data points, and it's really good at classifying for those data points. But when we pass it some new data points, like our testing data, for example, it's horrible at kind of classifying those. So what we do to kind of prevent this from happening is we just make sure we start with like a lower amount of epochs, and then we can work our way up and kind of incrementally change that if we need to go higher, right? We need more epochs. So that's kind of it for epochs. Now I will say that this training process kind of applies to all the different machine learning models that we're going to look at. We have epochs, we have batches, we have a batch size, and now we have something called an input function. Now, this is pretty complicated. This is the code for the input function. I don't like that we need to do this, but it's necessary. So essentially what an input function is the way that we define how our data is going to be broke into epochs and into batches to feed to our model. Now, these you probably aren't ever going to really need to code like from scratch by yourself, but this is one I've just stolen from the Tensorflow website, pretty much like everything else that's in the series. And what this does is it takes our data and encodes it in a tf.data.dataset object. Now, this is because our model needs this specific object to be able to work. It needs to see a dataset object to be able to use that data to create the model. So what we need to do is take this pandas data frame, we need to turn it into that object. And the way we do that is with the input function. So we can see that what this is doing here, so this is make input function. We actually have a function defined inside of another function. I know this is kind of complicated for some of you guys, and what I'm actually going to do, sorry, I'm going to just copy this into the other page because I think it's easier to explain without all the text around. So let's create a new code block. Let's paste this in, and let's have a look at what this does. So actually, let me just tab down. Okay, so make input function. We have our parameters data frame, which is our pandas data frame, our label data frame, which stands for those labels, so that y train or that eval, y eval, right? We have a number of epochs, which is how many epochs we're going to do. We set that at default 10. Shuffle, which means are we going to shuffle our data and mix it up before we pass it to the model? And batch size, which is how many elements are we going to give to the model while it's training at once. Now what this does is we have an input function defined inside of this function, and we say dataset equals tensorframe.data.dataset from tensor slices dict data frame label data frame. Now what this does, and we can read the comment, create a tuf.data.dataset object with the data and its label. Now I can't explain to you like how this works on a lower level, but essentially we pass a dictionary representation of our data frame, which is whatever we passed in here, and then we pass the label data frame, which is going to be all those y values, and we create this object. And that's what this line of code does. So tf.data.dataset from tensor slices, which is just what you're going to use. We can read this documentation, create a dataset whose elements are slices of the given tensors. The given tensors are sliced along their first dimension. This operation preserves the structure of the input tensors, removing the first dimension of each tensor and using it as the dataset dimension. So you guys can look at that, like read through the documentation if you want, but essentially what it does is create the dataset object for us. Now, if shuffle ds equals ds.shuffle 1000, what this does is just shuffle the dataset. You don't really need to understand more than that. And then what we do is we say dataset equals dataset.batch, the batch size, which is going to be 32, and then repeat for the number of epochs. So what this is going to do is essentially take our dataset and split it into the number of, what do I want to call it? Like blocks that are going to be passed to our model. So it can do this by knowing the batch size. It obviously knows how many elements because that's the dataset object itself, and then repeat the number of epochs. So this can figure out, how many blocks do I need to split it into to feed it to my model. Now return dataset, simply from this function here, we'll return that dataset object, and then on the outside return, we actually return this function. So what this exterior function does, and I'm really just trying to break this down so you guys understand, is make an input function. It literally makes a function and returns the function object to wherever we call it from. So that's how that works. Now we have a train input function and an eval input function, and what we need to do to create these is just use this function that we've defined above. So we say make input function df train y train, so our data frame for training and our data frame for the labels of that. So we can see the comment, here we'll call the input function, right? And then eval train, so it's going to be the same thing except for the evaluation. We don't need to shuffle the data because we're not training it. We only need one epoch because again we're just training it, and we'll pass the evaluation dataset and the evaluation value from y. Okay, so that's it for making the input function. Now I know this is complicated, but that's the way we have to do it, and unfortunately if you don't understand after that, there's not much more I can do. You might just have to read through some of the documentation. All right, creating the model. We are finally here. I know this has been a while, but I need to get through everything. So linear estimator. So we're going to copy this, and I'm just going to put it in here, and we'll talk about what this does. So linear_est equals tf.estimator.linear classifier, and we're giving it the feature columns that we created up here. So this work was not for nothing. We have this feature column, which defines, what is in every single, like what should we expect for our input data. We pass that to a linear classifier object from the estimator module from Tensorflow, and then that creates the model for us. Now, this again is syntax that you don't need to memorize. You just need to understand how it works. What we're doing is creating an estimator. All of these kind of core learning algorithms use what's called estimators, which are just basic implementations of algorithms in TensorFlow. And again, pass the feature columns. That's how that works. All right, so now let's go to training the model. Okay, so I'm just going to copy this again. I know you guys think I'm just copying the code back and forth, but I'm not going to memorize the syntax. I just want to explain to you how all this works. And again, you guys will have all this code. You can mess with it, play with it, and learn on your own that way. So to train is really easy. All we need to do I say linear est.train and then just give that input function. So that input function that we created up here, right, which was returned from make input function, like this train input function here is actually equal to a function. It's equal to a function object itself. If I were to call train underscore input function like this would actually call this function. That's how this works in Python. It's a little bit of a complicated syntax, but that's how it works. We pass that function here, and then this will use the function to grab all of the input that we need and train the model. Now, the result is going to be, rather than train, we're going to evaluate, right? And notice that we didn't store this one in a variable, but we're storing the result in a variable so that we can look at it. Now, clear output is just from what we imported above. Just going to clear the console output because there will be some output while we're training. And we can print the accuracy of this model. So let's actually run this and see how this works. This will take a second, so I'll be back once this is done. Okay, so we're back, and we've got a 73.8% accuracy. So essentially what we've done, right, is we've trained the model. You might have seen a bunch of output while you were doing this on your screen, and then we printed out the accuracy after evaluating the model. And this accuracy isn't very good, but for our first shot, this is okay, and we're going to talk about how to improve this in a second. Okay, so we've evaluated the dataset, we stored that in result. I want to actually look at what result is, because obviously you can see we've referenced the accuracy part, as if this was a Python dictionary. So let's run this one more time. This is going to take a second again. So, okay, so we printed out results here, and we can see that we have actually a bunch of different values. So we have accuracy baseline, AUC, and all these different kind of statistical values. Now, these aren't really going to mean much to you guys, but I just want to show you that we do have those statistics, and to access any specific one, this is really just a dictionary object, so we can just reference the key that we want, which is what we did with accuracy. Now, notice our accuracy actually changed here. We went to 76. Now, the reason for this is, like I said, our data is getting shuffled, it's getting put in a different order, and based on the order in which we see data, our model will, make different predictions and be trained differently. So if we had, another epoch, right, if I change epochs to say 11 or 15, our accuracy will change. Now, it might go up, it might go down. That's something we have to play with as, a machine learning developer, right? That's what your goal is to get the most accurate model. Okay, so now it's time to actually use the model to make predictions. So up until this point, we've just been doing a lot of work to understand how to create the model, what the model is, how we make an input function, training, testing data. I know a lot of stuff. Now, to actually use this model and make accurate predictions with it is somewhat difficult, but I'm going to show you how. So essentially, TensorFlow models are built to make predictions on a lot of things at once. They're not great at making predictions on like one piece of data. You just want like one passenger to make a prediction for. They're much better at working in like large batches of data. Now you can definitely do it with one, but I'm just going to show you how we can make a prediction for every single point that's in that evaluation data set. So right now we looked at the accuracy, and the way we determined the accuracy was by essentially comparing the results that the predictions gave from our model versus what the actual results were for every single one of those passengers. And that's how we came up with an accuracy of 76%. Now, if we want to actually check and get predictions from the model and see what those actual predictions are, what we can do is use a method called .predict. So what I'm going to do is I'm going to say, I guess, result like this equals, and in this case, we're going to do the model name, which is linear est.predict. And then inside here, what we're going to pass is that input function we use for the evaluation. So just like, we need to pass an input function to actually train the model, we also need to pass an input function to make a prediction. Now, this input function could be a little bit different. We can modify this a bit if we wanted to, but to keep things simple, we use the same one for now. So what I'm going to do is just use this eval input function. So the one we've already created where we did, one epoch. We don't need to shuffle because it's just the evaluation set. So inside here, we're going to do eval input function. Now, what we need to do, though, is convert this to a list just because we're going to loop through it. And I'm actually going to print out this value so we can see what it is before we go to the next step. So let's run this and have a look at what we get. Okay, so we get logistics array. We can see all these different values. So we have, this array with this value. We have probabilities, this value, and this is kind of what we're getting. So we're getting logistic, all classes, like there's all this random stuff. But what you hopefully should notice, and I know I'm just like whizzing through, is that we have a dictionary that represents the predictions. And I'll see if I can find the end of the dictionary here for every single, prediction. So since we passed, 267 input data from this, eval input function, what was returned to us is a list of all of these different dictionaries that represent each prediction. So what we need to do is look at each dictionary so that we can determine what the actual prediction was. So what I'm going to do is actually just do result. I'm going to do result 0 because this is a list, so that should mean we can index it so we can actually look at one prediction. Okay, so this is the dictionary of one prediction. So I know this seems like a lot, but this is what we have. This is our prediction. So logistics, we get some array, we have logistic in here in this dictionary, and then we have probabilities. So what I actually want is probability. Now, since what we ended up having was a prediction of two classes, right? Either 0 or 1. We're predicting either someone survived or they didn't survive, or what their percentage should be. We can see that the percentage of survival here is actually 96%, and the percentage that it thinks that it won't survive is, 3.3%. So if we want to access this, what we need to do is click do result at some index, so whatever one we want. So we're gonna say result, and then here we're gonna put probabilities. So I'm just gonna print that like that, and then we can see the probabilities. So let's run this, and now we see our probabilities are 96 and 33. Now, if we want the probability of survival, so I think I actually might have messed this up. I'm pretty sure the survival probability is actually the last one, whereas like the non-survival is the first one because 0 means you didn't survive and 1 means you did survive. So that's my bad. I messed that up. So if I actually want their chance of survival, I'll index 1. So if I index 1, you see we get 3.3%. But if I wanted their chance of not surviving, I would index 0. And that makes sense because 0 is, what we're looking like. 0 represents they didn't survive, whereas 1 represents they did survive. So that's kind of how we do that. So that's how we get them. Now, if we wanted to loop through all of these, we could loop through every dictionary. We could print every single probability of each person. And we could also look at that person's stats and then look at their probability. So let's see, the probability of surviving is, in this case, 3% or whatever it was, 3.3%. But let's look at the person that we were actually predicting on and see if that makes sense. So if I go eval, df eval.loc 0, we print that, and then we print the result. What we can see is that for the person who was male and 35, that had no siblings, their fare was this, they're in 3rd class, we don't know what deck they were on, and they were alone, they have a 3.3% chance of surviving. Now, if we change this, we could go like 2. Let's have a look at this second person and see what their chance of survival is. Okay, so they have a higher percent chance. So 38% chance, they're female, they're a little bit older, so that might be a reason why their survival rate's a bit lower. And I mean, we can keep doing this and look through and see what it is, right? And if we want to get the actual value, like if this person survived or if they didn't survive, then what I can do is I can print df eval. Actually, it's not going to be eval. It's going to be y_eval. Yeah. And that's going to be .loc 3. Now, this will give us if they survived or not. So actually, in this case, that person did survive, but we're only predicting a 32%. So you can see that that's represented in the fact that we only have about a 76% accuracy because this model is not perfect. And in this instance, it was pretty bad. It's saying they have a 32% chance of surviving, but they actually did survive. So maybe that should be high, right? So we could change this number and go 4. I'm just messing around and showing you guys, how we use this. So in this one, same thing. This person survived, although what is it? They only were given a 14% chance of survival. So anyways, that is how that works. This is how we actually make predictions and look at the predictions. You understand that now what's happening is I've converted this to a list just because this is actually a generator object, which means it's meant to just be looped through rather than just look at it with a list, but that's fine. We'll use a list. And then we can just print out, result at whatever index, probabilities, and then 1 to represent their chance of survival. Okay, so that has been it for linear regression. Now let's get into classification.
Oh, definitely need to look this up a bunch of times. Probably read documentation to get it.
And now we We're on to classification. So essentially, classification is differentiating between data points and separating them into classes. So rather than predicting a numeric value, which we did with regression earlier, so linear regression and the percentage survival chance, which is a numeric value, we actually want to predict classes. So what we're going to end up doing is predicting the probability that a specific data point or a specific entry or whatever we're going to call it is within all of the different classes it could be. So for the example here, we're going to use flowers. So it's called the iris, I think it's the iris flower dataset or something like that. And we're going to use some different properties of flowers to predict what species of flower it is. So that's the difference between classification and regression. Now I'm not going to talk about the specific algorithm we're going to use here for classification because there's just so many different ones you can use. But yeah, I mean, if you really care about how they work on a lower mathematical level, I'm not going to be explaining that because it doesn't make sense to explain it for one algorithm when there's like hundreds and they all work a little bit differently. So you guys can kind of look that up and I'll tell you some resources and where you can find that. I'm also going to go faster through this example just because I've already covered kind of a lot of the fundamental stuff in linear regression. So hopefully we should get this one done a little bit quicker and move on to the next kind of aspects in this series. All right, so first steps, load TensorFlow, import TensorFlow. We've done that already. Dataset, we need to talk about this. So the dataset we're using is that iris flowers dataset like I talked about. And this specific dataset separates flowers into 3 different species. So we have these different species. This is the information we have. So septal length, width, petal width. We're going to use that information obviously to make the predictions. So given this information, in our final model, can it tell us which one of these flowers it's most likely to be? Okay, so what we're going to do now is define the CSV column names and the species. So the column names are just going to define what we're going to have in our data set as like the headers for the columns. Species obviously is just the species and we'll throw them there. All right, so now we're going to load in our data sets. So this is going to be different every time you're kind of working with models depending on where you're getting your data from. In our example, we're going to get it from Keras, which is kind of a sub-module of TensorFlow that has a lot of useful data sets and tools that we'll be using throughout the series. But keras.utils.getFile, again, don't really focus on this. Just understand what this is going to do is save this file onto our computer as iristraining.csv, grab it from this link, and then what we're going to do down here is load the train and test. And again, notice this is training and this is testing into 2 separate data frames. So here we're going to use the names of the columns as the CSV column names. We're going to use the path as whatever we loaded here. Header equals 0, which just means row 0 is the header. All right, so now we will move down and we'll have a look at our data set. So like we've done before. Oh, I've got to run this code first. CSV column names. Okay, so we're just running things in the wrong order here apparently. Okay, so let's look at the head. So we can see this is kind of what our data frame looks like. And notice that our species here are actually defined numerically. So rather than before when we had to do that thing where we made those feature columns and we converted the categorical data into numeric data with those kind of weird TensorFlow tools, this is actually already encoded for us. Now 0 stands for Setosa, and then 1 and 2 obviously stand for these ones respectively. And that's how that works. Now these I believe are in centimeters, the septal length, petal width. That's not super important, but sometimes you do want to know that information. Okay, so now we're going to pop off those columns for the species like we did before and separate that into train Y, test Y, and then have a look at the head again. So let's do that and run this. Notice that is gone. Again, we've talked about how that works. And then these, if we want to have a look at them, and actually let's do this by just having a new block. Let's say train underscore.
The biggest problem I'm having so far with this is that I still don't understand what's the process, and I don't think he's going to explain probably. So this course might not be sufficient because I want to understand what's the process behind the AI, like what's the logic and how is actually learning how to predict things instead of just calling the methods.
Y dot, what is it, dot head. If I could spell head correctly. Okay, so we run head, and we can see this is what it looks like, nothing special. That's what we're getting. All right, so let's delete that. Let's look at the shape of our training data. I mean, we can probably guess what it is already, but we're going to have shape 4 because we have 4 features. And then how many entries do we have? Well, I'm sure this will tell us. So 120 entries in shape 4. Awesome, that's our shape. Okay, input function. So we're moving fast here already. We're getting into a lot of the coding. So what I'm actually going to do is, again, copy this over into a separate document, and I'll be back in a second with all that. Okay, so input function time. We already know what the input function does because we used it previously. Now, this input function is a little bit different than before just because we're kind of changing things slightly. So here, we don't actually have any, what do you call it? We don't have any epochs, and our batch size is different. So what we've done here is rather than actually, defining like make input function, we just have input function like this. And what we're going to do is a little bit different when we pass this input function. I'll kind of show you. It's a little bit more complicated, but you can see that we've cleaned this up a little bit. So exactly we're doing what we did before. We're converting this data, which is our features, which we're passing in here, into a data set, and then we're passing those labels as well. And then if we're training, so if training is true, what we're going to do is say dataset is equal to the dataset.shuffle. So we're going to shuffle that information and then repeat that. And that is all we really need to do. We can do dataset.batch at the batch size, 256, return that, and we're good to go. So this is our input function. Again, these are kind of complicated. You kind of have to just get experience seeing a bunch of different ones to understand how to actually make one on your own. For now on, don't worry about it too much. You can pretty much just copy the input functions you've created before and modify them very slightly if you're going to be doing your own models. But by the end of this, you should have a good idea of how these input functions work. We will have seen like 4 or 5 different ones, and then, we can kind of mess with them and tweak them as we go on, but don't focus on it too much. Okay, so input function. This is our input function. I'm not really going to go into too much more detail with that. And now our feature columns. So this is, again, pretty straightforward for the feature columns. All we need to do for this is, since they're all numeric feature columns, is rather than having 2 for loops where we were separating the numeric and categorical feature columns before, we could just loop through all of the keys in our training data set, and then we can append to my feature columns blank list, the feature column.numeric column, and the key is equal to whatever key we've looped through here. And I'm going to show you what this means in case anyone's confused. Again, you can see when I print my feature columns, we get key equals septal length, we get our shape, and we get all of that other nice information. So let's copy this into the other one and have a look at our output after this. Okay, so my feature columns for key and train.keys. So notice train is here. Train.keys, what that does is actually give us all of the columns. So this was a really quick and easy way to kind of loop through all the different columns, although I could have looped through CSV column names and just removed the species column to do that, but again, we don't really need to. So for key in train.keys, my feature columns, .append, tf feature column, numeric column, key equals key. This was just going to create those feature columns. We don't need to do that vocabulary thing and that .unique because again, these are all already encoded for us. Okay, awesome. So that was the next step. So let's go back here. Building the model. Okay, so this is where we need to talk a bit more in depth of what we're actually going to build. So the model for this is a classification model. Now there is like hundreds of different classification models we can use that are pre-made in Tensorflow. And so far what we've done with that linear classifier is that's a pre-made model that we kind of just feed a little bit of information to and it just works for us. Now here we have two kind of main choices that we can use for this kind of classification task that are pre-built in TensorFlow. We have a DNN classifier, which stands for a deep neural network, which we've talked about very vaguely, very briefly, and we have a linear classifier. Now a linear classifier works very similarly to linear regression, except it does classification rather than regression, so we get actually numeric value, or we get, the labels, like the probability of being a specific label rather than a numeric value. But in this instance, we're actually going to go with deep neural network. Now that's simply because TensorFlow on their website, like all of this is kind of building off of the TensorFlow website, just all of the code is very similar, and I've just added my own spin and explained things very in depth. They recommend using that. Deep neural network for this is a better kind of choice, but typically when you're creating machine learning apps, you'll mess around with different models and kind of tweak them, and you'll notice that it's not that difficult to change models because most of the work comes from loading and kind of pre-processing our data. Okay, so what we need to do is build a deep neural network with two hidden layers with 30 nodes and 10 hidden nodes each. Now, I'm going to draw out the architecture of this neural network in just 1 second, but I want to show you what we've done here. So we said classifier equals tf.estimator. So this estimator module just stores a bunch of pre-made models from TensorFlow. So in this case, DNN classifier is one of those. What we need to do is pass our feature columns just like we did to our linear classifier, and now we need to define the hidden units. Now, hidden units is essentially us building the architecture of the neural network. So like you saw before, we had an input layer, we had some like middle layers called our hidden layers in a neural network, and then we had our output layer. I'm going to explain neural networks in the next module, so this will all kind of click and make sense. For now, we've arbitrarily decided 30 nodes in the first hidden layer, 10 in the second, and the number of classes is going to be 3. Now, that's something that we need to decide. We know there's 3 classes for the flowers, so that's what we've defined. Okay, so let's copy this in, go back to the other page here, and that is now our model. And now it is time to talk about how we can actually train the model, which is coming down here. Okay, so I'm going to copy this, I'm going to paste it over here, and let's just dig through this because this is a bit more of a complicated piece of code than we usually used to work with. I'm also going to remove these comments just to clean things up in here. So we've defined the classifier, which is a deep neural network classifier. We have our feature columns, hidden units, classes. Now to train the classifier. So we have this input function here. This input function is different than the one we created previously. Remember when we had previously was like make input, whatever function I will continue typing, and inside it defined another function, and it actually returned that function from this function. I know, complicated. If you're not a Python kind of pro, I don't expect that to make perfect sense. But here we just have a function, right? We're not returning a function from another function, it's just one function. So when we want to use this to train our model, what we do is create something called a lambda. Now a lambda is an anonymous function that can be defined in one line. When you write lambda, what that means is essentially this is a function. So this is a function, and whatever's after the colon is what this function does. Now this is a one-line function. So like if I create a lambda here, right, and I say lambda print hi, and I said x equals lambda, and I called x like that, this works. This is a valid line of syntax. And actually, I want to make sure that I'm not just like messing with you when I say that, and that this is actually correct. Okay, so sorry, I just accidentally trained the model, so I just commented that out. You can see we're printing hi, right? At the bottom of the screen, I know it's kind of small, but it does say hi. That's how this works, okay? So this is a cool thing. If you haven't seen this in Python before, that's what a lambda does. Allows you to define a function in one line. Now, the thing that's great about this is that we can say, like, x equals lambda, and here put another function, which is exactly what we've done with this print function. And that means when we call x, it will, execute this function, which will just execute the other function. So it's kind of like a chain, right? You call x is a function, and inside that function, it does another function, right? It's just like calling a function from inside a function. So what is lambda doing here? Well, since we need the actual function object, what we do is we define a function that returns to us a function. So this actually just like it calls this function when you put this here. Now there's no, it's very difficult to explain this if you don't really understand the concept of lambdas and you don't understand the input functions, but just know we're doing this because of the fact that we didn't embed another function and return the function object. If we had done that, input function that we had created before where we had the interior function, then we wouldn't need to do this because what would happen is we would return the input function, right, like that, which means when we passed it into here, it could just call that directly. It didn't need to have a lambda. Whereas here though, since we need to just put a lambda, we need to define what this is, and then this works. That's just, there's no other way to really explain this. So yeah, what we do is we create this input function. So we have train y, and we have training equals true. And then we do steps equals 5,000. So this is similar to an epoch.
It's pretty simple with calling recursively.
Except this is just defining a set amount of steps we're going to go through. So rather than saying like we'll go through the dataset 10 times, we're just going to say we'll go through the dataset until we've hit 5,000 numbers, like 5,000 things that have been looked at. So that's what this does with that train. And let's run this and just look at the training output from our model. It gives us some like things here. We can kind of see how this is working. Notice that if I can stop here for a second, it tells us the current step. It tells us the loss. The lower this number, the better. And then it tells us global steps per second. So how many steps we're completing per second. Now at the end here, we get final step loss of 39, which is pretty high, which means this is pretty bad. But That's fine. This is kind of just our first test at training a neural network. So this is just giving us output while it's training to kind of say what's happening. Now, in our case, we don't really care because this is a very small model. When you're training models that are massive and take terabytes of data, you kind of care about the progress of them. So that's when you would use kind of that output, right? And you would actually look at that. Okay, so now that we've trained the model, let's actually do an evaluation on the model. So we're just going to say classifier.evaluate. And what we're going to do is a very similar thing to what we've done here, is just pass this input function, right? Like here with a lambda, once again. And reason we add the lambda when we don't have this like double function going on, like a nested function, we need the lambda. And then in here, what we do is rather than passing train and train y, we're going to pass test, I believe, and I think I just called it test y. Okay, and then for training, obviously this is false, so we can just set that false like that. I'm just going to look at the other screen to make sure I didn't mess this up because, again, I don't remember the syntax. Yeah, so classifier.evaluate test y looks good to me. We'll take this print statement just so we get a nice output for our accuracy. Okay, so let's look at this. Again, we're going to have to wait for this to train, but I will show you a way that we don't need to wait for this to train every time in 1 second, and I'll be right back. Okay, so what I'm actually going to do, and I'm just going to pause like the execution of this code, is throw this in the next block under, because the nice thing about Google Collaboratory is that I can run this block of code, right? I can train all this stuff, which is what I'll run now while we're talking, just so it happens. And then I can have another code block kind of below it, which I have here. And it doesn't matter, I don't need to rerun that block every time I change something here. So if I change something on any lower blocks, I don't need to change the upper block, which means I don't need to wait for this to train every time I want to do an evaluation on it. Anyways, so we've done this, we've done test, we got test y. I just need to change this instead of eval result. Actually, I need to say eval underscore result equals classifier.evaluate so that we can actually store this somewhere and get the answer. And now we'll print this, and notice this happens much, much faster. We get a test accuracy of 80%. So if I were to retrain the model, chances are this accuracy would change, again, because of the order in which we're seeing different flowers. But this is pretty decent considering we don't have that much test data, and we don't really know what we're doing, right? We're kind of just messing around and experimenting for right now. So to get 80% is pretty good. Okay, so actually what am I doing? We need to go back now and do predictions. So how am I going to predict this for specific flowers? So let's go back to our core learning algorithms, and let's go to predictions. Now, I've written a script already, just to save a bit of time, that allows us to do a prediction on any given flower. So what I'm going to do is create a new block down here, code block, and copy this function in. Now, we're going to digest this and kind of go through this on our own to make sure this makes sense. But what this little script does is allow the user to type in some numbers, so the septal length, width, and I guess petal length and width, and then it will spit out to you what the predicted class of that flower is. So we could do a prediction on every single one of our data points like we did previously. Now, we already know how to do that. I showed you that with linear regression. But here, I just wanted to do it on one entry. So what do? So I start by creating an input function. It's very basic. We have batch size 256. All we do is we give some features, and we create a data set from those features that's a dict, and then .batch and the batch size. So what this is doing is, notice we don't give any y value, right? We don't give any labels. The reason we don't do that is because when we're making a prediction, we don't know the label, right? Like we actually want the model to give us the answer. So here, I wrote down the features. I create a predict dictionary just because I'm going to add things to it. And then I just prompted here with a print statement, please type numeric values as prompted. So for feature and feature, val equals true, while valid, val equals input feature colon. So this just means what we're going to do is for each feature, we're going to wait to get some valid response. Once we get some valid response, what we're going to do is add that to our dictionary. So we're going to say predict feature. So whatever that feature was, so septal length, septal width, petal length, or petal width is equal to a list that has, in this instance, whatever that value was. Now, the reason we need to do this is because, again, the predict method from Tensorflow works on predicting for multiple things, not just one value. So even if we only have one value we want to predict for, we need to put it inside of a list because it's expecting the fact that we will probably have more than one value in which we would have multiple values in the list, right? Each representing a different row or a new flower to make a prediction for. Okay. Now we say predictions equals classifier.predict, and then in this case we have input function lambda input function predict, which is this input function up here. And then we say for prediction dictionaries, because remember every prediction comes back as a dictionary. In predictions, we'll say the class ID is equal to whatever the class IDs of the prediction dictionary at 0, and these are simply I don't know exactly how to explain this. We'll look at it in a second, and I'll go through that. And then we have the probability is equal to the prediction dictionary probabilities of class ID. Okay. Then we're going to say print prediction is. We're going to do this weird format thing. I just stole this from TensorFlow. And it's going to be the species at the class ID and then 100 times probability, which will give us actual integer value. We're going to digest this, but let's run this right now and have a look. So please type numeric values as prompted. Septal length, let's type like 2.4. Septal width, 2.6. Petal width, let's just say that's like 6.5. And yeah, petal width like 6.3. Okay, so then it calls this and it says prediction is Virginica. I guess that's the class we're going with. And it says that's an 86.3% chance that that is the prediction. So yeah, that is how that works. So that's what this does. I wanted to give a little script. I wrote most of this. I mean, I stole some of this from TensorFlow, but just to show you how we can actually predict on one value. So let's look at these prediction dictionary because I just want to show you what one of them actually is. So I'm going to say print pred underscore dict, and then this will allow me to actually walk through what class IDs are, probabilities are, and how I've kind of done this. So let's run this septal length. Okay, let's just go with 1.4, 2.3. I don't know what these values are going to end up being, and we get prediction is the same one with 77.1%, which makes sense because these values are similar kind of in difference to what I did before. Okay, so this is the dictionary. So let's look for what we were looking for. So probabilities, notice we get 3 probabilities, one for each of the different classes. So we can actually say what, the percentages for every single one of the predictions. Then what we have is class IDs. Now class IDs, what this does is tell us what class ID it predicts is actually the flower, right? So here it says 2, which means that this probability at 77%, that's at index 2 in this array, right? So that's why this value is 2. So it's saying that that class is 2. It thinks it's class 2. Like that's whatever was encoded in our system is 2. And that's how that works. So that's how I know which one to print out, is because this tells me it's class 2. And I know from making this list all the way back up here, if I can get rid of this output, where is it? When I say species, that number 2 is Virginica, or I guess that's how you say it. So that is what the classification is, or that's what the prediction is. So that's how I do that, and that's how that works. Okay, so I think that is pretty much it for actually classification. So that was pretty basic. I'm going to go and see if there's anything else that I did for classification in here. Okay, so here I just put some examples. So here's some example input expected classes. So you guys could try to do these if you want. So for example, this one, septal length, septal width. So for 5.1, 3.3, 1.7, and 0.5, the output should be Setosa. For 5.9, 3.0, 4.2, 1.5, it should be this one. And then obviously this for this, just so you guys can mess with them if you want. But that's pretty much it for classification. And now on to clustering.
It's getting really confusing, and I'm not gonna lie, I got distracted a little bit in the middle there.
Okay, so now we're moving on to clustering. Now,
I think I'm gonna learn more when I actually do the projects. And those are ones I'm actually gonna do them. Or try to do them on my own. And just read the documentation. Which of the following steps is not part of the k-means algorithm?
clustering is the first unsupervised learning algorithm that we're going to see in this series, and it's very powerful. Now, clustering only works for a very specific set of problems, and you use clustering when you have a bunch of input information or features, but you don't have any labels or output information. Essentially, what clustering does is finds clusters of like data points and tells you the location of those clusters. So you give a bunch of training data, you can pick how many clusters you want to find. So maybe we're going to be classifying digits, right? Handwritten digits using k-means clustering. In that instance, we would have 10 different clusters for the digits 0 through 9, and you pass all this information, and the algorithm actually finds those clusters in the dataset for you. We're going to walk through an example that'll make sense, but I just want to quickly explain the basic algorithm behind k-means. Essentially the set of steps, because I'm going to walk you through them and with a visual example. So we're going to start by randomly picking k points to place k centroids. Now, a centroid stands for where our current cluster is kind of defined, and we'll see it in a second. The next step is we're going to assign all of the data points to the centroids by distance. So actually, now that I'm talking about this, I think it just makes more sense to get right into the example, because if I keep talking about this, you guys are probably just going to be confused, although I might come back to this just to reference those points. Okay, so let's create a little graph like this in 2 dimensions for our basic example, and let's make some data points here. So I'm just going to make them all red, and you're going to notice that I'm going to make this kind of easier for ourselves by putting them in like their own unique little groups, right? So actually, we'll add one up here, then we can add some.
I think it's pretty intuitive to understand.
Now, the algorithm starts for k-means clustering, and you guys will understand how this works as we continue, by randomly picking k centroids. Now, I'm going to denote a centroid by a little filled in triangle like this. And essentially what these are is where these different clusters currently exist. So we start by randomly picking k, which is what we've defined. So like me in this instance, we're going to say k equals 3, k centroids wherever. So maybe we put one, somewhere like here. You know what, I might not bother filling these in because they're going to take a while. Maybe we put one here, and maybe we end up putting one over here. Now, I've kind of put them close to where the clusters are, but these are going to be completely random. Now, what happens next is each group, or each data point, is assigned to a cluster by distance. So essentially what we do is for every single data point that we have, we find what's known as the Euclidean distance, or it actually could be a different distance. You could use like Manhattan distance, if you guys know what that is, to all of the centroids. So let's say we're looking at this data point here. What we do is find the distance to all of these different centroids. And we assign this data point to the closest centroid. So the closest one by distance. Now in this instance, it's looking like it's going to be a bit of a tie between this centroid and this centroid, but I'm going to give it to the one on the left. So what
we're going to find the center of mass, kind of something like that, between these 3 points.
We do is we're going to say this is now a part of this centroid. So if I'm calling this, like, let's just say this is centroid 1, this is centroid 2, and this is centroid 3, then this now is going to be a part of centroid 1 because it's closest to centroid 1. And we can go through and we do this for every single data point. So obviously we know all of these are going to be our 1s, right? And we know these are going to be our 2, so 2, 2, 2, and then these are obviously going to be our 3. Now I'm actually just going to add a few other data points because I want to make this a little bit more sophisticated almost, if that makes any sense. So I'll add those data points here. We'll even add one here, and now we'll give these labels. So these ones are close. So I'm going to say this one's 1. I'm going to say this one's 2. I know it's not closest to it, but just because I want to do that for now, we'll say 2 for that, and we'll say 3 here. Okay, so now that we've done that, we've labeled all these points. What we do is we now move these centroids that we've defined into the middle of all of their data points. So what I do is I essentially find, it's called center of mass, the center of mass between all of the data points that are labeled the same. So in this case, these will be all the ones that are labeled the same. And I take this centroid, which I'm going to have to erase, get rid of it here, and I put it right in the middle. So let's go back to blue, and let's say the middle of these data points ends up being somewhere around here. So we put it in here, and this is what we call center of mass, and this again would be centroid 2. So let's just erase this, and there we go. Now we do the same thing with the other centroids. So let's remove these ones, let's remove these ones. So for 3, I'm saying it's probably going to be somewhere in here, and then for 1, our center of mass is probably going to be located somewhere about here. Now what I do is I repeat the process that I just did, and I reassign all the points now to the closest centroid. So all these points are labeled 1, 2, all that. We can kind of remove their labels, and this is just going to be great. Me trying to erase the labels, I shouldn't have wrote them on top. But essentially what we do is we're just going to be like reassigning them. So I'm going to say, okay, so this is 2, and we just do the same thing as before, find the closest distance. So we'll say, these can stay in the same cluster. Maybe this one actually here gets changed to 1 now because it's closest to centroid 1, and we just reassign all these points. And maybe this one now, if it was 2 before, let's say like this one's 1, and we just reassign them. Now we repeat this process of finding the closest, or assigning all the points to their closest centroid, moving the centroid into the center of mass, and we keep doing this until eventually we reach a point where none of these points are changing which centroid they're part of. So eventually we reach a point where I'm just going to erase this and draw like a new graph because it'll be a little bit cleaner. But what we have is like a bunch of data points. So we have some over here, some over here. Maybe we'll just put some here, and maybe we'll do like a k equals 4 example for this one. And we have all these centroids, and I'll just draw these centroids with blue again, that are directly in the middle of all of their data points. They're like as in the middle as they can get, assigned to that one. And we can do this for any data point, right? So even if I put a data point all the way over here, well, its closest cluster is this, so it gets assigned to this cluster, and my output will be whatever this label of this cluster is. And that's essentially how this works. So you're just clustering data points, figuring out which ones are similar, and it's a pretty basic algorithm. I mean, you draw your little triangle, you find the distance from every point of the triangle, or to all the triangles actually, and then what you do is just simply assign those values to that centroid, you move that centroid to the center of mass, and you repeat this process constantly until eventually you get to a point where none of your data points are moving. That means you've found the best clusters that you can, essentially. Now, the only thing with this is you do need to know how many clusters you want for k means clustering, because k is a variable that you need to define, although there is some algorithms that can actually determine the best amount of clusters for a specific data set, but that's a little bit beyond what we're going to be focusing on right now. So that is pretty much clustering. There's not really much more to talk about it, especially because we can't really code anything for it now. So we're going to move on to hidden Markov models.
I think it's either this option or this one. Or maybe this one. God damn. Maybe I need to watch the video again. Yeah, this option doesn't make sense to me. Shuffle the k points so they are redistributed randomly. But isn't the point of the algorithm to find the center of mass of each one? So it's not random.
R3. Now I'm actually just going to add a few other data points because I want to make this a little bit more
Well, it's not
that makes
part
sense. So I'll
of
add those
it.
data points here. We'll even add one here, and I'll give these labels.
I
So these
didn't
ones are
read
close. So I'm going to say this
this.
one's 1. I'm going to say this one's 2.
Now makes more sense. Yeah, I was kind of confused there. A lot of options seem
Now
to
hidden
make
Markov
sense.
models are way
That makes a hidden Markov model different than linear regression or classification. I'm gonna watch the video first before I answer. I'll be right back, real quick. Right, I'm back.
Are way different than what we've seen so far. We've been using kind of algorithms that rely on data. So like k-means clustering, we gave a lot of data and we clustered all those data points, found those centroids, used those centroids to find where new data points should be. Same thing with linear regression and classification. Whereas hidden Markov models, we actually deal with probability distributions. Now, the example we're going to go into here, and it's kind of, I have to do a lot of examples for this because it's a very abstract concept, is a basic weather model. So what we actually want to do is predict the weather on any given day, given the probability of different events occurring. So let's say we know, maybe in like a simulated environment or something like that, this might be an application, that we have some specific things about our environment. Like we know if it's sunny, there's an 80% chance that the next day it's going to be sunny again, and a 20% chance that it's going to rain. Maybe we know some information about sunny days and about cold days, and we also know some information about the average temperature on those days. Using this information, we can create a hidden Markov model that will allow us to make a prediction for the weather in future days, given kind of that probability that we've discovered. Now you might be like, well, how do we know this? Like, how do I know this probability? A lot of the times you actually do know the probability of certain events occurring or certain things happening, which makes these models really good. But there's sometimes where what you actually do is you have a huge data set and you calculate the probability of things occurring based on that data set. So we're not going to do that part because that's just kind of going a little bit too far. And the whole point of this is just to introduce you to some different models. But in this example, what we will do is use some predefined probability distributions. So let me just read out the exact definition of a hidden Markov model and start going more in depth. So the hidden Markov model is a finite set of states, each of which is associated with a generally multidimensional probability distribution. Transitions among the states are governed by a set of probabilities called transition probabilities. So in a hidden Markov model, we have a bunch of states. Now, in the example I was just talking about with this weather model, the states we would have is hot day and cold day. Now, these are what we call hidden because never do we actually access or look at these states while we interact with the model. In fact, what we look at is something called observations. Now, at each state, we have an observation. I'll give you an example of an observation. If it is hot outside, Tim has an 80% chance of being happy. If it is cold outside, Tim has a 20% chance of being happy. That is an observation. So at that state, we can observe the probability of something happening during that state is X, right? Or is Y, or whatever it is. So we don't actually care about the states in particular, we care about the observations we get from that state. Now, in our example, what we're actually going to do is we're going to look at the weather as an observation for the state. So, for example, on a sunny day, the weather has, the probability of being between 5 and 15 degrees Celsius with an average temperature of 11 degrees. That's a probability we can use. Now, I know this is slightly abstract, but I just want to talk about the data we're going to work with here. I'm going to draw out a little example, go through it, and then we'll actually get into the code. So let's start by discussing the type of data we're going to use. So typically in previous ones, right, we use like hundreds, if not like thousands of entries or rows or data points for our models to train. For this, we don't need any of that. In fact, all we need is just constant values for probability and transition distributions and observation distributions. Now, what I'm going to do is go in here and talk about states, observations, and transitions. So we have a certain amount of states. Now, we will define how many states we have. But we don't really care what that state is. So we could have states, for example, like warm, cold, high, low, red, green, blue. We have as many states as we want. We could have one state, to be honest, although that would be kind of strange to have that. And these are called hidden because we don't directly observe them. Now, observations. So each state has a particular outcome or observation associated with it based on a probability distribution. So it could be the fact that during a hot day, it is 100% true that Tim is happy. Although, in a hot day, we could observe that 80% of the time Tim is happy and 20% of the time he is sad, right? Those are observations we make about each state. And each state will have their different observations and different probabilities of those observations occurring. So if we were just going to have like an outcome for the state, that means it's always the same. There's no probability that something happens. And in that case, that's just called an outcome because the probability of the event occurring will be 100%. Okay, then we have transitions. So each state will have a probability defining the likelihood of transitioning to a different state. So for example, if we have a hot day, there will be a percentage chance the next day will be a cold day. And if we have a cold day, there will be a percentage chance that the next day is either a hot day or a cold day. So we're going to go through like the exact what we have for our specific model below. But just understand there's a probability that we could transition into a different state. And from each state, we can transition into every other state or a defined set of states given a certain probability. So I know it's a mouthful, I know it's a lot, but let's go into a basic drawing example because I just want to illustrate like graphically a little bit kind of how this works in case these ideas are a little bit too abstract for any of you. Okay, so I'm just pulling out the drawing tablet just 1 second here, and let's do this basic weather model. So what I'm going to do is just simply draw two states. Actually, let's do it with some colors because why not? So we're going to use yellow, and this is going to be our hot day, okay? This is going to be our sun. And then I'm just going to make a cloud. We'll just do like a gray cloud. This will be my cloud, and we'll just say it's going to be raining over here. Okay, so these are my two states. Now, in each state, there's a probability of transitioning to the other state. So for example, in a hot day, we have a, let's say, 20% chance of transitioning to a cold day. And we have a 80% chance of transitioning to another hot day, like the next day, right? Now, in a cold day, we have, let's say, a 30% chance of transitioning to a hot day. And we have, in this case, what is that going to be? A 70% chance of transitioning to another cold day. Now, on each of these days, we have a list of observations. So these are what we call states, right? So this could be S1, and this could be S2. It doesn't really matter, like, if we name them or anything. We have two states. That's what we know. We know the transition probability. That's what we just defined. Now we want the observation probability or distribution for that. So essentially, on a hot day, our observation is going to be that the temperature could be between 15 and 25 degrees Celsius with an average temperature of, let's say, 20. So we could say observation, right? So say observation, and we'll say that the mean, so the average temperature is going to be 20, and then the distribution for that will be like the minimum value is going to be 15, and the max is going to be 25. So this is what we call actually like a standard deviation. I'm not really going to explain exactly what standard deviation is, although you can kind of think of it as something like this. So essentially there's a mean, which is the middle point, the most common event that could occur, and at different levels of standard deviation, which is going into statistics, which I don't really want to mention that much because I'm definitely not an expert, we have a probability of hitting different temperatures as we move to the left and right of this value. So on this curve somewhere, we have 15, and on this curve to the right somewhere, we have 25. Now we're just defining the fact that this is where we're going to kind of end our curve. So we're going to say that like the probability is in between these numbers. It's going to be in between 15 and 25 with an average of 20, and then our model will kind of figure out some things to do with that. That's as far as I really want to go in standard deviation. And I'm sure that's like a really horrible explanation, but that's kind of the best I'm going to give you guys for right now. Okay, so that's our observation here. Now our observation over here is going to be similar. So we're going to say mean on a cold day, temperature is going to be 5 degrees. We'll say the minimum temperature maybe is going to be something like -5, and the max could be something like 15, or like, yeah, I'm going to say 15. So we'll have some distribution. That's just what we want to understand, right? And this is kind of a strange distribution because we're dealing with, standard deviation, although we can just deal with like straight percentage observations. So for example, there's a 20% chance that Tim is happy, or there's an 80% chance that he is sad. Like those are probabilities that we can have as our observation probabilities in the model. Okay, so there's a lot of lingo. There's a lot going on. We're going to get into like a concrete example now, so hopefully this should make more sense. But again, just understand states, transitions, observations. We don't actually ever look at the states. We just have to know how many we have and the transition probability and observation probability in each of them. Okay, so what I want to say now, though, is what do we even do with this model? So once I make this, right, once I make this hidden Markov model, what's the point of it? Well, the point of it is to predict future events based on past events. So we know that probability distribution, and I want to predict the weather for the next week. Well, I can use that model to do that because I can say, well, if the current day today is warm, then what is the likelihood that the next day tomorrow is going to be cold, right? And that's what we're kind of doing with this model. We're making predictions for the future based on probability of past events occurring. Okay.
The issue is that you're assuming a bunch of things about the probabilities by doing things this way. I guess this is the issue of science, just part of the problem. From the way he explained at least. You're never gonna know for sure the state's probability of something. What TensorFlow module should you import to implement hidden Markov model?
So imports and setup. So let's just run this. Oh, we already loaded. Import TensorFlow. And notice that here I've imported TensorFlow probability is TFP. This is because this is a separate module from TensorFlow that deals with probability. Now we also need TensorFlow 2, but for this hidden Markov model, we're going to use the TensorFlow probability module. Not a huge deal. Okay, so weather model. So this is just going to define what our model actually is, so the different parts of it. So this is taken directly from the documentation of TensorFlow. You guys can see, where I have all this information from, like I've sourced all of it. But essentially, what the model we're going to try to create is that cold days are encoded by 0 and hot days are encoded by 1. The first day in our sequence has an 80% chance of being cold. So whatever day we're starting out at has an 80% chance of being cold, which would mean 20% chance of being warm. A cold day has a 30% chance of being followed by a hot day, and a hot day has a 20% chance of being followed by a cold day, which would mean 70% cold to cold and 80% hot to hot. On each day, the temperature is normally distributed with mean and standard deviation 0 and 5 on a cold day, and mean and standard deviation 15 and 10 on a hot day. Now, what that means, standard deviation, is essentially, we can read this thing here, is that on a hot day, the average temperature is 15, that's mean, and ranges from...
Like this, for example, I don't understand. The first day in our sequence has an 80% chance of being cold. Like, how is that known? Is that an assumption they make on the model? Is that a consequence of other training? I don't really understand this. Cold day has a 30% chance of being followed by a hot day. Like, how does this percentages come? Where do they come from?
From 5 to 25, because the standard deviation is 10 of that, which just means 10 on each side, kind of the min max value. Again, I'm not in statistics, so please don't quote me on any definitions of standard deviation. I'm just trying to explain it enough so that you guys can understand what we're doing here. Okay, so what we're going to do to model this, and I'm just kind of going through this fairly quickly because it's pretty easy to really do this, is I'm going to load the TensorFlow probability distributions kind of module and just save that as TFD. And I'm just going to do that so I don't need to write tfp.distributions. All of this. I can just kind of shortcut it. So you'll notice I'm referencing TFD here, which just stands for tfp.distributions, and TFP is TensorFlow probability. Okay, so my initial distribution is TensorFlow probability distributions.categorical. And this is probability of 80% and 20%. Now this refers to point 2. So let's look at point 2. The first day in our sequence has an 80% chance of being cold. So we're saying that that's essentially what this is. The initial distribution of being cold is 80%, and then 20% after. Categorical is just a way that we can do this distribution. Okay, so transition distribution. What was it? TensorFlow probability, categorical. The probability is 70% and 30%, and 20% and 80%. Now notice that since we have two states, we've defined two probabilities. Notice since we have two states, we have defined two probabilities, the probability of landing on each of these states at the very beginning of our sequence. This is the transition probability, referred to points 3 and 4 above. So this is what we have here. So cold day has 30% chance, 20% chance for a hot day, and that's what we've defined. So we say this is going to be cold day, state 1. We have 70% chance of being cold day again. We have 30% chance of going hot day, and then, reverse here. Okay, so observation distribution. Now, this one is a little bit different, but essentially we do tfd.normal. Now, I don't know, I'm not going to explain exactly what all this is, but when you're doing standard deviation, you're going to do it like this, where you're going to say loc, which stands for your average or your mean, right? So that was our average temperature, is going to be 0 on a hot day, 15 on a cold day. The standard deviation on the cold day is 5, which means we range from -5 to 5 degrees. And on a hot day, it's 10.
I guess I get it now. They just got a bunch of data and then make the distribution. And then they use these probabilities to do this calculus, but it's still an assumption, I think. Because you can always have deviations from the data. But I guess the bigger the data, the more likely that it's going to be correct. Or not correct, but a lesser chance. Less chance of future events deviating a lot from past events. But that's a much bigger issue, I think, with the way we think, which is an epistemological. Not sure if I'm saying this correctly, but yeah, it's the issue of the nature of knowledge. Then yeah.
So that is going to be, we range from 5 to 25 degrees, and our average temperature is 15. Now, the reason we've added dot here is because these just need to be float values. So rather than inserting integers here and having potentially type errors later on, we just have floats. Okay, so the loc argument represents the mean and the scale is the standard deviation. Yeah, exactly what we just defined there. All right, so let's run this. I think we actually already did. And now we can create our model. So to create the model is pretty easy. I mean, all we do is say model equals TensorFlow distribution dot hidden Markov model, give it the initial distribution, which is equal to initial distribution, transition distribution, observation distribution, and steps. Now, what is steps? Well, steps is how many days we want to predict for. So the number of steps is how many times we're going to step through this probability cycle and run the model, essentially. Now, remember, what we want to do is we want to predict the average temperature on each day, right? Like that's what the goal of our example is to predict the average temperature. So given this information, using these observations and using these transitions, what we'll do is predict that. So I'm going to run this model. What is the issue here? Tensor is unhashable. Tensor is... Okay, give me 1 sec. I'll have a look here, though I haven't had this issue before. Okay, so after a painful amount...
I guess my main source of... not confusion, but what I want to understand is if there's a way or if someone has already done something that... Like, how is the algorithm updating itself? Because if it's making predictions based on the past data, then the predictions are always going to be skewed. So I wonder if there's a way to... There's an algorithm or a set of algorithms that correct the predictions and update themselves based on new input.
Amount of searching on Stack Overflow and Google and actually just reading through more documentation on TensorFlow, I have determined the issue. So remember the error was we're getting on actually this line here. I think I can see what the output is. Okay, well, this is a different error. But anyways, there was an error at this line. Essentially, what was happening is we have a mismatch between the two versions here. So the most recent version of TensorFlow is...
The other thing that I'm wondering is what's the correlation, the physical correlation between the logic behind the sample size construction and the algorithm. If there's a way to connect the physics of an event with the probability distribution and use that to with the AI, with the machine learning to update and try to restructure the physics based on the data, if that makes sense.
Not compatible with the older version of TensorFlow probability, at least in the sense that the things that we're trying to do with it. So I just need to make sure that I install the most recent version of TensorFlow probability. So what you need to do, if this is in your notebook, and this should actually work fine for you guys because this will be updated by the time you get there, but in case you run into the issue, I'll deal with it. But essentially, we're going to do select version 2.x of TensorFlow. You're going to run this install command. So you're going to install TensorFlow probability.
I think that's the main issue actually with this thing, is that it's good that I'm learning a lot of stuff, but it's not really what I was looking for, because what I want to know more is the physics and the logic behind the construction of the machine learning, so I can understand why people came up, like what was the process of coming up with this technology. Because then it would allow me to understand better like the fundamental part and not just the libraries and how to use them. Because although it is hard to remember and to know exactly how to implement each thing, I don't think that's the biggest problem or challenge. I think it's a lot better to try to understand the fundamental part of the thing. And I think, for example, the concept of tensors, I think they come from the physics from the vector space. And there's probably correlations there, and that's how people decided to design this. So there are a bunch of... That's the issue, I think. There are a bunch of assumptions that are embedded into this already, and I want to understand what those assumptions are, so I can understand how to use this better, I guess, and not just learn the libraries and stuff. Because I think there are probably different ways to do it, and there's a bunch of things that I'm thinking about with the projects I'm gonna try to build in the future that are more related to physics, and I think understanding this on a deeper level is gonna be crucial to be able to do the things that I wanna do. and should test these different assumptions on physics and probability. So I guess I will need to probably look at some other way to learn this or read the libraries after I'm done with these sections and the challenges.
Just run this command. Then after you run this command, you're going to need to restart your runtime. So go to runtime and then restart runtime. And then you can just continue on with the script, select TensorFlow 2.x again, do your imports, and then, we'll test if this is actually going to work for us here. Run our distributions, create the model without any issues this time, notice no red text, and then run this final line, which will give you the output. Now, this is what I wanted to talk about here that we didn't quite get to because we were having some bugs. But this is how we can actually kind of run our model and see the output. So what you can do is do model.mean. So you say mean equals model.mean. And what this is going to do is essentially just calculate the probability. It's going to essentially take that from the model. Now, when we have model.mean, this is what we call, a partially defined tensor. So remember our tensors were like partially defined computations? Well, that's what model.mean actually is. That's what this method is. So if we want to get the value of that, what we actually need to do is create a new session in TensorFlow, run this part of the graph, which we're going to get by doing mean.numpy, and then we can print that out. So I know this might seem a little bit confusing, but essentially to run a session in the new version of TensorFlow, so 2.x or 2.1 or whatever it is, you're going to type with tf.compat.v1.session as sesh, and then, this doesn't really matter what you have here, but whatever you want. And then what I'm doing is just printing mean.numpy. So to actually get the value from this here, this variable, I call it .numpy, and then what it does is print out this array that gives me the expected temperatures on each day. So we have, 3, 6, essentially 7.5, 8.25, and you can see these are the temperatures based on the fact that we start with an initial probability of starting on a cold day. So we kind of get that here, right? We're starting at 3 degrees. That's what it's determined we're going to start at. And then we have all of these other temperatures that's predicting for the next days. Now notice if we recreate this model, so I'll just rerun the distributions, rerun them, and go model.mean again. This stays the same, right? Well, because our probabilities are the same, this model's going to do the calculation the exact same. There's not really any training that goes into this. So we get, very similar, if not the exact same values. I can't remember if these are identical, but that's what it looks like to me. We can run this again. See, we get the same one. And we'll create the model one more time. And let me just check these values here to make sure I'm not lying to you guys. Yes, they are the exact same. Okay, so let's start messing with a few probabilities and see what we can do to this temperature and see what changes we can cause. So if I do 0.5 here and I do 0.5 for the categorical probability, remember this refers to points 3 and 4 above. So that's a cold day has a 30% chance of being followed by hot day, and then hot day has a 20% chance of being followed by cold day. So what I've just done now is change the probability to be 50%, so that a cold day now has a 50% chance of being followed by hot day and a 50% chance of being followed by cold day. And let's recreate this model. Let's rerun this and let's see if we get a difference. Oh, we do. Notice this. The temperature now is going a little bit higher. Now notice that we get the same starting temperature because that's just the average based on this probability that we have here. But if we wanted to potentially start, hotter, we could reverse these numbers. We go 0.2, 0.8. Let's rerun all of this. And now look at this, what our temperatures are. We start at 12 and then we actually drop our temperature down to 10. So that's how this hidden Markov model works. Now this is nice because you can just tweak the probabilities. This happens pretty well instantly and we can have a look at our output very nicely. So obviously this is representing the temperature on our, the first day. This would be the second day, third day, fourth day, fifth, sixth, seventh. And obviously the more days you go on, the least accurate this is probably going to be because it just runs off probability. And if you're going to try to predict, a year in advance and you're using the weather that you have from, I guess, the previous year, you're probably not going to get a very accurate prediction. But anyways, these are hidden Markov models. They're not extremely useful. There's some situations where you might want to use something like this. So that's why we're implementing them in this course and showing you how they work. It's also another feature of TensorFlow that a lot of people don't talk about or see. And, personally, I hadn't really heard of hidden Markov models until I started developing this course. So anyways, that has been it for this module. Now, I hope that this kind of gave you guys a little bit of an idea of how we can actually implement some of these machine learning algorithms, a little bit of idea of how to work with data, how we can feed that to a model, the importance between testing and training data. And then obviously linear regression is one we focused a lot on. So I hope you guys are very comfortable with that algorithm. And then what was the second one we did? I gotta go up to remember exactly the sequence we had here. So classification, that one was important as well. So I hope you guys really understood that. Clustering, we didn't go too far into that, but again, this is an interesting algorithm. And if you need to do some kind of clustering, you now know of one algorithm to do that called k-means clustering, and you understand how that works. And now you know hidden Markov models. So in the next module, we're gonna start covering neural networks. We now have the knowledge we need to really dive in there and start doing some cool stuff. And then in the future modules, we're gonna do deep computer vision. I believe we're gonna do chatbots with recurrent neural networks, and then some form of reinforcement learning at the end. So with that being said, let's go to the next module.
Honestly, I don't know which one of this answer. Yeah, probability makes more sense, but don't remember hearing him talking about library or modules. Densely connected neural networks, one in which all the neurons in the current layer are connected to one neuron in the previous layer. All the neurons in each layer are connected randomly. All the neurons in the current layer are connected to every neuron in the previous layer.
Hello everybody and welcome to Module 4. Now in this module of this course, we're going to be talking about neural networks, discussing how neural networks work, a little bit of the math behind them, talking about gradient descent and backpropagation, and how information actually flows through the neural network, and then getting into an example where we use a neural network to classify articles of clothing. So I know that was a lot, but that's what we're going to be covering here. Now neural networks are complex. There's kind of a lot of components that go into them, and I'm going to apologize right now because it's very difficult to explain it all at once. What I'm going to be trying to do is kind of piece things together and explain them in blocks, and then at the end, kind of combine everything together. And I will say, in case any of you didn't watch the beginning of this course, I do have very horrible handwriting, but this is the easiest way to explain things to you guys. So bear with me. I'm sure you'll be able to understand what I'm saying, but it might just be painful to read some of it. All right, so let's get into it right away and start discussing what neural networks are and how they work. Well, the whole point of a neural network is to provide, classification or predictions for us. So we have some input information, we feed it to the neural network, and then we want it to give us some output. So if we think of the neural network as this black box, we have all this input, right? We give all this data to the neural network. Maybe we're talking about an image, maybe we're talking about just some random data points, maybe we're talking about a dataset, and then we get some meaningful output. This is what we're looking at. So if we're just looking at a neural network from kind of the outside, we think of it as this magical black box. We give some input, it gives us some output. I mean, we could call this black box just some function, right? Where it's a function of the input, maps it to some output. And that's exactly what a neural network does. It takes input and maps that input to some output, just like any other function, right? Just like if you had a straight line like this is a function. This is your line, whatever it is, you're gonna say y equals like 4x. Maybe that's your line. You give some input x and it gives you some value y. This is a mapping of your input to your output. All right, so now that we have that down, what is a neural network made up of? Well, a neural network is made up of layers. And remember we talked about the layered representation of data when we talked about neural networks. So I'm gonna draw a very basic neural network. We're gonna start with the input layer. Now the input layer is always the first layer in our neural network, and it is what is going to accept our raw data. Now what I mean by raw data is whatever data we want to give to the network, whatever we want to classify, whatever our input information is, that's what this layer is going to receive in the neural network. So we can say, these arrows represent our input, and they come to our first input layer. So this means, for example, if you had an image, and this image, and I'll just draw like one like this, let's say this is our image, and it has all these different pixels, right? All these different pixels in the image, and you want to make a classification on this image. Well, maybe it has a width and a height, and a classic width and height example is 28 by 28. If you had 28 by 28 pixels, and you want to make a classification on this image, how many input neurons do you think you would need in your neural network to do this? Well, this is kind of, a tough question if you don't know a lot about neural networks. If you're predicting for the image, if you're going to be looking at the entire image to make a prediction, you're going to need every single one of those pixels, which is 28 times 28 pixels, which I believe is something like 784. I could be wrong on that number, but I believe that's what it is. So you would need 784 input neurons. Now, that's totally fine. That might seem like a big number, but we deal with massive numbers when it comes to computers, so this really isn't that many. But that's an example of how you would use a neural network input layer to represent an image. You would have 784 input neurons, and you would pass one pixel to every single one of those neurons. Now, if we're doing an example where maybe we just have one piece of input information, maybe it's literally just one number, well then all we need is one input neuron. If we have an example where we have 4 pieces of information, we would need 4 input neurons, right? Now this can get a little bit more complicated, but that's the basis that I want you to understand is, the pieces of input you're going to have, regardless of what they are, you need one input neuron for each piece of that information, unless you're going to be reshaping or putting that information in a different form. Okay, so let's just actually skip ahead and go to now our output layer. So this is going to be our output. Now, what is our output layer? Well, our output layer is going to have as many neurons, and again, the neurons are just representing like a node in the layer, as output pieces that we want. Now, let's say we're doing a classification for images, right? And maybe there's 2 classes that we could represent. Well, there's a few different ways we could design our output layer. What we could do is say, okay, we're going to use one output neuron. This output neuron is going to give us some value. We want this value to be between 0 and 1, and we'll say that's inclusive. Now, what we can do now if we're predicting 2 classes, say, okay, so if my output neuron is going to give me some value, if that value is closer to 0, then that's going to be class 0. If this value is closer to 1, it's going to be class 1, right? And that would mean when we have our training data, right, when we talk about training and testing data, we give our input, and our output would need to be the value 0 or 1, because it's either the correct class, which is 0, right, or the correct class, which is 1. So like our labels for our training data set would be 0 and 1, and then this value on our output neuron would be guaranteed to be between 0 and 1, based on something that we're going to talk about a little bit later. That's one way to approach it, right? We have a single value, we look at that value, and based on what that value is, we can determine, what class we predicted. That works sometimes, but in other instances when we're doing classification, what makes more sense is to have as many output neurons as classes you're looking to predict for. So let's say we're going to have, like 5 classes that we're predicting for, maybe these 3 pieces of input information are enough to make that prediction. Well, we actually have 5 output neurons, and each of these neurons would have a value between 0 and 1, and the combination, so the sum of every single one of these values would be equal to 1. Now, can you think of what this means? If every single one of these neurons has a value between 0 and 1, and their sum is 1, what does this look like to you? Well, to me, this looks like a probability distribution. And essentially what's going to happen is we're going to make predictions for how strongly we think our input information is each class. So if we think that it's like class 1, maybe we'll just label these like this. Then what we would do is say, okay, this is going to be 0.9, representing 90%. Maybe this is like 0.001, maybe this is 0.05, 0.003, but you get the point. It's going to add up to 1, and this is the probability distribution for our output layer. So that's a way to do it as well. And then obviously if we're doing some kind of regression task, we can just have one neuron, and that will just predict some value, and we'll define, what we want that value to be. Okay, so that's my example for my output. Now let's erase this, and let's actually just go back to one output neuron, because that's what I want to use for this example. Now, we have something in between these layers, because obviously, we can't just go from input to output with nothing else. What we have here is called a hidden layer. Now, in neural networks, we can have many different hidden layers. We can have, hidden layers that are connecting to other hidden layers, and like we could have hundreds, thousands if we wanted to. For this basic example, we'll use one, and I'll write this as hidden. So now we have our 3 layers. Now, why is this called hidden? The reason this is called hidden is because we don't observe it when we're using the neural network. We pass information to the input layer, we get information from the output layer, we don't know what happens in this hidden layer or in these hidden layers. Now, how are these layers connected to each other? How do we get from this input layer to the hidden layer to the output layer and get some meaningful output? Well, every single layer is connected to another layer with something called weights. Now we can have different kind of architectures of connections, which means I could have something like this one connects to this, this connects to this, this connects to this, and that could be like my connection kind of architecture, right? We could have another one where this one goes here, and maybe this one goes here, and actually, after I've drawn this line, now we get what we're going to be talking about a lot, which is called a densely connected neural network. Now, a densely connected neural network or a densely connected layer essentially means that it's connected to every node from the previous layer. So in this case, you can see every single node in the input layer is connected to every single node in the output layer, or in the hidden layer, my bad. And these connections are what we call weights. Now, these weights are actually what the neural network is going to change and optimize to determine the mapping from our input to our output. Because again, remember, that's what we're trying to do. We have some kind of function, we give some input, it gives us some output. How do we get that input and output? Well, by modifying these weights. Now, it's a little bit more complex, but this is the start. So these lines that I've drawn are really just numbers, and every single one of these lines is some numeric value. Typically, these numeric values are between 0 and 1, but they can be large, they can be negative. It really depends on what kind of network you're doing and how you've designed it. Now, let's just write some random numbers. We have like 0.1, this could be like 0.7. You get the point, right? We just have numbers for every single one of these baselines, and these are what we call the trainable parameters that our neural network will actually tweak and change as we train to get the best possible result. So we have these connections. Now our hidden layer is connected to our output layer as well. This is again another densely connected layer because every layer or every neuron from the previous layer is connected to every neuron from the next layer. If you would like to determine how many connections you have, what you can do is say there's 3 neurons here, there's 2 neurons here, 3 times 2 equals 6 connections. That's how that works from layers, and then obviously you can just multiply all of the neurons together as you go through and determine what that's going to be. Okay, so that is how we connect these layers. We have these weights. So let's just write a W on here so we remember that those are weights. Now we also have something called biases. So let's add a bias here. I'm going to label this B. Now biases are a little bit different than these nodes we have regularly. There's only one bias, and a bias exists in the previous layer to the layer that it affects. So in this case, what we actually have is a bias that connects to each neuron in the next layer from this layer, right? So it's still densely connected, but it's just a little bit different. Now notice that this bias doesn't have an arrow beside it because this doesn't take any input information. This is another trainable parameter for the network. And this bias is just some constant numeric value that we're going to connect to the hidden layer so we can do a few things with it. Now these weights always have a value of 1. We're going to talk about why they have a value of 1 in a second, but just know that whenever a bias is connected to another layer or to another neuron, its weight is typically 1. Okay, so we have that connected, we have our bias, and that actually means we have a bias here as well, and this bias connects to this. Notice that our biases do...
The other thing I'm wondering is if it's possible to train a neural network on a specific data set for something and then apply it to another data set, to another thing. For example, train it with information about the weather, so you get the logic and the weights right, and then make it play chess or something like that. Learn to teach it how to play chess based on the weights and the biases. I think that's an interesting question, because if all it matters is the probability and the logic behind it, the connection of weights, if you have roughly same probability distributions over the logic of how the physics of a system works, it should be similar, the solutions to apply. But of course the rules are going to be different, but I wonder if it's possible, because all you really need is a logic and framework to relate the logic to different probability distributions and how they correlate across space-time.
do not connect with each other. The reason for this again is there's some constant value, and there's something we're kind of adding into the network as another trainable parameter that we can use. Now let's talk about how we actually pass information through the network and why we even use these weights and biases and what they do. So let's say we have, I can't really think of good examples, we're just gonna do some arbitrary stuff. Let's say we have like data points, right? X, Y, Z. And all of these data points have some mapped value, right? There's some value we're looking for them, or there's some class we're trying to put them in. Maybe we're clustering them between like red dots and blue dots. So let's do that. Let's say an XYZ is either part of the red class or the blue class. Let's just do that. So what we want this output neuron to give us is red or blue. So what I'm going to do is say, since it's just one class, we'll get this output neuron in between the range 0 and 1. We'll say, okay, if it's closer to 0, that's red. If it's closer to 1, that's blue. And that's what we'll do for this network and for this example. Now our input neurons are going to obviously be X, Y, and Z. So let's pick some data point, and let's say we have, the value 2, 2, 2. That's our data point, and we want to predict whether it's red or blue. How do we pass it through? Well, what we need to do is determine how we can, find the value of this hidden layer node. We already know the value of this input node, but now we need to go to the next layer using these connections and find what the value of these nodes are. Well, the way we determine these values is I'm going to say, and I've just said N1 just to represent like this is a node, like this is node 1, maybe this one should be node 2, is equal to what we call the weighted sum of all of the previous nodes that are connected to it, if that makes any sense to you guys. So a weighted sum is something like this. So I'm just going to write the equation, I'll explain it. I'm going to say N1 is equal to the sum of, let's not say N equals 0, let's say I equals 0 to N of, in this case, we're going to say Wi times Xi plus B. Now, I know this equation looks really mathy and complicated. It's really not. What this symbol and this equation here means is take the weighted sum of all the neurons that are connected to this neuron. So in this case, we have neuron X, neuron Y, and neuron Z connected to N1. So when we take the weighted sum, or we calculate this, what this is really equal to is the weight at neuron X. So we say Wx times the value at neuron X, which in this case is just equal to 2, right? Plus whatever the weight is at neuron Y. So in this case, this is Wy, and then times 2, and then you get the point where we have Wz, and I'm trying on the edge of my drawing tablet to write this, times 2. Now obviously these weights have some numeric value. Now when we start our neural network, these weights are just completely random. They don't make any sense, they're just some random values that we can use. As the neural network gets better, these weights are updated and changed to make more sense in our network. So right now we'll just leave them as Wx, Wy, Wz, but no, these are some numeric values. So this returns to us some value, right? Some value, let's just call this value V, and that's what this is equal to, so V. Then what we do is we add the bias. Now remember, the bias was connected with a weight of 1, which means if we take the weighted sum of the bias, right, all we're doing is adding whatever that bias's value was. So if this bias value was 100, then what we do is we add 100. Now I've just written the plus B to explicitly state the fact that we're adding the bias, although it could really be considered as a part of the summation equation because it's another connection to the neuron. Now let's just talk about what this symbol means for anyone that's confused about that. Essentially this stands for sum, I stands for an index, and N stands for what index will go up to. Now N means how many neurons we had in the previous layer, and then what we're doing here is saying Wi, Xi, so we're going to say weight 0, X0 plus weight 1, X1 plus weight 2, X2. It's almost like a for loop where we're just adding them all together, and then we add the B. And I hope that makes enough sense. sense so that we understand that. So that is our weighted sum and our bias. So essentially what we do is we go through and we calculate these values. So if this gets some value, maybe this value is like 0.3, maybe this value is 7, whatever it is, and we do the same thing now at our output neuron. So we take the weighted sum of this value times its weight, and then we take the weighted sum, so this value times its weight, plus the bias. This is given some value here, and then we can look at that value and determine what the output of our neural network is. So that is pretty much how that works in terms of the weighted sums, the weights, and the biases. Now let's talk about the kind of the training process and another thing called an activation function. So I've lied to you a little bit because I've said, I'm just going to start erasing some stuff so we have a little bit more room on here. So I've lied to you and I've said that this is completely how this works. Well, we're missing one key feature that I want to talk about, which is called an activation function. Now remember how we want this value to be in between 0 and 1, right?
I think it's this one.
Well, right now, we can't really guarantee that that's going to happen. I mean, especially if we're starting with random weights and random biases in our neural network, and we're passing this information through, we could get to this point.
I've seen this on some videos about AI where they use the derivatives, the slope of lines on a function to make decisions.
Here, we could have like 700 as our value. That's kind of crazy to me, right? We have this huge value. How do we look at 700 and determine whether this is red or whether this is blue? Well, we can use something called an activation function. Now, I'm going to go back to my slides here, whatever you want to call this notebook, just to talk about what an activation function is. And you guys can see here, you can follow along. I have all the equations kind of written out here as well. So let's go to activation function, which is right here. Okay. So these are some examples of an activation function, and I just want you to look at what they do. So this first one is called rectified linear unit. Now notice that essentially what this activation function does is take any values that are less than 0 and just make them 0. So any x values that are in the negative, it just makes their y 0. And then any values that are positive, it's just equal to whatever their positive value is. So if it's 10, it's 10. This allows us to just pretty much eliminate any negative numbers, right? That's kind of what rectified linear unit does. Now tan h, or hyperbolic tangent. What does this do? This actually squishes our values between -1 and 1. So it takes whatever values we have, and the more positive they are, the closer to 1 they are. The more negative they are, the closer to -1 they are. So can we see why this might be useful, right, for a neural network? And then the last one is sigmoid. What this does is squish our values between 0 and 1. A lot of people call it like the squishifier function, because all it does is take any extremely negative numbers and put them closer to 0, and any extremely positive numbers and put them close to 1. Any values in between, you're going to get some number that's kind of in between that, based on the equation 1 over 1 plus e to the negative z, and this is theta z, I guess, is equal to that. Okay, so that's how that works. Those are some activation functions. Now, I hope that's not too much math for you, but let's talk about how we use them, right? So essentially what we do is at each of our neurons, we're going to have an activation function that is applied to the output of that neuron. So we take this weighted sum plus the bias, and then we apply an activation function to it before we send that value to the next neuron. So in this case, n1 isn't actually just equal to this. What n1 is equal to is n1 is equal to f, which stands for our activation function of this equation, right? So say I equals 0, wi, xi plus b, and that's what n1's value is equal to when it comes to this output neuron. So each of these have an activation function on them. N2 has the same activation function as N1, and we can define what activation function we want to apply at each neuron. Now, at our output neuron, the activation function is very important because we need to determine what we want our value to look like. Do we want it between -1 and 1? Do we want it between 0 and 1? Or do we want it to be some massively large number? Do we want it between 0 and positive infinity? What do we want, right? So what we do is we pick some activation function for our output neuron, and based on what I said, where we want our values between 0 and 1, I'm going to be picking the sigmoid function. So sigmoid, recall, squishes our values between 0 and 1. So what we'll do here is we'll take N1, right? So N1 times whatever the weight is there, so weight 0, plus N2 times weight 1, plus a bias, and apply sigmoid, and then this will give us some value between 0 and 1. Then we can look at that value and we can determine what the output of this network is. So that's great, and that makes sense why we would use that on the output neuron, right? So we can squish our value in between some kind of value so we can actually look at it and determine what to do with it rather than just having these crazy, I want to see if I can make this eraser any bigger. That's much better. Okay. So there we go. Let's just erase some of this. And now let's talk about why we'd use the activation function on like an intermediate layer like this. Well, the whole point of an activation function is to introduce complexity into our neural network. So essentially, we just have these basic weights and these biases, and this is kind of just, like a complex function at this point. We have a bunch of weights, we have a bunch of biases, and those are the only things that we're training and the only things that we're changing to make our network better. Now, what an activation function can do is, for example, take a bunch of points that are on the same plane, right? So let's just say these are in some plane. If we can apply an activation function to these where we introduce a higher dimensionality, so an activation function like sigmoid that is like a higher dimension function, we can hopefully spread these points out and move them up or down off the plane in hopes of extracting kind of some different features. Now, it's hard to explain this until we get into the training process of the neural network, but I'm hoping this is maybe giving you a little bit of idea. If we can introduce a complex activation function into this kind of process, then it allows us to make some more complex predictions. We can pick up on some different patterns. If I can see that, when sigmoid or rectified linear unit is applied to this output, it moves my point up or it moves it down or it moves it in like whatever direction in n-dimensional space, then I can determine specific patterns I couldn't determine in the previous dimension. That's just like if we're looking at something in 2 dimensions, if I can move that into 3 dimensions, I immediately see more detail. There's more things that I can look at, right? And I'll try to do a good example of why we might use it like this. So let's say we have a square, right? Like this, right? And I ask you, tell me some information about this square. Well, what you can tell me immediately is you can tell me the width, you can tell me the height, and I guess you can tell me the color, right? You can tell me it has one face, you can tell me it has 4 vertexes, you can tell me a fair amount about the square, you can tell me its area. Now what happens as soon as I extend the square and I make it into a cube? Well, now you can immediately tell me a lot more information. You can tell me, the height, or I guess the depth, width, height, depth, whatever you want to call it there. You can tell me how many faces it has. You can tell me what color each of the faces are. You can tell me how many vertexes. You can tell me if this cube or this square or this rectangle is uniform or not. And you can pick up on a lot more information. So that's kind of, this is a very oversimplification of what this actually does, but this is kind of the concept, right? Is that if we are in 2 dimensions, if we can somehow move our data points into a higher dimension by applying some function to them, then what we can do is get more information and extract more information about the data points, which will lead to better predictions. Okay, so now that we've talked about this, it's time to talk about how neural networks train, and I think you guys are ready for this. This is a little bit more complicated, but again, it's not that crazy. All right, so we talked about these weights and biases, and these weights and biases are what our network will come up with and determine to, make the network better. So essentially, what we're going to do now is talk about something called a loss function. So as our network starts, right, the way that we train it, just like we've trained other networks or other machine learning models, is we give it some information, we give it what the expected output is, and then we just see what the expected output or what the output was from the network, compare it to the expected output, and modify it like that. So essentially, what we start with is we say, okay, 222, we say this class is red, which I forget what I labeled that was as, but let's just say like that was a 0, okay? So this class is 0. So I want this network to give me a 0 for the point 222. Now this network starts with completely random weights and completely random biases. So chances are, when we get to this output here, we're not going to get 0. Maybe we get some value after applying the sigmoid function that's like 0.7. Well, this is pretty far away from red. But how far away is it? Well, this is where we use something called a loss function. Now what a loss function does is calculate how far away our output was from our expected output. So if our expected output is 0 and our output was 0.7, the loss function is going to give us some value that represents like how bad or how good this network was. Now, if it tells us this network was really bad, it gives us like a really high loss, then that tells us that we need to tweak the weights and biases more and move the network in a different direction. We're starting to get into gradient descent, but let's understand the loss function first. So it's going to say if it was really bad, let's move it more, let's change the weights more drastically, let's change the biases more drastically. Whereas if it was really good, it'll be like, okay, so that one was actually decent. You only need to tweak a little bit, and you only need to move this, this, and this, so that's good. And that's the point of this loss function. It just calculates some value. The higher the value, the worse our network was. A few examples of loss function. Let's go down here because I think I had a few. Optimizer loss, here. Mean squared error, mean absolute error, and hinge loss. Now, mean absolute error, let's actually just look one up here. So mean absolute error. And have a look at what this is. So images, let's pick something. This is mean absolute error. This is the equation for mean absolute error. Okay, so the summation of the absolute value of yi minus lambda of xi over n. Now, this is kind of complicated. I'm not going to go into it too much. I was hoping I was going to get like a better example for mean squared error. Okay, so these are the three loss functions here. So mean squared error, mean absolute error, hinge loss. Obviously, there's a ton more that we could use. I'm not going to talk about how each of these work specifically. I mean, you can look them up pretty easily. And also, so you know, these are also referenced as cost functions, so cost or loss. You might hear these terms kind of interchanged. Cost and loss essentially being the same thing. You want your network to cost the least. You want your network to have the least amount of loss. Okay, so now that we have talked about the loss function, we need to talk about how we actually update these weights and biases. Now, let's go back to here because I think I had some notes on it. This is what we call gradient descent. So essentially, the parameters for our network are weights and biases. And by changing these weights and biases, we will, either make the network better or make the network worse. The loss function will determine if the network is getting better, if it's getting worse, and then we can determine how we're going to move the network to change that. So this is now gradient descent, where the math gets a little bit more complicated. So this is an example of what your neural network function might look like. Now, as you have higher dimensional math, you have, a lot more dimensions, a lot more space to explore when it comes to creating different parameters and creating different biases and activation functions and all that. So as we apply our activation functions, we're kind of spreading our network into higher dimensions, which just makes things much more complicated. Now, essentially what we're trying to do with the neural network is optimize this loss function. This loss function is telling us how good it is or how bad it is. So if we can get this loss function as low as possible, then that means we should technically have the best neural network. So if this is our kind of loss functions like mapping or whatever, what we're looking for is something.
I think I understand what this is. It's kind of like the Newton method. I watched the video on 3 Blue, 1 Brown, where he speaks about finding the slopes, finding the roots of a function by calculating the slope of the derivative and correcting that until the derivative reaches 0. And in that way, you find the minimum spots of the function because, well, it's an algorithm. And that doesn't necessarily mean that is the roots, because sometimes you're going to have local minimums that are just slopes in the function, but they are not crossing the x equals 0 or y equals 0. But it still works. And when you have that case, then you're going to have roots on the complex plane for the ones that don't cross the lines on the graph equals 0. Yeah, it's kind of complicated to explain, but I'm probably gonna watch that video on stream again. I watched, I think, about 5 or 6 times already, each one. And yeah, it's kind of complicated to understand. But I think what this is the same thing that this function is doing, but it's doing on the 3-dimensional plane instead. So you have these values and peaks here. The loss function is trying to figure out where they are based on the probability distribution, and then correcting based on that thing.
Called a global minimum. We're looking for the minimum point where we get the least possible loss from our neural network. So if we start where these red circles are, right, I just stole this image off Google Images, what we're trying to do is move downwards into this global minimum. And this is the process called gradient descent. So we calculate this loss, and then we use an algorithm called gradient descent, which tells us what direction we need to move our function to determine or to get to this global minimum. So it essentially looks where we are. It says this was the loss, and it says, okay, I'm going to calculate what's called a gradient, which is literally just a steepness or a direction, and we're going to move in that direction. And then the algorithm called back propagation will go.
So yeah, this gradient would be the same as calculating the derivative of a function, because with the derivative you're gonna have a line that is tangent to the slope to the function itself, and once the line is or horizontal in relationship to x, the x plane, then it's going to be equal to 0, and it's going to be either a value or a peak of the function.
Backwards through the network and update the weights and biases so that we move in that direction. Now, I think this is as far as I really want to go because I know this is getting more complicated already than some of you guys probably can handle and that I can probably explain. But that's kind of the basic principle. We'll go back to the drawing board and we'll do a very quick recap before we get into some of the other stuff. Neural networks. Input, output, hidden layers. Connected with weights, there's biases that connect to each layer. These biases can be thought of as y-intercepts. They'll simply move completely up or move completely down that entire activation function, right? We're just shifting things left or right because this will allow us to get a better prediction and have another parameter that we can train and add a little bit of complexity to our neural network model. Now, the way that information is passed through these layers is we take the weighted sum at a neuron of all of the connected neurons to it. We then add this bias neuron and we apply some activation function that's going to put this, these values in between two set values. So for example, when we talk about sigmoid, that's going to squish our values between 0 and 1. When we talk about hyperbolic tangent, that's going to squish our values between -1 and 1. And when we talk about rectified linear unit, that's going to squish our values between 0 and positive infinity. So we apply those activation functions and then we continue the process. So n1 gets its value, n2 gets its value, and then finally we make our way to our output layer. We might have passed through some other hidden layers before that. And then we do the same thing. We take the weighted sum, we add the bias, we apply an activation function, we look at the output, and we determine whether we are class Y or we are class Z or whether this is the value we're looking for, and that's how it works. Now we're at the training process, right? So we're doing this, now that's kind of how this worked when we were making a prediction. So when we're training, essentially what happens is we just make predictions, we compare those predictions to whatever these expected value should be using this loss function. Then we calculate what's called a gradient. A gradient is the direction we need to move to minimize this loss.
So now it's finally starting to get interesting to me. And I think my level of understanding of the concepts is a lot more advanced than the level of skill that I have. So I probably need to find exercises on Python, I think, just to train a lot more and become comfortable and familiar with the. I think I'll do more Numpy and Pandas stuff, and then I want to train a lot, so it becomes very intuitive to me, the technical part and the skill itself. Because on a conceptual level, I think I understand everything already.
Okay. So now we have an optimizer. This is kind of the last thing on how neural networks work. Optimizer is literally just the algorithm.
I wish it shows on the scores, at least practical applications and with graphs and stuff. It shows the whole process of building one and applying and then correcting. If it doesn't, then I'll probably search on YouTube as well. So if anyone watches this and you know a good resource to do Python exercises, please let me know. What is an optimizer function? I guess it's this one. Go watch the video first.
Algorithm that does the gradient descent and backpropagation for us. So I mean, you guys can read through some of them here. We'll be using probably the Atom optimizer for most of our examples, although there's lots of different ones that we can pick from. Now, this optimization technique, again, is just a different algorithm. There's some of them are faster, some of them are slower, some of them work a little bit differently. And we're not really going to get into picking optimizers in this course because that's more of an advanced machine learning technique. All right, so enough explaining, enough math, enough drawings, enough talking. Now it is time to create our first official neural network. Now, these are the imports we're going to need. So import TensorFlow TF from TensorFlow, import Keras. Again, so this does actually come with TensorFlow. I forget if I said you need to install that before. My apologies. And then import NumPy as NP, import Matplotlib.pyplot as PLT. All right, so I'm going to do actually similar thing to what I did before. I'm kind of just going to copy some of this code into another notebook just to make sure that we can look at everything at the end and then kind of step through the code step by step rather than all the text kind of happening here. All right, so the dataset and the problem we're going to consider for our first neural network is the fashion MNIST dataset. Now, the fashion MNIST dataset contains 60,000 images for training and 10,000 images for validating and testing, 70,000 images, and it is essentially pixel data of clothing articles. So what we're going to do to load in this dataset from Keras, so this is actually built into Keras, it's meant as like a beginner like testing, training dataset. We're going to say fashion_MNIST equals keras.datasets.fashion_MNIST. Now this will get the dataset object, and then we can load that object by doing fashion_MNIST.loadData. Now by doing this, by having the tuples train images, train labels, test images, test labels equals this will automatically split our data into the sets that we need. So we need the training and we need the testing. And again, we talked about all of that, so I'm going to kind of skim through that. And now we have it in all of these kind of tuples here. All right, so let's have a look at this dataset to see what we're working with. Okay, so let's run some of this code. Let's get this import going. If it doesn't take forever. Okay, let's get the dataset. This will take a second to download for you guys if you don't already have a cache. And then we'll go train images.shape, and let's look at what one of the images looks like. Or sorry, what our dataset looks like. So we have 60,000 images that are 28 by 28. Now what that means is we have 28 pixels, or 28 rows of 28 pixels, right? So that's kind of what our information is. So we're gonna have in total 784 pixels, which I've denoted here. So let's have a look at one pixel. So to reference one pixel, this is what I'm doing. This comes in as a, actually I'm not sure what type of data frame this is, but let's have a look at it. So let's say type of train_images because I want to see that. So that's NumPy array. So to reference the different indexes in this, it's similar to Pandas. We're just going to do 0, 23, 23, which stands for, image 0, 23, and then 23, and this gives us one pixel. So row 23, column 23, which will be that. Okay, so let's run this, and let's see, this value is 194. Okay, so that's kind of interesting. That's what one pixel looks like. So let's look at what multiple pixels look like. So we'll print train_images. And okay, so we get all these zeros. Let's print train images 0 colon. That should work for us. And we're getting all these zeros. Okay, so that's the border of the picture. That's okay, I can't show you what I want to show you. Anyways, 1 pixel, and I wanted to have you guys guess it, is simply just represented by a number between 0 and 255. Now, what this stands for is the grayscale value of this pixel. So we're dealing with grayscale images, although we can deal with 3D, 4D, 5D images as well. Not 5D images, but we can deal with images that have like RGB values. So for example, we could have a number between 0 and 255, another number between 0 and 255, and another number between 0 and 255 for every single pixel, right? Whereas this one is just one simple static value. Okay, so it says that here our pixel values between 0 and 255, 0 being black and 255 being white. So essentially, if it's 255, that means that this is white. If it's 0, that means that it is black. All right, so let's have a look at the first 10 training labels. So that was our training images. Now what are the training labels? Okay, so we have an array and we get values from 0 to 9. Now, this is because we have 10 different classes that we could have for our data set. So there's 10 different articles of clothing that are represented. I don't know what all of them are, although they are right here. So t-shirt, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. Okay, so let's run this class names just so that we have that saved. And now what I'm going to do is just use Matplotlib to show you what one of the images looks like. So in this case, this is a shirt. I know this is printing out kind of weird, but I'm just showing the image. I know it's like different colors, but that's because if we don't define that we're drawing a grayscale, it's going to do this. But anyways, that is what we get for the shirt. So let's go to another image and let's have a look at what this one is. I actually don't know what that is, so we'll skip that. Maybe that's a, what is it, t-shirt or top. This, I guess, is going to be like a dress. Yeah, so we do have dress there. Let's go 4, have a look at this. Yeah, some of these are like hard to even make out when I'm looking at them myself. And then I guess this will be like a hoodie or something. I'm trying to get one that's a sandal to show you guys a few different ones. There we go. So that is a sandal or a sneaker. Okay, so that is kind of how we do that and how we look at the different images. So if you wanted to draw it out, all you do is just make a figure. You just show the image, do the color bar, which is just giving you this. Then you're going to say, I don't want a grid, and then you can just show the image, right? Because if you don't have this line here and you show with the grid, oh, it's actually not showing the grid. That's interesting. Although I thought it was going to show me those pixelated grids, so I guess you don't need that line. All right, so data preprocessing. All right, so this is an important step in neural networks, and a lot of times when we have our data, we have it in these like random forms, or we're missing data, or there's information we don't know, or that we haven't seen, and typically what we need to do is preprocess it. Now what I'm going to do here is squish all my values between 0 and 1. Typically it's a good idea to get all of your input values in a neural network in between like that range. In between, I would say -1 and 1 is what you're trying to do. You're trying to make your numbers as small as possible to feed to the neural network. The reason for this is your neural network starts out with random weights and biases that are in between the range 0 and 1, unless you change that value. So if you have massive input information and tiny weights, then you're kind of having a bit of a mismatch, and you're going to make it much more difficult for your network to actually classify your information because it's going to have to work harder to update those weights and biases to reduce how large those values are going to be, if that makes any sense. So it usually is a good idea to preprocess these and make them in between the values 0 and 1. Now, since we know that we're just going to have pixel values that are in the range of 255, we can just divide by 255 and that will automatically scale it down for us. Although it is extremely important that we do this to not only the training images, but the testing images as well. If you just preprocess your training images and then you pass in new data that's not preprocessed, that's going to be a huge issue. You need to make sure that your data comes in the same form, and that means when we're using the model to make predictions, whatever I guess the pixel data we have, we need to preprocess in the same way that we preprocessed our other data. Okay, so let's preprocess that. So train images and test images, and I'm just going to actually steal some of this stuff here and throw it in my other one before we get too far. So let's get this data set and let's throw it in here, just so we can come back and reference all this together. Let's go class names. We don't actually need the figures, a few things I can skip. We do need this pre-processing step like that. If I can go over here. And then what else do we need? We're going to need this model. Okay, so let's actually just copy the model into this and just make it a little bit cleaner. We can have a look at it. So new code block, model.
Right back. Right, I'm back. This is a lot of information, actually. Wasn't expecting the videos should be this big, this long. Not even halfway through yet. Yeah, but that's the only section, and then the other one is a lot smaller.
Okay, so model. Creating our model. Now, creating our model is actually really easy. I'm hoping what you guys have realized so far is that data is usually the hardest part of machine learning and neural networks. Getting your data in the right form, the right shape, and pre-processed correctly. Building the model is usually pretty easy because we have tools like Tensorflow and Keras that can do it for us. So we're going to say model equals keras.sequential. Now, sequential simply stands for the most basic form of a neural network, which we've talked about so far, which is just information going from the left side to the right side, passing through the layers sequentially, right? Called sequential. We have not talked about recurrent or convolutional neural networks yet. Now, what we're going to do here is go keras.layers.flatten. So sorry, inside here, we're going to define the layers that we want in our neural network. This first layer is our input layer, and what flatten does is allows us to take in a shape of 28 by 28, which we've defined here, and flatten all of the pixels into 784 pixels. So we take this 28 by 28 kind of matrix-like structure and just flatten it out. And Keras will do that for us. We don't actually need to take our matrix data and transform it before passing. So we've done that. Next we have keras.layers.dense 128 activation equals rectify linear unit. So this is our first hidden layer, layer 2, right? That's what I've denoted here. And this is a dense layer. Now, dense, again, means that all of the, the neurons in the previous layer are connected to every neuron in this layer. So we have 828 neurons here. How do we pick that number? We don't know. We kind of just came up with it. Usually it's a good idea that you're going to do this as like a little bit smaller than what your input layer is, although sometimes it's going to be bigger, sometimes it's going to be half the size. It really depends on the problem. I can't really give you a straight answer for that. And then our activation function will define as rectify linear unit. Now we could pick a bunch of different activation functions. There's a ton. We could pick sigmoid, we could pick tanh, which is hyperbolic tangent. It doesn't really matter. And then we're going to define our last layer, which is our output layer, which is a dense layer of 10 output neurons with the activation of softmax. Okay, so can we think of why we would have picked 10 here, right? I'll give you guys a second to think about it based on the fact that our output layer, is supposed to have as many neurons as classes we're going to predict for. So that is exactly what we have 10. If we look, we have 10 classes here. So we're going to have 10 output neurons in our output layer. And again, we're going to have this probability distribution. And the way we do that is using the activation function softmax. So softmax will make sure that all of the values of our neurons add up to 1 and that they're between 0 and 1. So that is our model. We've created the model now. So let's actually run this. See, are we going to get any errors here? Is this going to run? And then we'll run the model, and then we'll go on to the next step, which is actually going to be training and testing the model. Okay, so let's create the model now. Shouldn't get any issues, and we're good. And now let's move on to the next step. I'm forgetting what it is, though, which is training the model. Oh, sorry, compiling the model. Okay, so to compiling the model. So we've built now what we call the architecture of our neural network, right? We've defined the amount of neurons in each layer. We've defined the activation function, and we've defined the type of layer and the type of connections. The next thing we need to pick is the optimizer, the loss, and the metrics we're going to be looking at. So the optimizer we're going to use is Atom. This is, again, just the algorithm that performs the gradient descent. You don't really need to look at these too much. You can read up on some different activation functions, optimizers, if you want to kind of see the difference between them, but it's not crazy. We're going to pick a loss. So in this case, sparse categorical cross entropy. Again, not going to go into depth about that. You guys can look that up if you want to see how it works. And then metrics. So what we're looking for, the output that we want to see from the network, which is accuracy. Now, from kind of right now with our current knowledge, we're just going to stick with this as what we're going to compile our neural networks with. We can pick different values if we want, and these are what we call hyperparameter tuning. So the parameters that are inside here, so like the weights and the biases, are things that we can't manually change, but these are things that we can change, right? The optimizer, the loss, the metrics, the activation function, we can change that. So these are called hyperparameters. Same thing with the number of neurons in each layer. So hyperparameter tuning is a process of changing all these values and looking at how models perform with different hyperparameters change. So I'm not really going to talk about that too much, but that is something to note because you'll probably hear that, this hyperparameter kind of idea. Okay, so we compiled the model now using this, which just means we picked all the different things that we need to use for it. And now on to training the model. So I'm just going to copy this in. Again, remember these parts are pretty syntactically heavy, but fairly easy to actually do. So we're going to fit the model. So fit just means we're fitting it to the training data. It's another word for training, essentially. So we're going to pass it the training images, the training labels, and notice how much easier it is to pass this now. We don't need to do this input function. We don't need to do all that because Keras can handle it for us, and we define our epochs as 10. Epochs is another hyperparameter that you could tune and change if you wanted to. All right, so that will actually fit our model. So what I'm going to do is put this in another code block so I don't need to keep retraining this. So we'll go like that. And let's actually look at this training process. So we've run the model. This should compile, and now let's fit it, and let's see what we actually end up getting. All right, so epoch 1, and we can see that we're getting a loss and we're getting accuracy printing out on the side here. Now, this is going to take a second. This is going to take a few minutes, as opposed to our other models that we made. Or not a few minutes, but a few seconds. When you have 60,000 images and you have a network that's comprised of 784 neurons, 128 neurons, and then 10 neurons, you have a lot of weights and biases and a lot of math that needs to go on. So this will take a few seconds to run. Now, if you're on a much faster computer, you're probably faster than this. But this is why I like Google Collaboratory, because this isn't using any of my computer's resources to train. It's using this. And we can see, like the RAM in the disk. How do I look at this? In this network, Oh, is it going to let me look at this now? Okay, I don't know why it's not letting me click this, but usually you can have a look at it. And now we've trained and we've fit the model. So we can see that we had an accuracy of 91%. But the thing is, this is the accuracy on our testing or our training data. So now if we want to find what the true accuracy is, what we need to do is actually test it on our testing data. So I'm going to steal this line of code here. This is how we test our model. Pretty straightforward. I'll just close this. So let's go to code block. So we have test loss, test accuracy is model.evaluate, test images, test labels, verbose equals 1. Now, what is verbose? I was hoping it was going to give me the thing so I could just read it to you guys, but verbose essentially is just, are we looking at output or not? So like how much information are we seeing as this model evaluates? It's like how much is printing out to the console. That's what that means. And yes, this will just split up kind of the metrics that are returned to this into test loss and test accuracy so we can have a look at it. Now you will notice when I run this, that the accuracy will likely be lower on this than it was on our model. So actually the accuracy we had from this was about 91, and now we're only getting 88.5. So this is an example of something we call overfitting. Our model seemed like it was doing really well on the testing data, or sorry, the training data, but that's because it was seeing that data so often, right? With 10 epochs, it started to just kind of memorize that data and get good at seeing that data. Whereas now when we pass it new data that it's never seen before, it's only 88.5% accurate, which means we overfit our model and it's not as good at generalizing for other data sets, which is usually the goal, right? When we create a model, we want the highest accuracy possible, but we want the highest accuracy possible on new data. So we need to make sure our model generalizes properly. Now, in this instance, like it's hard to figure out how do we do that because we don't know that much about neural networks, but this is the idea of overfitting and of hyperparameter tuning, right? So if we can start changing some of this architecture and we can change maybe the optimizer, the loss function, maybe we go epochs 8. Let's see if this does any better, right? So let's now fit the model with 8 epochs. We'll have a look at what this accuracy is, and then we'll test it and see if we get a higher accuracy on the testing data set. And this is kind of the idea of that hyperparameter tuning, right? Where we just look at each epoch, or not each epoch, we look at each parameter, we tweak them a little bit, and usually we'll like write some code that automates this for us. But that's the idea, is we want to get the most generalized accuracy that we can. So I'll wait for this to train. We're actually almost done, so I won't even bother cutting the video. And then we'll run this evaluation, and we'll see now if we got a better accuracy. Now I'm getting a little bit scared because the accuracy is getting very high here. And sometimes, like you want the accuracy to be high on your training data, but when it gets to a point where it's very high, you're in a situation where it's likely that you've overfit. So let's look at this now, and let's see what we get. So 88.4. So we actually dropped down a little bit, and it seemed like those epochs didn't make a big difference. So maybe if I train it on one epoch, let's have an idea and see what this does. Make your prediction. Do you think we're going to be better? Do you think we're going to be worse? It's only seen the training data one time. Let's run this, and let's see, 89.34. So in this situation, less epochs was actually better. So that's something to consider. A lot of people I see just go like 100 epochs and just think their model is going to be great. That's actually not good to do. A lot of the times you're going to have a worse model because what's going to end up happening is it's going to be seeing the same information so much, tweaking so specifically to that information that it's seen, that when you show it new data, it can't actually classify and generalize on that. All right, so let's go back and let's see what else we're doing now with this. Okay, so now we've done that, we need to make predictions. So to make predictions is actually pretty easy. So I'm actually just going to copy this line in. We'll go into a new code block down here. So all you have to do is say model.predict, and then you're going to give it an array of images that you want to predict on. So in this case, if we look at test images shape, so actually let's make a new code block and let's go here. So let's say
I don't understand the logic on that very well because, yeah, I get it that the model is going to be used to the data set, but isn't that the point of building the model in the first place? Because you can make the argument that less epochs is going to be better because, on some cases, because the model is not going to be trained specifically to that specific data set, is not going to be biased. But then, what if it's just a matter of how can I say this? Not exposing the model to a bunch of different data sets as well. So it's not that it's being more accurate when you use the other data set, it's just that you're training it less often. So yeah. So yeah, in my mind doesn't mean that it's better. It just means that it's less used, let's say, to the training data set. And it's kind of hard to me. I don't think you can say with certainty that it's better or worse. You can't make any conclusions based simply on that, on my mind.
say test underscore images dot shape. All right, give me a second. So we have 10,000 by 28 by 28. So this is an array of 10,000 entries of images. Now, if I just wanted to predict on one image, what I could do is say test images 0 and then put that inside an array. The reason I need to do that is because the data that this model is used to seeing is an array of images to make a prediction on. That's what this predict method needs, and it's much better at making predictions on many things at once than just one specific item. So if you are predicting one item only, you do need to put it in an array because it's used to seeing that form. So we could do this. I'm just going to leave it so we're just going to predict on every single one of the test images because then we can have a look at a cool function I've kind of made. So let's actually do this. Predictions equals model.predict test images. Let's print predictions and look at actually what it is. Where is my autocomplete? There it is. Okay. Let's have a look. Is this some object? Whoa. Okay. So this is arrays of arrays that looks like we have some like really tiny numbers in them. So what this is essentially every single prediction or every single image has a list that represents the prediction for it, just like we've done with kind of the linear models and stuff like that. So if I want to see the prediction for test image 0, let's say prediction 0, right? Let's print this out, and this is the array that we're getting. This is the probability distribution that was calculated on our output layer for these for that image. So if we want to figure out what class we actually think that this is predicting for, we can use a cool function from Numpy called argmax, which essentially is just going to take the index. This is going to return to us the index of the maximum value in this list. So let's say that it was, I'm looking for the least negative, which I believe is this, so this should be 9. This should return to us 9 because this is the index of the highest value in this list, unless I'm just wrong when I'm looking at the negatives here. So 9, that's what we got. Okay, so now if we want to see what the actual class is, well, we have our class names up here. So we know class 9 is actually ankle boot. So let's see if this is actually an ankle boot. So I'm just going to do class underscore names. I think that's what I called it, like this. So that should print out what it thinks it is. Yeah, class underscore names. But now let's actually show the image of this prediction. So to do that, I'm just going to steal some code from here because I don't remember all the syntax off the top of my head. So this. So let's steal this figure. Let's show this and let's see if it actually looks like an ankle boot. So to do that, we're going to say test underscore images 0 because obviously image 0 corresponds to prediction 0. And now we'll show this and see what we get. Okay, so ankle boot, and we'll be looking at that. The image is actually an ankle boot. And we can do this for any of the images that we want, right? So if I do prediction 1. Now let's have a look. Pull over. It kind of looks like a pullover to me. I mean, I don't know if it actually is, but that's what it looks like. We do 2. Let's have a look here. Okay, trouser. Yep, looks like trousers to me. And we can see that is how we get the predictions for our model. We use model.predict. All right, so let's move down here now to the next thing that we did. All right, so we've already done that. So verifying predictions. Okay, so this is actually a cool kind of script that I wrote. I'll zoom out a little bit so we can read it. What this does is let us use our model to actually make, and I'm stealing some of this from Tensorflow, to make predictions on any entry that we want. So what it's going to do is ask us to type in some number. We're going to type in that number. It's going to find that image in the test dataset. It's going to make a prediction on that from the model, and then show us what it actually is versus what it was predicted being. Now, I just need to actually run, actually, let's just steal this code and bring in the other one because I've already trained the model there so we don't have to wait again. So let's go F11, let's go to a new code block and run that. So let's run this script. Have a look down here. So pick a number. We'll pick some number. Let's go 45. And then what it's going to do is say expected sneaker, guess sneaker, and actually show us the image that's there. So we can see this is what our pixel kind of data looks like. And this is what the expected was, and this is what the guess was from the neural network. Now we can do the same thing if we run it again. Pick a number 34. Let's see here, expected bag, guess bag. So that's kind of showing you how we can actually use this model. So anyways, that has been it for this kind of module on neural networks. Now I did this in about an hour. I'm hoping I explained a good amount that you guys understand now how neural networks work. In the next module, we're going to move on to convolutional neural networks, which again should help kind of get your understanding of neural networks up, as well as learn how we can do deep computer vision, object recognition, and detection using convolutional neural networks. So that being said, let's get into the next module.
What's going on here?
Hello everyone, and welcome to the next module in this TensorFlow course. So what we're going to be doing here is talking about deep computer vision, which is very exciting, very cool. This has been used for all kinds of things. You ever seen the self-driving cars, for example, Tesla? They actually use a TensorFlow deep learning model. Obviously very complicated, more than I can really explain here, to do a lot of the computer vision for self-driving. We've used computer vision in the medicine field. Computer vision is actually used in sports a lot for things like goal line technology and even detecting images and players on the field, doing analysis. There's lots of cool things we're doing with it nowadays. And for our purposes, what we're going to be doing is using this to perform classification, although it can be used for object detection and recognition, as well as facial detection and recognition as well. So all kinds of applications. In my opinion, one of the cooler things in deep learning that we're doing right now. And let's go ahead and talk about what we're actually going to be focusing on here. So we're going to start by discussing what convolutional neural network is, which is essentially the way that we do deep learning. We're going to learn about image data. So what's the difference between image data and other regular data? We're going to talk about convolutional layers and pooling layers and how stacks of those work together is what we call a convolutional base for our convolutional neural network. We're going to talk about CNN architectures and get into actually using pre-trained models that have been developed by companies such as Google and TensorFlow themselves to perform classification tasks for us. So that is pretty much the breakdown of what we're about to learn. There's quite a bit in this module. It's probably the more difficult one, or the most difficult one we've been doing so far. So if you get lost at any point, you can't understand some of it, don't feel bad. This stuff is very difficult, and I would obviously recommend reading through some of the descriptions I have here in this notebook, which again you can find from the link in the description, or looking up some things that maybe I don't go into enough depth about in your own time, as I can't really spend 10, 11 hours explaining a convolutional neural network. So let's now talk about image data, which is the first thing we need to understand. So in our previous examples, what we did with when we had a neural network is we had two-dimensional data, right? We had a width and height when we were trying to classify some kind of images using a dense neural network, and well, that's what we use, 2 dimensions. But with an image, we actually have 3 dimensions, and what makes up those dimensions? Well, we have a height and we have a width, and then we have something called colored channels. Now it's very important to understand this because we're going to see this a lot as we get into convolutional networks, that the same image is really represented by 3 specific layers, right? We have the first layer which tells us all of the red values of the pixels, the second layer which tells us all the green values, and the third layer which tells us all the blue values. So in this case, those are the colored channels, and we're going to be talking about channels in depth quite a bit in this series. So just understand that although you think of an image as a 2-dimensional kind of thing, in our computer it's really represented by 3 dimensions where these channels are telling us the color of each pixel. Because remember, in red, green, blue, you have 3 values for each pixel, which means that you're going to need 3 layers to represent that pixel, right? So this is what we kind of think of it as a stack of layers, and in this case a stack of pixels, right? Or a stack of colors really telling us the value for each pixel. So if we were to draw this to the screen, we would get the blue, green, and red values of each pixel, determine the color of it, and then draw the 2-dimensional image, right? Based on the width and the height. Okay, so now we're talking about convolutional neural network and the difference between that and a dense neural network. So in our previous examples, when we used a dense neural network to do some kind of image classification like that fashion MNIST dataset, what it essentially did was look at the entire image at once and determined based on finding features in specific areas of the image what that image was, right? Maybe it found an edge here, a line here, maybe it found a shape, maybe it found a horizontal diagonal line. The important thing to understand though is that when it found these patterns and learned the patterns that made up specific shapes, it learned them in specific areas. It knew that if we're in between, for example, looking at this cat image, we're going to classify this as a cat. If an eye exists on the left side of the screen where the eyes are here, then that's a cat. It doesn't necessarily know that if we flip this cat, we did a horizontal flip of this cat, and the eyes were over here, that is a pattern that makes up a cat. So the idea is that the dense network looks at things globally. It looks at the entire image and learns patterns in specific areas. That's why we need things to be centered, we need things to be very similar when we use a dense neural network to actually perform image classification, because it cannot learn local patterns and apply those to different areas of the image. So for example, some patterns we might look for when we're looking at an image like a cat here would be something like this, right? We would hope that maybe we could find a few ears, we could find the eyes, the nose, and the paws here, and those features would tell us that this makes up a cat. And with a dense neural network, it would find these features, it would learn these patterns, it would only learn them in this specific area where they're boxed off, which means if I horizontally flip this image, right, and I go like that, then it's not going to know that that's a cat because it learned that pattern in a specific area. It'll need to relearn that pattern in the other area. Now, convolutional neural network, on the other hand, learns local patterns. So rather than learning that the ear exists in this specific location, it just learns that this is what an ear looks like, and it can find that anywhere in the image. And we'll talk about how we do that as we get to the explanation, but the whole point is that our convolutional neural network will scan through our entire image, it will pick up features and find features in the image, and then based on the features that exist in that image, we'll pass that actually to a dense neural network or a dense classifier. It will look at the presence of these features and determine the combination of these presences of features that make up specific classes or make up specific objects. So that's kind of the point. I hope that makes sense. The main thing to remember is that dense neural networks work on a global scale, meaning they learn global patterns which are specific and are found in specific areas, whereas convolutional neural networks or convolutional layers will find patterns that exist anywhere in the image because they know what the pattern looks like, not that it just exists in a specific area. All right, so how they work, right? So let's see when a neural network, regular neural network, looks at this dog image. This is a good example. I should have been using this before. It will find that there's two eyes that exist here, right? It'll say, okay, so I found that these eyes make up a dog. This is its training image, for example, and it's like, okay, so this pattern makes up the dog. The eye is in this location. Now, what happens when we do this? And we flip the image to the other side. Well, our neural network starts looking for these eyes, right? On the left side of the image where it found them previously and where it was trained on. It obviously doesn't find them there, and so it says that our image isn't a dog. Although it clearly is a dog, it's just a dog that's orientated differently. In fact, it's just flipped horizontally, right? Or actually, I guess I would say vertically, flipped vertically. So since it doesn't find the eyes in this location, and it can only look at patterns that it's learned in specific locations, it knows that this, or it's going to say this isn't a dog, even though it is. Whereas our convolutional layer will find the eyes regardless of where they are in the image, and still tell us that this is a dog, because even though the dog's moved over, it knows what an eye looks like, so it can find the eye anywhere in the image. So that's kind of the point of the convolutional neural network and the convolutional layer. And what the convolutional layer does is look at our image and essentially feed back to us what we call an output feature map that tells us about the presence of specific features, or what we're going to call filters in our image. So that is kind of the way that works. Now, essentially, the thing we have to remember is that our dense neural networks output just a bunch of numeric values, whereas what our convolutional layers are actually going to be doing is outputting what we call a feature map. I'm going to scroll down here to show you this example. What we're actually going to do is run what we call a filter over our image. We're going to sample the image at all these different areas, and then we're going to create what we call an output feature map that quantifies the presence of the filters pattern at different locations. And we'll run many different filters over our image at a time, so we have all these different feature maps telling us about the presence of all these different features. So one convolutional layer will start by doing that with very small, simple filters such as straight lines like this, and then other convolutional layers on top of that, right? Because it's going to return a map that looks something like this out of the layer. We'll take this map in now, the one that was created from the previous layer, and say, okay, well, if this map is representing to me, for example, the presence of these diagonal lines, let me try to look for curves, right? Let me try to look for edges. So it will look at the presence of the features from the previous convolutional layer, and then say, okay, well, if I have all these lines combined together, that makes up an edge, and it will look for that, right? And that's kind of the way that a convolutional neural network works and why we stack these different layers. Now, we also use something called pooling, and there's a few other things we're going to get into, but that is the basics. I'm going to go into a drawing example and show you exactly how that works, but hopefully this makes a little bit of sense that the convolutional layer returns a feature map that quantifies the presence of a filter at a specific location. And this filter, the advantage of it is that we slide it across the entire image, so if this filter or this feature is present anywhere in the image, we will know about it, rather than in our dense network where it had to learn that pattern in a specific global location.
I think I need to watch this video again. Wasn't paying too much attention
Well,
there.
we have a height and we have a width, and then we have something called color channels. Now, it's very important to understand this because we're going to see this a lot as we get into convolutional networks, that the same image is really represented by three specific layers, right? We have the first layer, and we would get the patterns that made up specific shapes. It learns them in specific areas. It knew that if we're in between, for example, looking at this cat image, we're going to classify this as a cat. If an eye exists on the left side of the screen where the eyes are here, then that's a cat. It doesn't necessarily know that if we flip this cat, we did a horizontal flip of this cat, and the eyes were over here, that is a pattern that makes up a cat. So the idea is that the dense network looks at things globally. It looks at the entire image and learns patterns in specific areas. That's why we need things to be centered. We need things to be very similar when we use a dense neural network to actually perform image classification, because it cannot learn local patterns and apply those to different areas of the image. So, for example, some patterns we might look for when we're looking at an image like a cat here would be something like this, right? We would hope that maybe we could find a few ears, we could find the eyes, the nose, and the paws here, and those features would tell us that this makes up a cat. Now, with a dense neural network, it would find these features, it would learn these patterns. It would only learn them in this specific area where they're boxed off, which means if I horizontally flip this image, right, and I go like that, then it's not going to know that that's a cat because it learned that pattern in a specific area. It'll need to relearn that pattern in the other area. Now, convolutional neural network, on the other hand, learns local patterns. So rather than learning that the ear exists in this specific location, it just learns that this is what an ear looks like, and it can find that anywhere in the image. And we'll talk about how we do that as we get to the explanation. But the whole point is that our convolutional neural network will scan through our entire image. It will pick up features and find features in the image, and then based on the features that exist in that image, we'll pass that actually to a dense neural network or a dense classifier. It will look at the presence of these features and determine the combination of these presences of features that make up specific classes or make up specific objects. So that's kind of the point. I hope that makes sense. The main thing to remember is that dense neural networks work on a global scale, meaning they learn global patterns which are specific are found in specific areas, whereas convolutional neural networks or convolutional layers will find patterns that exist anywhere in the image because they know what the pattern looks like, not that it just exists in a specific area. All right, so how they work, right? So let's see when a neural network, regular neural network, looks at this dog image. This is a good example. I should have been using this before. It will find that there's two eyes that exist here, right? It'll say, okay, so I found that these eyes make up a dog. This is its training image, for example, and it's like, okay, so this pattern makes up the dog. The eye is in this location. Now, what happens when we do this? And we flip the image to the other side. Well, our neural network starts looking for these eyes, right, on the left side of the image where it found them previously and where it was trained on. It obviously doesn't find them there, and so it says that our image isn't a dog. Although it clearly is a dog, it's just a dog that's orientated differently. In fact, it's just flipped horizontally, right? Or actually, I guess I would say vertically, flipped vertically. So since it doesn't find the eyes in this location, and it can only look at patterns that it's learned in specific locations, it knows that this, or it's going to say this isn't a dog, even though it is. Whereas our convolutional layer will find the eyes regardless of where they are in the image, and still tell us that this is a dog, because even though the dog's moved over, it knows what an eye looks like, so it can find the eye anywhere in the image. So that's kind of the point of the convolutional neural network and the convolutional layer. And what the convolutional layer does is look at our image and essentially feed back to us what we call an output feature map that tells us about the presence of specific features, or what we're going to call filters in our image. So that is kind of the way that works. Now, essentially, the thing we have to remember is that our dense neural networks output just a bunch of numeric values, whereas what our convolutional layers are actually going to be doing is outputting what we call a feature map. Now, I'm going to scroll down here to show you this example. What we're actually going to do is run what we call a filter over our image. We're going to sample the image at all these different areas, and then we're going to create what we call an output feature map that quantifies the presence of the filters pattern at different locations. And we'll run many different filters over our image at a time, so we have all these different feature maps telling us about the presence of all these different features. So one convolutional layer will start by doing that with very small, simple filters such as straight lines like this, and then other convolutional layers on top of that, right, because it's going to return a map that looks something like this out of the layer. We'll take this map in now, the one that was created from the previous previous layer and say, okay, well, if this map is representing to me, for example, the presence of these diagonal lines, let me try to look for curves, right? Let me try to look for edges. So it will look at the presence of the features from the previous convolutional layer and then say, okay, well, if I have all these lines combined together, that makes up an edge, and it will look for that, right? And that's kind of the way that a convolutional neural network works and why we stack these different layers. And we also use something called pooling, and there's a few other things we're going to get into, but that is the basics. I'm going to go into a drawing example and show you exactly how that works, but hopefully this makes a little bit of sense that the convolutional layer returns a feature map that quantifies the presence of a filter at a specific location. And this filter, the advantage of it is that we slide it across the entire image, so if this filter or this feature is present anywhere in the image, we will know about it, rather than in our dense network where it had to learn that pattern in a specific global location. Okay, so let's get on the drawing tablet and do a few examples. All right, so I'm here on my drawing tablet, and we're going to explain exactly how a convolutional layer works and how the network kind of works together. So this is an image I've drawn on the left side of our screen here. I know this is very basic, this is just an X, right? This is what our image is. We're just going to assume this is grayscale. We're going to avoid doing anything with color channels this second just because they're not that important, but just understand that what I'm about to show you does apply to color channels as well and to multiple kind of layers and depth. And then if we can understand it on a simple level, we should be able to understand it more thoroughly. So what we want essentially is our convolutional layer to give us some output that's meaningful about this image. So we're going to assume this is the first convolutional layer, and what it needs to do essentially is return to us some feature map that tells us about the presence of specific what we call filters in this image. So each convolutional layer has a few properties to it. The first one is going to be the input size. So what can we expect? Wow, what is that? That was as the input size. How many filters are we going to have? So filters like this. And what's the sample size of our filters? That's what we need to know for each of our convolutional neural networks. So essentially, what is a filter? Well, a filter is just some pattern of pixels. And we saw them before. We'll do a pretty basic one here as the filter we're going to look for, which will look something like this. This will be the first filter we're going to look for, just to illustrate how this works. But the idea is that at each convolutional layer, we look for many different filters. And in fact, the number we're typically looking for is actually about times 32 filters. Sometimes we have 64 filters as well, and sometimes even 128. So we can do as many filters as we want, as few filters as we want, but the filters are what is going to be trained. So this filter is actually what is going to be found by the neural network. It's what's going to change. It's, this is essentially what we're looking for. This is what's created in the program. And that's kind of like the trainable parameter of a convolutional neural network is the filter. So the amount of filters and what they are will change as the program goes on, as we're learning more and figuring out what features that make up, a specific image. So I'm going to get rid of this stuff right now, just so we can draw and do a basic example. But I want to show you how we look for a filter in the image. So we have filters, right? They'll come up with them. They're going to start completely random, but they'll change as we go on. So let's say the filter we're looking for is that one I drew before. I'm just going to redraw at the top here a little bit smaller. And we'll just say it's a diagonal line, right? But another filter we could look for might be something like, a straight line, just like that, all across. We could have a horizontal line, and in fact, we'll have 32 of them. And when we're doing just, 3 by 3 grids of filters, well, there's not that many, combinations we're going to do, at least grayscale wise. So what we'll do is we'll define the sample size, which is how big our filter is going to be 3 by 3, which we know right now, which means that what we're going to do is we're going to look at 3 by 3 spots in our image and look at the pixels and try to find how closely these filters match with the pixels we're looking at on each sample. So what this is going to do, this convolutional layer, is going to output to us what we call a feature map, which is going to be a little bit smaller than the original image, and you'll see why in a second, but it tells us about the presence of specific features in areas of the image. So since we're looking for 2 filters here, actually, we'll do 2 filters, which means that we're actually going to have a depth 2 feature map being returned to us, right? Because for 2 filters, that means we need 2 maps quantifying the presence of both of those filters. So for this green box that we're looking at on the left side here, we'll look for this first filter here. And what do we get? Well, the way we actually do this, the way we look at this filter, is we take the cross product, or actually not the cross product, the dot product, sorry, between this little green box and this filter, right? Because they're both pixels, they're both actually numeric values down at the bottom. So what we do is we take that dot product, which essentially means we're element-wise adding, or was it element-wise multiplying all these pixels by each other. So if this pixel value is 0, right, because it's white, or it could be the other way around, we could say white is 1, black is 0, it doesn't really matter, right? If this is a 0 and this is a 1, these are obviously very different. And when we do the dot product of those two, so we multiply them together, then in our output feature, we would have a 0, right? That's kind of the way it works. So we do this dot product of this entire thing. If you don't know what the dot product is, I'm not really going to go into that. But we do the dot product, and that gives us some value, essentially telling us how similar these two blocks are. So how similar this sample is that we're taking of the image and the filter that we're looking for. If they're very similar, we're going to likely put a 1 or something telling us, they're very close together. If they're not similar at all, we're going to put a 0. So in this case, for our first filter, we're probably going to have a value because this middle pixel is the same, something like 0.12, right? But all the other values are different, so it's not going to be very similar whatsoever. So then what we're going to do now is we'll look at the actually second filter, which is this horizontal line. And in fact, we're going to get a very similar output response here, probably something like 0.12. That's going to go in the top left. And again, these are both maps representing each filter, right? So now we'll move our green box over 1 like this. So just shift that over 1. And now we'll start looking at the next section. And in fact, I'm going to see if I can erase this just to make it a little bit cleaner here. Get rid of the green. There we go. Okay. So we'll move this box over like this. And now we'll start looking at this one. We'll do the exact same thing we did again before. So we're going to say, all right, how similar are these? Well, they're not similar at all. So we're going to get a 0 for that first filter. How similar are the other ones? Oh, actually, they're like a little bit similar. There's a lot of white that's kind of in the same space, like, stuff like that. So we'll say maybe this is like 0.7, right? I'm just randomly picking these numbers. They are going to be much different than what I'm putting in here, but I'm just trying to get you to understand what's kind of happening, right? And this is completely random the way I'm making the numbers. So just make sure you understand that because this is not exactly what it would look like. Okay, so then we're going to move the box over one more time. Let's just erase this to keep this clean. This will be the last time we do this for the purpose of this example. And now what we're going to have is, wow, we have a perfect match for the first filter. So we put 1. The other one's like, it's kind of similar. There's a few things that are different. So maybe this gets like a 0.4 or something, right? Whatever they are, we end up getting some values. So we'll fill in all these values. Let's just put some arbitrary values here for now, just so we can do something with the example. 0.7, 0, 0.12, 0.42. 0.3, 0.9, 0.1, again, completely random, 0.4, 0.6. All right, so this is now what we've gotten, our response map from looking at 2 filters on our original image of 5 by 5. Now notice that the size of these is 3 by 3, and obviously the reason for that is because in a 5 by 5 image, when we're taking 3 by 3 samples, well, we can only take 9 3 by 3 samples, because when we go down a row, right, we're going to move down 1, and we're going to do the same thing we did before of these 3 by 3 samples. And if we add the amount of times we can do that, well, we just get 3 by 3, which is that. So this now is kind of telling us of the presence of features in this original image map. Now, the thing is, though, we're going to do this 64 times, right? For 64 filters or 32 filters, or the amount of filters that we have. So we're going to have a lot of layers, like a ton of different layers, which means that we're going to be constantly expanding as we go through the convolutional layers, the depth of this kind of output feature map. And that means that there's a lot of computations that need to be done, and essentially that means that it's going to be very slow. So now we need to talk about an operation called pooling. So I'll backtrack a little bit, but we will talk about pooling in a second. What's going to happen, right, is when we have all these layers that are generated, so this is called the output feature map, right, from this original image, what we're going to do is the next convolutional layer in the network is now going to do the process we just talked about, except on this output feature map, which means that since this one was picking up things like lines and edges, right, the next convolutional layer will pick up combinations of lines and edges and maybe find what a curve is, right? We'll slowly work our way up from very, very small amount of pixels to finding more and more, almost I want to say abstract different features that exist in the image. And this is what really allows us to do some amazing things with convolutional neural network. When we have a ton of different layers stacking up on each other, we can pick out all the small little edges, which are pretty easy to find. And with all these combinations of layers working together, we can even find things like, say, eyes, right? Or feet, or heads, or face, right? We can find very complicated structures because we slowly work our way up, starting by solving very easy problems, which are like finding lines, and then finding combinations of lines, combination of edges, shapes, and like very abstract things. That's how this convolutional network works. So we've done that now. It's now time to talk about pooling, and I'll also talk about actually we'll go padding first before we go pooling. It doesn't really matter what order we talk about this in, but I just think padding makes sense based on where we're going right now. So sometimes we want to make sure that the output feature map from our original image here is the same dimensions or same size as this. Right? So this is 5 by 5, obviously, and this is 3 by 3. So if we want this to be 5 by 5 as an output, what we need to do is add something called padding to our original image. So padding is essentially just adding an extra row and column on each side of our image here, so that when we just fill in all these pixels and like kind of the padded pixels here as just blank like random pixels, they don't mean anything. Essentially, why we do that is so that when we do our 3 by 3 sample size here like this, we can take a 3 by 3 sample where every single pixel is in the center of that sample. Because right now, this pixel is not in the center, this pixel can never be in the center, this pixel can never be in the center, only a few pixels get to be in the center. And what this allows us to do is generate an output map that is the same size as our original input and allows us to look at features that are maybe right on the edges of images that we might not have been able to see before. Now, this isn't super important when you go to like very large images, but it's just something to consider. You can add padding. We may do this as we get through our examples. And there's also something called stride, which I want to talk about as well. So what a stride is essentially how much we move this sample box every time that we're about to move it, right? So before, let's say we're doing an example with padding here, right? Our first sample we would take here, and again, these pixels are just added. We added them in to make this work better for us. You would assume that the next time we move the box, we're going to move it 1 pixel over. That's called a stride of 1. We can do that, but we also can employ a stride of 2, which means we'll move over by 2. Obviously, the larger your stride, the smaller your output feature map is going to be, so you might want to add more padding. Well, you don't want to add too much padding, but it's just something to consider, and we will use a stride in different instances. Okay, so that's great. That hopefully makes sense. Let's erase this now. We don't need this anymore. We talked about padding, we talked about the stride, and now we're going to talk about a pooling operation, which is very important. So kind of the idea is that we're going to have a ton of layers, right, for all these filters, and we're just going to have a lot of numbers, a lot of computations, and there must be some way to make this a little bit simpler, a little bit easier to use. Well, yes, that's true, and there's a way to do that, and that's called pooling. So there's 3 different types of pooling. Well, there's more, but the basic ones are min, max, and average. And essentially a pooling operation is just taking specific values from a sample of the output feature map. So once we generate this output feature map, what we do to reduce its dimensionality and just make it a little bit easier to work with is we sample typically 2 by 2 areas of its output feature map and just take either the min, max, or average value of all the values inside of here and map these. We're going to go back this way to a new feature map that's twice, like 1 times the size essentially, or not what am I saying, 2 times smaller than this original map. Now it's kind of hard with 3 by 3 to really show you this, but essentially what's going to end up happening is we're going to have something like this. So we're going to take the sample here. We're going to say, okay, what are we doing? Min, max, or average pooling? If we're doing min pooling, we're going to take the smallest value, which means we'll take 0. If we're doing max pooling, we'll take the maximum value, which means we'll take 0.3. If we're doing average, we're probably going to get an average value of close to what? 0.2 maybe? So let's say 0.2, we'll go there. That's how we do that with pooling. Again, just to make this feature map smaller. So we'll do that for both of the filters, but let's just say this is 0.2. Let's say this here that I'm blocking off is, I don't know, what is this going to be? 0.6. It's hard to do this average with 4 numbers. Let's say this one down here is going to be 0. I don't know, let's just do 2.1 or something. And then this last one here, okay, we got some bigger values. Maybe this will be like 0.4. Okay, so that's one. The one down here will have some values of its own. We'll just do squiggles to represent that it has something. And we've effectively done a max pooling operation on this. We've reduced the size of it by about half, and that is kind of how that works. Now, typically what we do is we use a 2 by 2 pooling, or like sample size like that, with a stride of 2, which actually means that we would draw it like this. But since we're not going to do padding on this layer right now, we'll just do a stride of 1, and this is how we pool it. Now, the different kinds of pooling are used for different kind of things. The reason we use a max pooling operation is to pretty much tell us about the maximum presence of a feature in that kind of a local area. We really only care if the feature exists, where it doesn't exist, and average pooling is not very often used, although in this case we did use an average pooling. But, it's just different kinds of pooling. Average tells you about the average presence of the feature in that area. Max tells you about is that feature present in that area at all, and min tells you does it not exist. If it doesn't exist, right, we're just going to have a 0 if there's even 1 0 in that area. So that's the point of pooling. That's the point of convolutional layers. I think I'm done with the whiteboarding for now. We're actually going to start getting into a little bit of code and talking about creating our own convolutional networks, which hopefully will make this a lot more clear. So let's go ahead and get into that.
You can feel my attention getting worse. So I'm thinking maybe I'm gonna watch 1 or 2 more videos and then I'm gonna take a break.
All right.
Last video there, I wasn't paying too much attention.
All right, so now it is time to create our first convolutional neural network. Now we're going to be using Keras to do this, and we're also going to be using the CIFAR image dataset that contains 60,000 images of 10 different classes of everyday objects. Now these images are 32 by 32, which essentially means they are blurs, and they are colorful. Now, I just want to emphasize as we get into this that the reason I'm not typing all these lines out and I just have them in here already is because this is likely what you guys will be using or doing when you actually make your own models. Chances are that you are not going to sit, unless you're a pro at Tensorflow, and I'm not even there yet either with my knowledge of it, and have all the lines memorized and not have to go reference the syntax. So the point is here, as long as you understand why this works and what these lines are doing, you're going to be fine. You don't need to memorize them, and I have not memorized them, and I don't. I look up the documentation, I copy and paste what I need, I alter them, I write a little bit of my own code, but that's kind of what you're going to end up doing, so that's what I'm doing here. So this is the image dataset. We have truck, horse, ship, airplane, notice some everyday regular objects. There is 60,000 images, as we said, and 6,000 images of each class. So we don't have too many images of just one specific class. So we'll start by importing our modules. So Tensorflow, we're going to import Tensorflow.Keras. We're going to use the dataset built into Keras for this. So that's the CIFAR image dataset, which you can actually look at just by clicking at this. It'll bring you and give you information about the dataset, although we don't need that right now because I already know the information about it. And now we're just going to load our images in. So again, this stuff, the way this works is you're going to say datasets.cifar10.load data. Now this loads it in as like a very strange Tensorflow object. That's like a dataset object. So this is different from what we've used before, where some of our objects have actually been like in Numpy arrays where we can look at them better. This is not going to be in that, so just something to keep in mind here. I'm going to normalize this data into train images and test images, but just dividing both of them by 255. Now again, we're doing that because we want to make sure that our values are between 0 and 1 because that's just a lot better to work with in our neural networks rather than large integer values. It just causes some things to mess up sometimes. Now class names, we're just going to define a list here so we have all the class names so that 0 represents airplane, 1 automobile so far until truck. We'll run that block of code here. We'll download this dataset, although I don't think it takes that long to do that. So okay, so wait, I guess that's good. I think we're okay there. And now let's just have a look at actually some of the images here by running this script. So we can see this is a truck. We can change the image index to be 2. We can see this is another truck. Let's go to say 6. We get a bird. And you can see these are really blurry, but that's fine for this example. We're just trying to get something that works all right. Okay, so that's a horse. You get the point. All right, so now CNN architecture. So essentially, we've already talked about how a convolutional neural network works. We haven't talked about the architecture and how we actually make one. Essentially, what we do is we stack a bunch of convolutional layers and max pooling, min pooling, or average pooling layers together in something like this, right? So after each convolutional layer, we have a max pooling layer, some kind of pooling layer, typically to reduce the dimensionality. Although you don't need that. You could just go straight into 3 convolutional layers. And on our first layer, what we do is we define the amount of filters, just like here. We define the sample size, so how big are those filters, an activation function, which essentially means after we apply that, that dot product operation that we talked about, we'll apply rectifier linear unit to that and then put that in the output feature map. Again, we've talked about activation functions before, so I won't go too far into depth with them. And then we define the input shape, which essentially means what can we expect in this first layer. Well, 32 by 32 by 3. These ones we don't need to do that because they're going to figure out what that is based on the input from the previous layer. All right, so these are just a breakdown of the layers. The convolution or the max pooling layers here, 2 by 2 essentially means that what we're going to do is we're going to have a 2 by 2 sample size with actually a stride of 2. Again, the whole point of this is to actually divide or shrink it by a factor of 2 how large each of these layers are. All right, so now let's have a summary. It's already printed out here. We can see that we have, oh wait, is this correct? Mobile net to be 2. I don't think that's correct. That's because I haven't run this one. My apologies on that, guys. This is from something later in the tutorial. We can see that we have column 2D as our first layer. This is the output shape of that layer. Notice that it is not 32 by 32 by 32. It is 30 by 30 by 32 because when we do that sampling without padding, right, that's what we're going to get. We're going to get 2 pixels less because the amount of samples we can take. All right. Next, we have the max pooling 2D layer. So this now says the output shape is 15 by 15 by 32, which means we've shrunk this shape by a factor of 2. We do a convolution on this, which means now we get 13, 13, and we're doing 64 because we're going to take 64 filters this time. And then max pooling again, we go 6 by 6 by 64 because we're going to divide this again by a factor of 2. Notice that it just rounded, right? And then conv 2D, so another layer here, we get 4 by 4 by 64 again because of the way we take those values. So this is what we defined so far, but this is not the end of our convolutional neural network. In fact, this doesn't really mean much to us, right? This just tells us about the presence of specific features as we've gone through this convolution base, which is what this is called, the stack of convolution and max pooling layers. So what we actually need to do is now pass this information into some kind of dense layer classifier, which is actually going to take this pixel data that we've kind of calculated and found, so the almost extraction of features that exist in the image, and tell us which combination of these features map to either, what one of these 10 classes are. So that's kind of the point. You do this convolution base, which extracts all of the features out of your image, and then you use the dense network to say, okay, well, if these combination of features exist, then that means this image is this, otherwise it's this and that, and so on. So that's what we're doing here. All right, so let's say adding the dense layers. So to add the dense layers is pretty easy. Model.add is just how we add them, right? So we're going to flatten all of those pixels, which essentially means take the 4 by 4 by 64 and just put those all into a straight line like we've done before, so just one dimensional. Then we're going to have a 64 neuron dense layer that connects all of those things to it with an activation function of rectifier linear unit. Then our output layer of a dense layer with 10 neurons, obviously 10 because that's the amount of classes we have for this problem. So let's run this here. We'll add those layers. Let's look at a summary and see how things have changed now. So we go from 4 by 4 by 64 to 1024. Notice that is precisely the calculation of 4 times 4 times 64. That's how we get that number here. Then we have a dense layer and another dense layer. This is our output layer. Finally, this is what we're getting is we're going to get 10 neurons out. So essentially just a list of values, and that's how we can determine which class is predicted. So this up to here is the convolutional base. This is what we call the classifier, and they work together to essentially extract the features and then look at the features and predict the actual object or whatever it is in the class. All right, so that's how that works. Now it's time to train. Again, we'll go through this quickly. I believe I've already trained this. This takes a long time to train, so I'm actually going to reduce the epochs here to just be 4. I'd recommend you guys train this on higher, so like 10 if you're going to do it. It does take a while, so for our purposes and for my time, we'll leave it a little bit shorter right now, but you should be getting about a 70% accuracy. And you can see I've trained this previously if you trained it on 10 epochs, but I'm just going to train up to 4. We got a 67, 68%, and that should be fine. So we'll be back once this is trained, and we'll talk about how some of this works. Okay, so the model's finally finished training. We did about 4 epochs. You can see we got an accuracy about 67% on the evaluation data. To quickly go over this stuff, optimizers Adam, we've talked about that before. Loss function is sparse categorical cross entropy. That one, I mean, you can read this if you want. Computes the cross entropy loss between labels and predictions. And I'm going to go into that, but these kind of things are things that you can look up if you really want to understand why they work. For most problems, you can just, if you want to figure out what loss function optimizer to use, just use the basics. Like use Adam, use a categorical cross entropy. If you're using a classification task, you want to do something like this. There's just, you can go up and look kind of all of the different loss functions, and it'll tell you when to use which one. You can kind of mess with them and tweak them if you want. Now history equals model.fit. This is just so we can access some of the statistics from this. Model.fit obviously is just training the data to this test images, test labels, and train images and train labels, where this is the validation data. So evaluating the model. If we want to evaluate the model, we can evaluate it now on the test images and test labels. We're obviously going to get the same thing because the valuation is test images and test labels. So we should get the same accuracy as 67.35, which we do right here. All right, so there we go. We get about 70%. If you guys train this on 10 epochs, you should get close to 70. I'm a little bit lower just because I didn't want to go that high. And that is now the model. I mean, we could use this if we want. We could use predict. We could pass in some image and we could see the prediction for it. I'm not going to do that just because we've already talked about that enough, and I want to get into some of the cooler stuff when we're working with smaller data sets. So the basic idea here is this is actually a pretty small data set, right? We use about 60,000 images, and if you think about the amount of different patterns we need to pick up to classify, things like horses versus trucks, that's a pretty difficult task to do, which means that we need a lot of data. And in fact, some of the best convolutional neural networks that are out there are trained on millions of pieces of sample information or data. So obviously we don't have that kind of data. So how can we work with a few images, maybe like a few thousand images, and still get a decent model? Well, the thing is, you can't unless we use some of the techniques that I'm going to show you. So working with small data sets. So just like I mentioned, it's difficult to create a very good convolutional neural network from scratch if you're using a small amount of data. That is why we can actually employ these techniques. The first one, data augmentation, but also using pre-trained models to kind of accomplish what we need to do. And that's what we're going to be talking about now in the second part of the tutorial. We're going to create another convolutional neural network. So just to clarify, this is created. We've made the model up here already. This is all we need to do to it. This is the architecture, and this was just to get you familiar with the idea. So data augmentation. So this is basically the idea. If you have one image, we can turn that image into several different images and train and pass all those images to our model. So essentially, if we can rotate the image, if we can flip it, if we can stretch it, compress it, shift it, zoom it, whatever it is, and pass that to our model, it should be better at generalizing because we'll see the same image, but modified and augmented multiple times, which means that we can turn a data set, say, of 10,000 images into 40,000 images by doing 4 augmentations on every single image. Now, obviously, you still want a lot of unique images, but this technique can help a lot and is used quite a bit because that allows our kind of model to be able to pick up images that maybe are oriented differently or zoomed in a bit or stretched, something different, right? Just better at generalizing, which is the whole point. So I'm not going to go through this in too much depth, but this is essentially a script that does data augmentation for you. We're going to use this image data generator from the keras.preprocessing.image module. We're going to create an image and data generator object. Now, essentially, what this allows us to do is specify some parameters on how we want to modify our image. In this case, we have the rotation range, some shifts, shear, zoom, horizontal flip, and the mode. Now, I'm not going to go into how this works. You can look at the documentation if you'd like, but essentially, this will just allow us to augment our images. Now, what I'm going to do is pick one arbitrary image from the test image dataset, or test image, I guess, group of photos, whatever you want to call it. I'm going to convert that to an image array, which essentially takes it from the weird dataset object that it kind of is and turns it into a Numpy array. Then we're going to reshape this. So it's in the form 1 comma, which essentially means 1, and then this will figure out what the rest of the shape should be. 1, and then plus the image shape, which is whatever this shape is. So we'll reshape that. And then what we're going to do is we're going to say for batch in dataflow gen.flow. We'll talk about how that works in a second. Essentially, this is just going to augment the image for us and actually save it onto our drive. So in this instance, what's going to happen is this data gen.flow is going to take the image, which we created here, right? And we formatted it correctly by doing these 2 steps, which you need to do beforehand. It's going to save this image as test.jpg, and this will be the prefix, which means there'll be some information after. And it will do this as many times until we break. So essentially, given an image, it will do test 1, test 2, test 3, test 4, test 5, with random augmentations using this until eventually we decide to break out of this. Now, what I'm doing is just showing the image by doing this, and batch 0 is just showing us that first image in there. And that's kind of how this works. So you can mess with the script and figure out a way to use it. I would recommend if you want to do data augmentation, just look into image data generator. This is something that I just want to show you so you're aware of, and I'll just run it so you can see exactly how this works. So essentially, given an image of a truck, what it will do is augment it in these different ways. You can see kind of the shifts, the translations, the rotations, all of that. And we'll do actually a different image here to see what one looks like. Let's just do image, say 20. So we get something different. So in this case, I believe this is maybe like a deer or a rabbit or a dog or something. I don't really know exactly what it is because it's so blurry, but you can see that's kind of the shifts we're getting. And it makes sense because you want to have images in different areas so that we have a better generalization. All right, so let's close that. Okay, so now we're going to talk about using, pre-trained models. Okay, so we talked about data augmentation. That's a great technique if you want to increase the size of your data set. But what if even after that we still don't have enough images in our data set? Well, what we can do is use something called a pre-trained model. Now, companies like Google and Tensorflow, which is owned by Google, make their own amazing convolutional neural networks that are completely open source that we can use. So what we're going to do is actually use part of a convolutional neural network that they've trained already on, I believe, 1.4 million images, and we're just going to use part of that model as kind of the base of our model so that we have a really good starting point. And all we need to do is what's called fine-tune the last few layers of that network so that they work a little bit better for our purposes. So what we're going to do essentially is say, all right, we have this model that Google's trained. They've trained on 1.4 million images. It's capable of classifying, let's say, 1,000 different classes, which is actually the example we'll look at later. So obviously, the beginning of that model is what's picking up on the smaller edges and, kind of the very general things that appear in all of our images. So if we can use the base of that model, so kind of the beginning of it, that does a really good job picking up on edges and general things that will apply to any images, then what we can do is just change the top layers of that model a tiny bit or add our own layers to it to classify for the problem that we want, and that should be a very effective way to use this pre-trained model. We're saying we're going to use the beginning part that's really good at kind of the generalization step, then we'll pass it into our own layers that will do whatever we need to do specifically for our problem. That's what's like the fine-tuning step, and then we should have a model that works pretty well. In fact, that's what we're going to do in this example now. So that's kind of the point of what I'm talking about here is using part of a model that already exists that's very good at generalizing and it's been trained on so many different images, and then we'll pass our own training data in. We won't modify the beginning aspect of our neural network because it already works really well. We'll just modify the last few layers that are really good at classifying, for example, just cats and dogs, which is exactly the example we're actually going to do here. So I hope that makes sense. As we get through, this should be cleared up a little bit, but using a pre-trained model is now the section we're getting into. So this is based on this documentation. As always, I'm referencing everything so you guys can go see that if you'd like. We can do our imports like this. We're going to load a dataset. It actually takes a second to load the dataset, I believe. Oh, maybe not. And essentially the problem we're doing is trying to classify dogs versus cats with a fair degree of accuracy. In fact, we'd like to get above 90%. So this is the dataset we're loading in from Tensorflow datasets as TFDS. This is kind of a weird way to load in. Again, stuff like this, you just have to reference the documentation. I can explain it to you, but it's not really going to help when the next example is going to be a different way of loading the data, right? So long as you know how to get the data in the correct form, you can get it into some kind of Numpy array, you can split it into training, testing, and validation data. You should be okay. And if you're using a Tensorflow dataset, it should tell you in the documentation how to load it in properly. So we'll load it in here. We're training 80% train, we'll go 10% for raw validation and 10% for the testing data. So we've loaded that, and now what we're doing here is just we're going to look at a few images. So this actually creates a function. I know this is a weird thing. This is pretty unique to this example. That allows us to call this function with some integer essentially and get what the actual string representation of that is, so the label for it. And what I'm doing here is just taking 2 images from our raw training dataset and just displaying them, and you can see that's what we're getting here, dog and dog. If I go ahead and take 5, we'll see these are what our images look like, right? So here's an example of a dog, we have cats, right? And so on and so forth. You kind of get the point there. Now, notice though that these images are different dimensions. In fact, none of these images other than these two actually are the same dimension at all. Actually, I don't think these ones are either. So obviously there's a step that we need to do, which is we need to scale all these images to be the same size. So to do that, what we're going to do is write a little function like this. And essentially we'll return an image that is reshaped, so I guess that is reshaped to the image size, which I'm going to set at 160 by 160. Now we can make this bigger if we want, but the problem sometimes is if you make an image that is bigger than, like you want to make your image bigger than most of your dataset examples, and that means you're going to be really stretching a lot of the examples out and you're losing a lot of detail. So it's much better to make the image size smaller rather than bigger. You might say, well, if you make it smaller, you lose detail too, but it's better to compress it smaller than it is to go really big, even just when it comes to the amount of training time and how complex the network's going to be. So that's something to consider. You can mess around with those when you're making your own networks, but again, smaller is typically better in my opinion. You don't want to go too small, but something that's like, half the size of what an average image would be. All right, so we're going to go format example. So we're going to just take an image and a label, and what this will do is return to us just the reshaped image and label. So in this case, we're going to cast, which means convert every single pixel in our image to be a float 32 value because it could be integers. We're then going to divide that by 127.5, which taken is exactly half of 255, and then subtract 1. Then we're going to resize this image to be the image size. So sorry, the image will be resized to the image size, so 160 by 160, and we'll return the new image and the label. So now we can apply this function to all of our images using map. If you don't know what map is, essentially it takes every single example in this case going to be raw train, and applies the function to it, which will mean that it will convert raw train into images that are all resized to 160 by 160, and we'll do the same thing for validation and test. So run that, no issue there. And now let's have a look at our images and see what we get. And there we are. Now I just messed up the color because I didn't add a CMap thing, which I think I needed. Where was the CMap? Anyways, you know what, that's fine for now. This is what our images look like. This is the resize. Now we get all images 160 by 160, and we are good to go. All right, so now let's have a look at the shape of an original image versus our new image. So I mean, this was just to prove that essentially our original shapes were at 262, 409 by some random values, and they're all reshaped at 160, 160 by 3. 3 obviously is the color channel of the images.
Go watch one more, and then we'll take a break.
All right, so picking a pre-trained model. So this is the next step. This is probably one of the harder steps, is picking a model that you would actually like to use the base of. Now we're going to use one called MobileNet v2, which is actually from Google. It's built into TensorFlow itself. That's why I picked it. And all we're going to do is set this. So essentially we're going to say the base model in our code is equal to tf.keras.applications.mobilenet v2, which is just telling us the architecture of the model that we want. And we'll have a look at it down below here in just a second. We'll define the input shape, which is important because this can take any input shape that we want. So we'll change it to 160, 160 by 3, which we've defined up here. Include top, very important, means do we include the classifier that comes with this network already or not? Now in our case, we're going to be retraining parts of this network so that it works specifically for dogs and cats and not for 1,000 different classes, which is what this model was actually aimed to do, is train out 1.4 million images for 1,000 different classes of everyday objects. So we're going to not include the top, which means don't include the classifier for these 1,000 classes. And we're going to load the weights from what's called ImageNet, which is just a specific save of the weights. So this is the architecture, and this is kind of the data that we're filling in for that architecture, so the weights, and we'll load that in, which we have here. So base model, now let's look at it. So let's have a summary. You can see this is a pretty crazy model. I mean, we would never be expected to create something like this by ourselves. This is, teams of data scientists, PhD students, engineers, whatever, right? The experts in the field that have created a network like this. So that's why we're going to use it, because it works so effectively for the generalization at the beginning, which is what we want. And then we can take those features that this takes out. So in 5 by 5 by 1280, which is what I want us to focus on the output of this actual network here. So really, you can see this last layer. We're going to take this and using this information, pass that to some more convolutional layers and actually our own classifier, I believe, and use that to predict versus dogs versus cats. So at this point, the base model will simply output a shape 32 by 5 by 5 by 1280. That's the tensor that we're going to get out of this. That's the shape. You can watch how this kind of works as you go through it. And yes, all right. So we just have a look at this here. What I want to do essentially was just look at what the actual shape was going to be. So 32 5 by 5 by 1280, just because this gives us none until it knows what the input is. And now it's time to talk about freezing the base. So essentially the point is we want to use this as the base of our network, which means we don't want to change it. If we just put this network in right now as the base to our neural network, well, what's going to happen is it's going to start retraining all these weights and biases. And in fact, it's going to train 2.257 million more weights and biases when, in fact, we don't want to change these because these have already been defined. They've been set, and we know that they work well for the problem already, right? They work well for classifying 1,000 classes. Why are we going to touch this now? And if we were going to touch this, what's the point of even using this base, right? We don't want to train this. We want to leave it the same. So to do that, we're just going to freeze it. Now, freezing is a pretty, it just essentially means turning the trainable attribute of a layer off or of the model off. So what we do is just say base model.trainable equals false, which essentially means that we are no longer going to be training any aspect of that. I want to say model, although we'll just call it the base layer for now, or the base model. So now if we look at the summary, we can see when we scroll down to the bottom, if we get there any day soon, that now the trainable parameters is 0 instead of 2.257 million, which it was before, and now it's time to add our own classifier on top of this. So essentially, we've got a pretty good network, right? 5 by 5 by 1280 is our last output, and what we want to do now is take that, and we want to use it to classify either cat or either dog, right? So what we're going to do is add a global average layer, which essentially is going to take the entire average of every single, so 1,280 different layers that are 5 by 5, and put that into a 1D tensor, which is kind of flattening that for us. So we do that global average pooling, and then we're just going to add the prediction layer, which essentially is going to just be one dense node. And since we're only classifying 2 different classes, right, dogs and cats, we only need 1. Then we're going to add all these models together. So the base model, no, I guess layers, the global average layer that we define there, and then the prediction layer to create our final model. So let's do this. Global average layer, prediction layer, model. Give that a second to kind of run there. Now when we look at the summary, we can see we have MobileNet v2, which is actually a model, but that is our base layer, and that's fine because the output shape is that. Then global average pooling, which again just takes this, flattens it out, does the average for us. And then finally our dense layer, which is going to simply have 1 neuron, which is going to be our output. Now notice that we have 2.259 million parameters in total, and only 1,281 of them are trainable. That's because we have 1,280 connections from this layer to this layer, which means 1,280 weights and 1 bias. So that is what we're doing. This is what we have created now. This base, the majority of the network has been done for us, and we just add our own little classifier on top of this. And now we're going to feed some training samples and data to this. Remember, we're not training this base layer whatsoever, so the only thing that needs to be learned is the weights and biases on these 2 layers here. Once we have that, we should have a decent model ready to go. So let's actually train this now. I'm going to compile this here. I'm picking a learning rate that's very slow. Essentially what the learning rate means is how much am I allowed to modify the weights and biases of this network, which is what I've done. Just made that very low because we don't want to make any major changes if we don't have to, because we are using a base model that exists, right? So we'll set the learning rate. I'm not going to talk about what this does specifically, you can look that up if you'd like to. And then the loss function will use binary cross entropy just because we're using two classes. If you're using more than two classes, you just have cross entropy or some other type of cross entropy. And then what we're going to do is actually evaluate the model right now before we even train. So I've compiled it. I've just set what we'll end up using. But I want to evaluate the model currently without training it whatsoever on our validation data, our validation batches, and see what it actually looks like. What we're getting right now with the current base model being the way it is, and not having changed the weights and biases to completely random from the global average pooling and the dense layer. So let's evaluate. Let's see what we get as an accuracy. Okay, so we actually see that with the random weights and biases for those last layer that we added, we're getting accuracy of 56%, which pretty much means that it's guessing, right? It's 50% is like two classes. So if we got anything lower than 50, like 50 should have been our guess, which is what we're getting. So now what we're going to do, and actually I've trained this already, I think, so I might not have to do it again, is train this model on all of our images and cats and dogs that we've loaded in before, which will allow us now to modify these weights and biases of this layer. So hopefully it can determine what features need to be present for a dog to be a dog and for a cat to be a cat, right? And they can make a pretty good prediction. In fact, I'm not going to train this in front of us right now because it actually takes close to an hour to train, just because there is a lot of images that it needs to look at and a lot of calculations that need to happen. But when you do end up training this, you end up getting an accuracy of close to 92 or 93%, which is pretty good considering the fact that all we did was use an original layer, like base layer, that classified up to 1,000 different images, so very general, and applied that just to cats and dogs by adding our dense layer classifier on top. So you can see this was kind of the accuracy I had from training this previously. I don't want to train again because it takes so long, but I did want to show that you can save a model and load a model by doing this syntax. So essentially, on your model object, you can call model.save, save as whatever name you like, .h5, which is just a format for saving models in Keras. It's specific to Keras, not TensorFlow. And then you can load the model by doing this. So this is useful because after you train this for an hour, obviously you don't want to retrain this if you don't have to actually use it to make predictions, so you can just load the model. Now, I'm not going to go into using the model specifically. You guys can look up the documentation to do that. We're at the point now where I've showed you so much syntax on predicting and how we actually use the models. But the basic idea would be to do model.predict, right? And then you can see that it's even giving you the input here. So model.predict, give it some x, batch size, verbose, right? Because it will predict on multiple things, and that will spit back to you a class, which then you can figure out, okay, this is a cat or this is a dog. You're going to pass this obviously the same input information we had before, which is 160 by 160 by 3, and that will make the prediction for you. So that's kind of the thing there. I was getting an OS error just because I hadn't saved this previously, but that's how you save and load models, which I think is important when you're doing very large models. So when you fit this, feel free to change the epochs to be something slower if you'd like. Again, right, this takes a long time to actually end up running. But you can see that the accuracy increases pretty well exponentially from when we didn't even have that classifier on it. Now, the last thing that I want to talk about is object detection. I'm just going to load up a page. We're not going to do any examples. I'm just going to give you a brief introduction because we're kind of running out of time for this module, because you can use TensorFlow to do object detection and recognition, which is kind of cool. So let's get into that now. Okay, so right now I'm on a GitHub page that's built by TensorFlow here. I'm going to leave that link in the notebook where it said object detection so you guys can look at that. But essentially, there is an API for TensorFlow that does object detection for you. And in fact, it works very well and even gives you confidence scores. So you can see this is what you'll actually end up getting if you end up using this API. Now, unfortunately, we don't have time to go through this because this will take a good amount of time to talk about the setup and how to actually use this project properly. But if you go through this documentation, you should be able to figure it out. And now you guys are familiar with TensorFlow and you understand some of the concepts here. This runs a very different model than what we've discussed before. Unfortunately, again, we don't have time to get into it, but just something I wanted to make clear is that you can do something like this with TensorFlow, and I will leave that resource so that if you'd like to check this out, you can use it. There's also a great module in Python called facial recognition. It's not part of TensorFlow, but it does use some kind of convolutional neural network to do facial detection and recognition, which is pretty cool as well. So I'll put that link in here, but for now, that's going to be our convolutional neural network kind of module. So I hope this has cleared some things up on how deep vision works and how convolutional neural networks work. I know I haven't gone into crazy examples, but I've shown you some different techniques that hopefully you'll go look up kind of on your own and really dive into, because now you have that base kind of domain knowledge where you're going to be able to follow along with the tutorial and understand exactly what to do. And if you want to create your own model, so long as you can get enough sufficient training data, you can load that training data into your computer, put that in a Numpy array. Then what you can do is create a model like we've just done using even something like the mobile nets, what is it, V2 that we talked about previously. If I can even get up, I need to close this output. Oh my gosh, this massive output here. Where is this? Bigger pre-trained model. Yeah, mobile net V2. You can use the base of that and then add your own classifier on, do similar things what I've done with that dense neuron and that global average layer, and hopefully you should get a decent result from that. So this is just showing you what you can do. Obviously, you can pick a different base layer depending on what kind of problem you're trying to solve. So anyways, that has been convolutional neural networks. I hope you enjoyed that module. Now we're on to recurrent neural networks, which is actually going to be pretty interesting. So I'll see you in that module.
Yeah, I'm gonna pause now, and I'm gonna take a break and probably come back later today. If not, tomorrow probably. I'll see. So, see you then.